Hello guys, this is Saeed Mohammad Wakas. Today I'm gonna talk about complete HVAC design course. It's going to be a 7 hours long session. As you can see here, there are total 24 topics will be covered in this HVAC design course. So I'm gonna discuss them one by one. So I'm gonna use this software Cool Selector provided by Danfoss for cold storage room design. So first let's move back to our Excel sheet. You can see that this is our cold storage room which we are going to design. This is the length, this is the width, and this is the height. So room dimensions are given in here, and these are the inner dimensions: length 10 meter, width 5 meter, height 4 meter. And panel insulation which we used in here is polyurethane 100 mm thickness, and floor is made of concrete, and there is no insulation we used in here, so it's not insulated floor. And ambient condition is depends on location. So I'm talking about Abu Dhabi, UAE. So Abu Dhabi ambient condition is 46 degrees Celsius, so that means 115 degrees Fahrenheit. So ambient condition of Abu Dhabi is 46 degrees Celsius, that means outside temperature. And the surrounding conditions means the temperature of the spaces adjacent to this cold storage room. So normally we keep temperature 22.5 to 26 degrees Celsius for surroundings. So let's say we keep here is 23 degrees Celsius of the surrounding temperature, surrounding spaces temperature, and humidity we keep for thermal comfort is like 50 to 60%. So here we have taken 55% relative humidity. And below floor temperature is 12 degrees Celsius we kept in here. Normally we keep 10 to 12, so I kept 12 here. And this is the most important thing for cold storage room design, that is goods, what type of goods you are going to store, their storage life and storage temperature. So the goods which we are going to store inside here are the vegetables, and in vegetables we are storing broccoli. In here you can see that broccoli we are going to store inside. And storage life and storage temperature. So where you will get this data, storage life and storage temperature? This is the table: recommended temperature, relative humidity, approximate storage life of the fruits and vegetables is given in here, provided by the agricultural department. You can see that different products are given in here, from arranged alphabetically from A to Z, and their storage temperature is given in here, relative humidity and approximate storage life is given here. So we are talking about broccoli. So you can see this is the broccoli. So you can see that the storage temperature is 0 degrees Celsius, that means 32 degrees Fahrenheit, and relative humidity is 95 to 100, and approximate storage life is like 10 to 14 days, so maximum 2 weeks we can store. So let's move back to our software Cool Selector, which we are going to use to design cold storage room. So first of all, this is the main interface. First of all, you have to go to commercial applications, and here you will find the cold room. So you have to select this cold room, and you select cold room, this screen will pop up. There you find two methods to design the cold room. First one is wizard type, and second one is manually defined. So what is the difference between these two methods? Manually defined method is used only when you know all the parameters, then you will use this manual defined cold room. If you don't know some of the parameters, like in our case, we don't know the quantity of the food or mass of the food, how much food will be stored inside. So this is one of the important parameter. So that's why we're going to use this wizard type, because it will help you to estimate some parameters, like you don't know, like quantity of the goods, it is not known, so it is recommended to use this wizard type. So I'm going to use this wizard type. When you select this one, this screen will pop up. You have to give the dimensions. So make sure we have inner dimension, so make sure that inner dimension selected, and you can see in here length is 10 meter, width is 5, and height is 4. So it's 10 meter, this width is 5, and height is 4 meters. So after that you have to give the room surroundings temperature, like They have to give the temperature conditions adjacent to this cold storage room. So as we said that we have maintained 23 degrees Celsius with 55% relative humidity in the surroundings. So we have to change this to 23 degrees Celsius and relative humidity 55%, and temperature below floor we said it's 12 degrees Celsius. So 12 degrees Celsius, and floor is uninsulated, is not insulated, so I'm gonna uncheck this one, and after that you have to select next. Now you have to check what kind of goods you want to store in the cold storage room. So here the different types of products are given in here. So in our case we said that we are going to store broccoli vegetables, so we have to select the vegetables from here, vegetables, and the quantity per day we don't know the quantity. So how we can do that one, we will estimate the mass of the goods from the room volume. We know the room volume, so we can estimate. So estimate mass from the room volume, you have to select this one, and then this screen will pop up, and then you have to give the two things in here: first, percentage of the room used for the goods, and second, percentage of the goods changed each day. So percentage of the goods which will occupy in the room, we don't want to fill up like 80% or 90%. We need to keep two things in mind while giving this percentage of the room used for the goods. We want to keep the space so that person can easily move in between the racks, and he can easily remove the goods, or he can easily place the goods. So we need to keep that thing in mind. Also we need to keep in mind that we don't want to place goods too much close that there will be no air circulation between the goods. So we want to keep a little space between the goods so that air can easily flow in between the goods. So in order to that, we will keep percentage of the room goods like 60%. So that means 60% of this room volume will be occupied by the goods, and 40% will be empty, so that person can easily walk in, and there's a gap between the goods. So percentage of the goods changed each day. Obviously you will gonna put some new foods, and the new food will be replaced by the used food. So you have to, every day you have to replace the food. So percentage of the goods change each day, we're gonna change this one to, like, let's say 10% of the goods we are changing each day. So we'll change this to 10%. So after that you have to select OK. And one more thing, as you can see that when we estimated, then total mass in the room is 54,000 kgs, and quantity per day is 5,400 kg. That means we have to replace this quantity every day, 5,400. So here you have to consider one more thing, that is inlet temperature. Inlet temperature by default it's 5.5 degrees Celsius. So how we select the inlet temperature, it depends on the storage temperature. So if storage inlet temperature should be 5 degrees above the storage temperature by default, because the goods are assumed to be pre-cooled before storing in the cold storage room. So we keep 5 degrees inlet temperature 5 degrees above the cold storage temperature. So here cold storage temperature, a cold room storage temperature is 0 degrees Celsius for broccoli. So 5 degrees above, that means we have to keep 5 in here. So after that you have to select next, and the storage temperature, we know that we just checked from the Excel sheet. Broccoli storage is 0 degrees Celsius, so we will change this one to 0 degrees Celsius. And relative humidity is from 95 to 100%, so we'll keep the 95 same. And based on this storage temperature and relative humidity, operating hours will be calculated, that is 12.6 hours. That means our refrigeration system should run 12.6 hours to maintain 0 degrees Celsius storage temperature and 95% relative humidity. If we change the relative humidity from 95 to, let's say, 98%, and then estimate the operating hours again, then operating hours will be changed and it will be reduced. So let's estimate operating hours again, and now operating hours is 11.1 hours. So it depends on storage temperature and relative humidity. So let's change it back to 95 and keep the operating hours 12.6 for this refrigeration system. And we know that the insulation panels which we used in here are polyurethane 100 mm thickness. So we're going to select the same polyurethane and we are going to select 100 mm thickness. After that you have to select this one and this screen will pop up. Here you can review your cold room load. You can see or you can edit the parameters in here. If you want to change, you can change in here. So now air exchange, which we did not define before, let's talk about this one. Temperature, we know that 23 degrees Celsius and 55% relative humidity in the surroundings area. So now talk about the door opening. Since we kept 10% of the goods changed each day, so that means door will be open, you can say that it's regularly. Here we have three options in here: often, regular and rare. Since we are changing like 10% of the goods, and you know that the mass of the good which we can store is for maximum 2 weeks. It's not a very long period, it's like a short period. If you see that some of them store even for 6 months, 7 to 8 weeks, 4 to 8 weeks, so this is a short storage period. So that means door will open like regularly. It's not, if it is like very long period, then we can keep like door is open rarely. So that because of the long short storage time, we will keep this one like regularly. So if you change this one, you can see that based on this regular and our input parameters, air exchange rate is automatically calculated. You can even change this one if you want, but it is calculated based on our parameters. So if you change this one to, you can see 3.54 it's now. If you change this one to rare, it will decrease 2.12. So in our case it is regular, we're opening the door because of the low storage, less storage time. So it's regular. So after that you have to select the panels. Here you will calculate the heat load or heat transfer. So one is standard option available, other is custom. I'm gonna select the custom panel. The reason I'm selecting custom panel because left side, right side, front side, there we have a conditioned space in the surrounding, but the back side of this cold storage room, it is open, it is like exposed to the sun or exposed to the ambient conditions. So that's why I'm going to select custom panel. So here you can see the front, left, right, back, ceiling and floor. So front will keep, we know that the surrounding temperature is 23 degrees Celsius, we talked in the first place. So we're going to change this one to 23. Left is also 23, right is also 23, and the back side we said that is exposed to the sun or exposed to the ambient condition. We know the ambient condition is 46 degrees Celsius in Abu Dhabi. So I'm going to change this to 46. Back side 46. Ceiling I'm going to take same 23. And the floor we said that we kept 12. And we said that it is not insulated, so we will uncheck this one. So once you are done with the heat transfer, let's move to our this additional loads. So based on the room area, the lightning load is automatically calculated, that is 400 watt. So how did we get this 400 watt? You know that the length and the width, length is 10 and width is 5. So 10 cross 5, that is 50 square meters. So based on 8 watt per square meter thumb rule, this lightning load is calculated. So 8 watt per square meter means multiply with 8, you will get 400 watts. So 400 watt is calculated automatically in here based on 8 watt per square meters. So instead of using this 8 watt per square meter, I will go more precisely and I will take the electrical load sheet. I will check from there how many lights are used inside the cold storage room. Let's say we have used 8 light bulbs, each with 40 watt. So 40 watt for each and 8 light bulbs, that means 320 watt is the total. So I will change this one to 320 watts. So based on our input parameters, the fan power is automatically calculated, that is almost 500 watt. And number of and then people, how much time people will spend inside this cold storage room. Obviously you have to store the material inside, and then you have to remove the goods for the usage. So how much time people will consume inside? So since we said that door opening is regular, so we will keep this same 2 hours per day. If we had kept this one to rare, then we can change this to 1 hour per day. So in the whole day it will be 1 hour per day. But since we said that door opening is regularly, so that's why we keep this 2 hours per day. And you can see that the additional other load, if you have any equipment inside this cold storage room, then you have to add that load also in here. And the last thing here is a defrost. You can see that the defrost heater, this power is basically defrost heater power. And you can see there are two options available in here. One is electric, other is natural. Since natural is not available in here, the reason why it is not available, because room temperature, storage temperature which we selected is 0 degrees Celsius. At 0 degrees Celsius, natural defrost is not possible. Minimum 4 degrees Celsius temperature is required for natural defrost. Let's say if I change this to 4 degrees Celsius, then you can see that natural option will be available. So if I change this to 4, you can see that natural defrost is available. Since in our case storage temperature is 0, we'll keep it 0. And by default electric heater, defrost heater is selected in here, and automatically we have calculated the power based on the inputs, that is 3571 watt. And the defrost per day, we're gonna keep this one 3 by default, because when we open the door, very average amount of humidity it will enter. So we'll keep defrost 3 times per day. So if it was door opening was rare, so we can keep this defrost 1 time per day. So since this is regular, so we can keep defrost 2 to 3 times. We kept 3 times. So after that you have to select next, and then you will select the region of your area. So since I'm talking about the Middle East, UAE, United Arab Emirates, so I'm gonna select Middle East. And then the types of preferred type, I'm gonna prefer like Optima, or whatever your preference, you can select accordingly. So you can select Optima, and then select your refrigerant, what type of refrigerant you want to select in here. So I'm gonna select R134A because this is environmental friendly, so just select this one. Next. So once you select this one, you can see that your load summary, total required cooling load is 10.06 kilowatt. And cold room temperature condition which we selected, you can see in here. Operating hours based on storage temperature and relative humidity is 12.6 hours the refrigeration system will run. And here are the different types of loads you can see in here. Calculated transmission load, infiltration, goods respiration, cooling, light, fan, defrost. Total load is 10.06 kilowatt. And based on our inputs, you can see that the dew point temperature calculated is -8 degrees Celsius, and superheat calculated is 5.2 Kelvin. And after that you have option like thermostatic expansion valve material, what kind of thermostatic expansion valve you want, like stainless steel or brass. So I'm gonna select the brass in here. So after that you have to select, it will generate the equipments for you, best equipments suited for your application. You can see that this is a condensing unit which they have selected for our case based on our load calculation. So you can see that this is the unit which they have selected, OPMGUE148M LA060. So based on the condensing unit, it has also selected the controller for us. So if you select this condensing unit, you can see that the performance in here, you can see that envelope over here, you can see the performance details in here. You can see other information like technical data. If you want to check, you can check technical data. You can check the spare parts, you can check the electrical specifications, like how much is the fan current, is 1 amps, fan power consumption is 500 watt. Or you can select this performance, and you can read the data in here also. R134A refrigerant, total cooling kilowatt is 10.64, Also, you can generate a report. You just go to the report, and then you have to go here, left side, cold room 1, and whatever you want to include in your report you can select. Like if you want technical data, cooling capacity, power consumption, you want the current, you want the COP. So after that you just update here and it will update the report. So now it has updated the report. You can read. So you can see the refrigerant, you can see the evaporating pressure, everything is in here. You can see the charts. So even if you want to save it in the PDF, you just go to PDF and then you have to select OK and then save it wherever you want. You can just give the location and then save it. I'm gonna save on desktop, save it. Also if you want, you can see the report in here also. Also if you want to edit in your report, if you want to make some changes, so you just go back to your selection and then you have to go to edit selection. It will take you back what type of method you want to select, again wizard, or we selected the wizard, so we'll just select the wizard, this one, and it will remember the inputs which you put in here, so you don't have to change, you just have to next, and then if you want to make any changes you can make the changes. So this is how you can design your cold storage room based on your information, like what kind of vegetable or fruit you are going to store and the relative humidity. Every data is given in here, so based on this you have to give the input storage temperature, relative humidities, everything. Today I'm going to explain you guys about the expansion tank sizing procedure. So before starting the calculation, I want to explain you guys about expansion tank, what is expansion tank and why we are using expansion tank in our system. So expansion tanks are basically required in a closed loop heating or chilled water system to absorb the expanding fluid and limit the pressure within the heating or cooling system. So it is important to properly size your expansion tank, because a properly sized expansion tank will accommodate the expansion of system fluid during the heating or cooling cycle without allowing the system to exceed the critical pressures. Also, expansion tank basically uses the compressor to maintain the system pressure by accepting and expelling the changing volume of water as it heats and cools. So this is the chiller yard drawing I have over here. As you can see, let me zoom it. This is the expansion tank that is connected to our system or pressurization pump set. As you can see, this expansion tank. So basically today we are going to do the expansion tank sizing, and in the end I will explain you guys about the position or location of the expansion tank where we need to put our expansion tank. So make sure to watch the video till the end to get the better understanding of the expansion tank sizing. So let's start moving to the calculation procedure of the expansion tank. I have made this Excel sheet. First of all, we have this sheet that is related to expansion tank sizing formula. Second one is basically related to system volume calculation, and the third one I have prepared over here for different charts and tables we are going to use during our calculations. So let's start this expansion tank sizing. So this is the formula which we are going to use to calculate the expansion tank size. So what is this formula? Let's look at this. Vt is equal to Vs into V2 divided by V1 minus 1 minus 3 alpha delta T divided by 1 minus P1 by P2. So what are these parameters in this formula? First we need to understand what are these parameters. Only then we are able to calculate the size of expansion tank.
So what is VT? VT is basically the volume of the expansion tank, which we are going to calculate in gallons or cubic feet or cubic meter. And Vs is the volume of the system. Volume of the system means that all the pipes which we have used in our project, all of the volume occupied by the pipes and equipments, everything. It is the sum of all of the pipes and equipments volume. So we will calculate this one. And V1 is the specific volume of the water at low temperature, and V2 is the specific volume of the water at high temperature. And this P1 is low pressure, and the minimum pressure we took over here is 20 psi, the minimum pressure we can take for our system. And P2 is the higher pressure. Alpha is the linear coefficient of thermal expansion. It depends on material. This alpha value depends on material. Which material you are going to use, you need to put the value over here. So let me go to the third tab, that is tables and chart, to show you the value of alpha, that is linear coefficient of thermal expansion. So as you can see over here, there I have a material list for aluminium, carbon steel, cast iron, copper, and this is the thermal expansion coefficient for all the materials. So since we are working on chilled water system and the material which we use over here is carbon steel, so alpha value over here is 6.5 into 10 to the power minus 6 inches per inches degrees Fahrenheit. So this value we are going to use in our calculation because we are using black carbon steel material. So 6.5 into 10 to the power minus 6. So this is the value which I have used over here for the alpha. And delta T is equal to higher temperature minus lower temperature difference, and this is 66 degrees Fahrenheit. T1 is the lower temperature, T2 is the higher temperature. Now what is lower temperature? T1. T1 is basically our chilled water supply temperature, that is 44 degrees Fahrenheit. And T2 is the higher temperature or our ambient temperature on the location which I am working on. Let's say the location ambient temperature is 110 degrees Fahrenheit in which I am working with. So and T1 is the chilled water supply temperature. So delta T is equal to T2 minus T1. So our temperature difference will be delta T equal to this T2 minus T1, ambient temperature minus chilled water supply temperature. That comes out to be 66 degrees Fahrenheit. So now we have to calculate volume P1, specific volume of the water at lower temperature. Now how this value comes out, I will show you. So we know that our lower temperature chilled water supply temperature is 44 degrees Fahrenheit. Now we have to calculate the specific volume of the water at this lower temperature. So let's move back to our tables and charts to get this value. So 44 degrees Fahrenheit. So this table is in degrees Celsius and this one in Fahrenheit. As we know that our temperature is 44 degrees Fahrenheit, since we don't have 44 here, we have 40 and 50, and specific volume is same, 0.01602 at 40 degrees Fahrenheit and 0.01602 at 50 degrees Fahrenheit. So we can take this value at 44 degrees Fahrenheit, that is 0.01602 cubic feet per lb. So at 44 degrees Fahrenheit we have a specific volume of 0.01602 cubic feet per lb. And the specific volume of the water at higher temperature and higher temperature ambient temperature is 110 degrees Fahrenheit. So move back to our table and chart again. As you can see that there is 110 degrees Fahrenheit and specific volume of the water over here is 0.01617. So we can use this value 0.0167 cubic feet per lb at 110 degrees Fahrenheit. So this is value which I have right over here. So now we have to calculate the high pressure, that is 45 psi. How this comes out? P2 is basically our system maximum pressure. System maximum pressure is basically the pump head loss, which we have already calculated. If you have seen my previous videos related to chilled water pump head calculation, you can calculate the pump head and you can use that value over here to calculate your expansion tank size. So let's say the pump head which we have calculated over here is 70 feet. So we need to convert this into psi. In order to convert this into psi, you need to multiply this jet water pump head with 0.433, and you need to add 14.7 in order to convert this absolute to the gauge pressure. So total formula is this pump head into 0.433 plus 14.7. So P2 is the higher pressure we got over here is 45.01 psi. So now we have everything except system volume, we will calculate now. So now we have V2, V1, we have alpha value for the material, that is black carbon steel 0.000065, and we know the pressure P1, minimum pressure of our system is 20 psi and the high pressure is 45 psi. So only thing remaining over here is volume of the system, Vs. So let's move back to our second tab in order to calculate the volume of water in system. I have divided this into two parts. First part is related to the pipes, all of the pipes which we used in our project, and second part is related to the equipment side, water content. So first part, so let's say that this is all of the pipes which I have used in my project. I have to write over here. I need to mention the lengths which I have used in my system. Let's say that I have write everything, and the third tab is related to weight of water in pipe, that is lb per feet. How much lb per feet is required for that much this pipe size. So let's say we have a 2-inch pipe, and move to the right side. This is the water content table which we are going to use. We can say that 2-inch pipe size, how much lb per feet of the water is required. 2 feet, this is the weight in lb per feet. 2 inches weight per lb per feet, how much weight is required, that is 1.36. So as you can see that 1.36 is required for 2-inch pipe size. And let's say 8-inch, how much weight of the volume is required. 8 inches weight of the weight lb per feet, that is 21.8. So you have to write everything in the same way I have explained over here, that is lb per feet is required for each and every pipe. And the fourth column is related to water volume in gallons per feet. So let's say we have 3-inch pipe size, how much gallons per feet is required for 3-inch pipe dia. So gallons per feet for 3-inch pipe dia is required 0.367. You can see 0.367. So in the same way, let's say for 10-inch pipe size, how much gallons per feet is required for 10 inches. 10 inches gallons per feet 4.08. So in the same way you have to write gallons per feet for every pipe used in your project. Now next column is related to total volume. As you can see that we have write volume of water in gallons per feet. So now we have 100 feet. 100 feet, we need to multiply this 100 feet with that much volume of water per feet. So we'll get the total volume in that much length. So as you can see, so we need to, as you can see, the formula which I have applied over here is the volume of the water in gallons per feet multiply this length. You will get the total volume in gallons within this pipe and this length. So total volume of the water required for 1/4 pipe size having 100 feet length is 6.4 gallons. So 4-inch pipe size is 73 feet, length requires 47.67 gallons. So in the same way you have to calculate for all. So let's say we have calculated for all of these and we have summed it up over here. So we have summed it up and total volume of the water in the pipes is 1189.54 gallons needed. So this is basically the volume of the water inside the pipes, which we have calculated over here. Now the second part is related to the equipment's volume. How much volume of the water will be inside the equipments. So let's say we have we have write everything which we have in our project: 4 air cooled chillers and air handling units, and then FCUs over here. So air cooled chillers we use in project is 4. So water volume in the gallons required per air cooled chiller is 18.5 gallons. You can get this value from the supply directly, so you can write over here 18.5 or whatever the value which you have for your chiller. So one chiller required 18.5, so 4 chillers required 74 gallons. So and now the second we have air handling unit. So now we have air handling unit. So we need to write the water content in kgs and cubic meter, and then we need to convert this into gallons to get the total volume in gallons. So let's say we have air handling unit with a water content of 24.89 kgs. You need to convert this into cubic meter by dividing by 1000. So next is we need to convert this into gallons. You can get this value also from supply, how much content of the water is required for your air handling unit. So water volume in the gallons, in order to convert this into gallons, you need to multiply this cubic meter with 264.172 in order to convert this into, because 1 cubic meter required 264.172 US gallons. So this air handling unit requires 6.58 US gallons. So since we have one air handling unit of this type, so we got total volume is 6.58 gallons. So in the same way you have to calculate for all of the equipments of your project. So in order to get this value, and then you have to sum up all the volume of the system which you have calculated above. So total volume of the equipment over here is 140.94 gallons. So for the, due to the pipe, the volume which we have calculated is 1189.54, and due to the equipment, the volume which we have calculated over here is 140.94 gallons. So total volume of the system is equal to pipe volume plus equipment volume. So pipe volume is equal to 1189 and the equipment volume is 140.94. So this comes out to be 1330 gallons. So now we have to apply safety factor. You can take safety factor 10 to 15%. So now I am going to apply 10% safety factor to our calculation. So 10% safety factor of 1330 will be 133 gallons. So total volume of our system will be now 1400, that is 1330 plus 133, that is equal to 1463.53 gallons. So now what you have to do, you know all the values. You know V2, you know V1, you know alpha, delta T, P1, P2 and Vs. Total volume of the system we have just calculated now, that is 1463.53 gallons. So now we have to put all the values in our formula over here, that is Vs into V2 by V1 minus 1 minus 3 alpha delta T divided by 1 minus T1 by T2. So I have already write the formula over here and put all the values over here. After that I got the value is 24.66 gallons. So round off it will be 25 gallons. So for that much system volume, 1463 gallons volume of the whole system, how much size of the tank it should be? It should be 25 US gallons. So our expansion tank size should be 25 US gallons. So this is how you can calculate the expansion tank size So it's very easy to calculate. If you know all these values, you have to put it and then you can get the expansion tank size. And the last thing I want to explain over here is the location related to the expansion tank. So about the location of the expansion tank. Since the point of connection of expansion tank to system is point of no pressure change, therefore it is typically located at the suction side of system pumps. As you can see in this drawing, this is our expansion tank and this is our main chilled water return header, and this expansion tank is connected to main chilled water header, and this is further connected to suction side of primary chilled water pump. Therefore our expansion tank is connected to suction side of primary chilled water pumps, and we don't want any air to withdrawn into the system, and we want the pressure everywhere in the system must be above atmospheric pressure, and we don't want any air to drawn into the system. That's why it is located on the suction side of the pumps.
So today I'm going to explain you guys about the static pressure calculation of the machine. So as you can see that there I have a drawing. This is a 3D view. Let's go to our floor plan first. So there I have one air handling unit that is supplying air to the office space, as you can see here, to the meeting room and the manager's room. So if you move back to the 3D view, it looks like this. So there I have the air handling unit at the rooftop, and there I have return ducting, as you can see over here in the pink color. This is return ducting, and this blue color is supply ducting, that is supplying conditioned air to the space of the building, and this green color is the fresh air ducting. So basically I'm gonna use this Excel sheet which I have prepared here to calculate the static pressure of the fan. So as you can see that I have divided into three parts: supply side, return side, and the fresh air side. So first I'm gonna calculate for the supply side. As you can see that I have divided each section into and described over here. So move back to our drawing. The reason why I have selected this Revit to show you about 3D view, because in 3D view you can easily visualize each and every fitting that is coming on the way from the machine mouth till the our most remote outlet. So as I already selected, first of all you have to select the most remote outlet. So I already selected the most remote outlet. So this is from the machine supply side, it's going from here, so all the way in here. This is our most remote outlet. You have to check the length of each section and then you have to come up with the most remote outlet. So I already selected this most remote outlet to here. So if move back to our floor plan, ceiling plan, so this is the meeting room. This is our most remote outlet for ESP calculation. So we are going to follow that route all the way from up till here for our ESP calculation. So let's start the ESP calculation. So first of all we have a transition, rectangular transition, as you can see in the 3D view. So first of all we have a rectangular transition on the supply side of the air handling unit. Also I'm gonna use this X-ray fitting database software to calculate the static pressure for different components. The first fitting over here is rectangular transition over here. As you can see, the size of this rectangular transition is 1100 into 950 by 750 by 550. This one we already given here in our Excel sheet. So number of fitting is 1 and the flow rate is 2571 liters per second. So I'm gonna use this X-ray database to calculate the static pressure loss for this rectangular transition. So there I have a X-ray duct fitting database software. As you can see that this is the fitting we have used in our drawing, that is SR4-2. So this is from the fan side and this is to the other side of the fan. So fan side is H1 W1 and other side is W0 H0. So as you can see that the fan side is 1100 by 950 and the other side is 750 by 550. So H1 W1 is the fan side and the other is width height is 550 and width is 750 and the fan side is 950 and the width is 1100 and the flow rate we know that is 2571 liters per second and the length we can get from the Revit. As you can see that is 375 mm. 375 mm and then calculate. If you calculate you will get the pressure loss is 1. This is the calculate button, you need to click this and you will get pressure loss is 1 Pascal. So we need to add this pressure loss here in our Excel sheet, that is 1 Pascal in here, and then we have a straight duct piece. As you can see that we have a straight duct and until here our size and flow rate is same, so pressure loss will be same throughout this piece of duct, that is 750 by 550 size, because flow rate and duct size is same, so pressure loss will be same. So what I'm gonna do is I'm gonna add all the lengths, this one, and this piece and this piece. So there we have in between these two pieces we have a duct silencer. I'm gonna add this one later. First I'm adding the static pressure loss for the straight piece of duct, that is 750 by 550. If you add all of these duct lengths it will be 4.53. that's already added in here, or you can check the length of each piece one by one by using on the property palette. If you go there and you will find the length of this piece is 17.92 meters. So you have to add all of these lengths, so it will be total length will be around 24.53, that is 80.46 feet, and flow rate is 2571 liters per second, that's we already know here. For this piece of duct you know that flow rate is 2571. In the property palette you can see 2571 liters per second. So I'm going to again the X-ray database and I will check the rectangular straight duct fitting. This is called CR11-1 fitting. If you want to check your fittings in Revit also, you can check that by clicking the property palette. So we know that duct size is 750 by 550 and the length is 24.53. so go back to our H3 database. We are going to use this CR11-1 fitting. Height is 550 and width is 750. So absolute roughness we keep the same, that is 0.09. Length is 24.53 meters. Okay, and flow rate is 2571 liters per second and density of the air is same. So just calculate and it will give you the pressure loss for that piece of duct, that is 14.3 Pascal. For 550 by 750 duct with 2571 flow rate it will give you 14.3 Pascal. So 14.3 Pascal over here. This duct silencer over here. Basically you need to get this value from the supplier for this duct silencer. Let's say we got this duct silencer from Ruskin, and size of this duct silencer is 750 by 550, and had pressure loss we got is 16.87 Pascal. So you need to get this value from the supplier or manufacturer. So 16.87 directly I will write in the Excel sheet, that is here. And then we have 90-degree rectangular metered elbows, radius 1.5 W. As you can see that we have how many elbows. So straight piece of duct, transition, duct silencer, all of these are done. And then we have one elbow here and second elbow here, and size is same, that is 750 by 550, and the flow rate is again same, that is 2571 liters per second. So we have two elbows here. So as you can see that two elbows in here, 2571 liters per second, size is 750 by 550. Okay, there we go, and we find the smooth radius elbow without veins. This is the elbow which we have used in here, and the size of this elbow is width is 750 and the height is 550. Radius ratio, because we use 1.5 W, so it is by default 1.5, and 90-degree elbow we have, and flow rate is 2571 liters per second, and then calculate. So pressure loss calculated over here is 4 Pascal, and then we have to go back to our Excel sheet, and pressure loss is 4 Pascal. Since we have two elbows, so total is 8 Pascal. And then move back to our drawing, and then since up till here we are done, so after that we have a transition in here. As you can see, we have a transition here. So you need to calculate for transition in the same way as I explained before. So just for the to save the time, I'm skipping this one. And then we have a straight duct piece, that is 450 by 300, and the flow rate for this piece is 570 liters per second. As you can see over here in the property palette, 450 by 300, 570 liters per second, and length of this piece is, you can see here the length of this piece this one 5.74 meter is the length, 570 liters per second is the flow rate. So move back to our Excel sheet. Rectangular transition you calculate in the same way as I explained before. Then straight duct 450 by 300 with 5.74 meters the length, and 570 liter per second is the flow. This one I already explained before also, straight duct, so same way you have to calculate. And then you have since this is our most remote outlet, so we'll go to the right side. So there we have a T. So this T will be acting, after T we have a reducer, so this T will be acting as elbow T plus reducer T. So we divide this into two parts, that is elbow plus reducer, because we are going to the right side to the most remote outlet. And the flow rate, we can check that how much is the flow rate to that side, that is 269 liters per second. So as you can see in the Excel sheet, we divide this into elbow T and reducer T, elbow T and reducer T. So size is 450 by 300 for the elbow, and reducer size is 450 by 300 to 300 by 250. As you can see that this is the transition reducer we have, that is size is 450 by 300 and 300 by 250. As you can see here in the property palette, that is 450 by 300, 300 by 250. So elbow, as I already
explained you for the elbow also. The same way you have to calculate for elbow and for reducer transition. And then again we have a straight piece of duct. Flow rate is 269 liters per second, and length of that piece is 5.14 meters. You can see in the property palette. So go to our Excel sheet, straight piece 300 by 250, 5.14, 269 liters per second. So straight piece of duct is also I explained before, so you need to get in the same way, straight piece. And then we have a rectangular to round transition. If you move back here, so after straight piece is done, you have this rectangular to round transition, because this is a rectangular piece and then we have a round flexible duct, so we need rectangular to round transition to connect these two pieces. So you can see that rectangular to round transition over here. If you want to check the fitting also, you can just go to property palette and edit and check the fitting, that is SD4-2. This is the fitting which we have used here. So I move back to Ashray database, and then I will go to transition and then rectangular to round transition. So if you go there, you find the same fitting, SD4-2. So I'm going to use this fitting. You can see that from the fan side, or the flow direction is from this way, and this is to the round side. So this is H1 is the height and W1 is the width, and from the fan side. So this we know that that is 300 by 250. 300 is the width, 250 is the height. You can see there, this is 300 by 250. So this side is 300 by 250, and round side flexible dia is 300 mm. You can see here. So move back there. Then our height is, how much is our height? That is 250. Width is 300, and diameter is also 300 mm, and length of that transition is if you select this transition and check in the property palette, computed length is 60.4 mm, that is 61, we can say. Okay, 61 mm, and flow rate is 269. We already know, we check from Excel sheet and from the drawing, and then calculate. So pressure loss is 0 Pascal. So it has some value, but it's giving 0. So let's move back to our 3D model and check the pressure drop is 0.06 Pascal. It's very small, so we're going to add the same 0.06 Pascal. So rectangular to round transition 0.06 Pascal, only one fitting, so 0.06 Pascal. Then we have VCD, flexible duct, and diffuser onto the supplied side. As you can see that VCD here we did not add, so I'm gonna add the VCD also. For this VCD you need to get this value from the supplier. For this VCD supplier or manufacturer, he will provide you the pressure loss value. So right now I'm gonna keep 20 Pascal pressure drop, but you need to check this value from supplier or manufacturer. So I have used 15, so I'm gonna use 20 here. And flexible duct, I'm gonna use 1 Pascal here. If you move back here, and this is our flexible duct, and check the pressure drop for this flexible duct, that is 0.73 Pascal, so I'm gonna use 1 here. And then diffuser, for the diffuser also you need to check this value from supplier. So this is the most remote outlet diffuser, so you need to check this value also from the supplier, the one who provided you this diffuser. He will give you the value, pressure loss value. So pressure loss which I'm gonna keep here right now is 14 Pascal. 14 Pascal. So we are done with the supply side of the air handling unit. So static pressure loss, it will be the sum of all the duct and fitting losses coming on the way on the supply side to the most remote outlet. The total static pressure loss is
82.97, 15% safety factor we are going to use here. So total external static pressure on the supply side is 95 Pascal. So in the same way you have to calculate for the return side. If you see that the return side rectangular transition we already did, you know that how to calculate. Straight also did. Duct silencer, you need to get this value from the supplier, the one who provide you the duct silencer. And elbow we also finished. So only one thing is different here, that is rectangular wire mesh with insect screen. So if you move back to our, so this side we will have a rectangular wire mesh with insect screen to the return side, because it will suck all the air from this way to the return side and take it over here. So if you see, the size of this duct is same throughout until here. There we have a wire mesh, so its size is 750 by 550. So our duct size is 750 by 550, and the same size of the wire mesh we are going to use here, that is 750 by 550. So move back to our H3 database fittings and let me find the correct fitting. So if you go to rectangular and you will go to obstruction, there you will find screen only. So we will have a screen here onto the return side. Let me zoom it. We will have a screen to the return side to prevent any insect or anything to go inside the duct. So this screen will also compute in the pressure loss. As you can see that N is the free area ratio of the screen, A0 is the area of the duct, A1 is the cross-sectional area of the duct fitting where screen is located. So I'm gonna use same size of the screen as the duct size, same screen size as the duct size, and free ratio we will add like 50%. So our H0, this is our duct size. Duct size is 550 by 750, we already know. 550 is the height, 750 is the width. Area ratio is 1 because same size of the screen I'm using, so that's why it's 1. And free area ratio I'm gonna keep here is 50%. That means 50% of the air will be obstructed because of this screen. And the flow rate is on the return side. If you check the flow rate to the screen is 2185 liters per second. So 2185 liters per second. So pressure loss calculated is 28 Pascal. Because of this screen, it's much loss because of the screen. So due to the screen, you can see the pressure loss is 28 Pascal. So in the end, you have to sum up in the same way which you did for supply side. So static pressure loss is 67, 15% safety factor. Total external static pressure for the return side is 77 Pascal. That is 15% safety factor in this. And then in the end we have fresh air side also. Why we are calculating for the fresh air side also? Because sometimes you have fresh air is supplying from the fresh air handling unit. So that time you have to calculate in the other way, but this side we have fresh air supplied directly with the from the sand trap blower with insect screen. So this is supplying directly, so we need to consider the losses for the fresh air also, because there's only one fan working for the supply, return and the fresh air also. That's why we have to compute the loss for this fresh air also. If you see the fresh air, I did not add the sand trap blower fitting, but we will have a fresh air sand trap blower here. So fresh air sand trap blower, then straight piece of duct, and then we have a VCD in here. As you can see that this is the VCD, this is the VCD, and then we have a transition here also. Transition is 1050 into 400 by 600 by 400. So total 4 items. First transition, this one, flow rate is 386 liters per second, and straight duct is 600 by 400, VCD is 600 by 400, and fresh air sand trap blower over here. You need to get these values from the supplier for VCD and the fresh air sand trap blower. And straight duct you already know, rectangular transition you already know, as I already explained how to calculate the. So same way you have to calculate pressure loss for all of these items. So static pressure loss is 38.2 Pascal, safety factor 15%. So sorry, this is fresh air side. So total static pressure on the fresh air side is 43.93 Pascal. In the end you have to sum up all these static pressure loss, that is fresh, supply side, return side, and fresh air. So total will be sum of all these, that is 216 Pascal. So this is the external static pressure, but we need to add the internal static pressure also. So you need to get this value also from the supplier for internal static pressure. Internal static pressure, you will have pressure loss due to the filter, due to the coils. If you have a 4-row coil, if you have a 6-row coil, 8-row coil, you need to get this value from the supplier, because he will provide you the coil losses. If it is 4-row coil, it will be different, 6-row coil, it will be different, and due to the filter you will also have a losses. So right now I'm gonna consider, let's say I got this 20 Pascal from the supplier due to the filter, and 30 Pascal due to the coils. So total internal static pressure is 50 Pascal. So total fan static pressure loss will be the sum of external plus internal. External is 217 and internal is 250. So total it will be the sum of these two, that is 266.91. So you need to select the machine based on this static pressure loss of 267 or 267 Pascal. So this is how you have to calculate the static pressure loss for your machine. The topic which I am gonna discuss today is the air handling unit fan motor power calculation. If you remember that in my last video I have calculated external static pressure for air handling unit. So I'm gonna continue from the same Excel sheet to calculate the fan motor power of air handling unit. So if you remember that this is the drawing which we used last time to calculate the external static pressure of the air handling unit. So now I'm gonna calculate the fan motor power for this air handling unit. So move back to our Excel sheet. So as you can see that this is the main formula which we are going to calculate the fan motor power of the air handling unit. As you can see that formula is CFM into total static pressure divided by 6356 into efficiency of motor into efficiency of blower. So this formula you can find in the carrier handbook. I took this formula from the carrier handbook. So if you want to calculate the horsepower, you need to this formula. So CFM, as we already know that total CFM of the machine is, how much is the total CFM of the machine, we can see from the Revit also, or we can check from our Excel sheet. Total CFM was total airflow was 5445 CFM. So CFM we know that. Total static pressure we already calculated in the last video. Total static pressure was 267 Pascal, as you can see over here, but we have to use the static pressure in inches of water column over here. So we need to convert this into inches of water column. If you divide this figure with the 250, you can get the static pressure loss in inches of water column. So total fan static pressure loss is 1.07 inches of water column. So we are going to use 1.07 here. The total static pressure divided by 6356 is the constant in the formula, and multiply efficiency of motor into efficiency of blower. Efficiency of motor we normally take is 85%, that is 0.85, and efficiency of blower which we normally take is 80%. These are the standard values which we have used in here. So efficiency of motor is 85%, efficiency of blower is 80%. So if you used all of the values in here, CFM into total static pressure divided by 6356 into efficiency of motor into efficiency of blower. So after that you will get 1.3 horsepower. So you need 1.3 horsepower fan motor in the air handling unit. And if you want to convert this into kilowatt, you simply need to multiply this horsepower value with 0.746, so you will get the fan motor power in kilowatt. We needed 1 kilowatt fan motor power for air handling unit. So this is how you can calculate the fan motor power of the air handling unit.
So before starting this chill water pump head calculation, I'm going to explain you guys the main difference between primary and secondary chill water pumps. As you can see that I have this drawing of the chiller yard. You can see that I have a chillers over here, and then we have secondary chilled water pumps, and then primary chilled water pumps over here. So what is the main purpose of this secondary chilled water pump and the primary chilled water pump? So primary chilled water pump is basically, this primary chilled water pump is basically taking water from the building and push to the chillers, while the secondary chilled water pumps, they are taking water from the chillers and push to the building. So I will explain you over here in this chiller yard drawing. As you can see that this is our primary chilled water pumps and these are the chillers. So secondary chilled water pump basically taking water from chiller and push to the building. So this is the supply side of the chiller. As you can see that from this arrow, it is supplying water from the chillers. It's coming from here like this, and it is going into the secondary chilled water pumps. After secondary chilled water pumps, it is circulating over here through this line, and then it supplies to the building over here. And primary chilled water pump is taking water from buildings and push to the chillers. As you can see that this is the return. This one is the return from the building. This return is coming from here through this pipe and then going inside the primary chilled water pumps, as you can see over here. Then it's circulating back from this pipe like this, and is coming back from here into the chillers. So this is the main function of this primary pumps and secondary chilled water pumps. So let's start the pump head calculation. As you can see that I have Excel sheet over here. So I'm going to explain you the pump head calculation for secondary chilled water pumps. As you can see that this is the drawing I have, in which I will show you the pump head calculation. So you can see that we have a chiller over here that is has capacity of 200 tons, and we have a 4 air handling units over here, 1, 2, 3 and 4, each with a capacity of 50 ton. And you can see the supply piping from there going into secondary chilled water pumps, 1, 2, 3, and then it's going into the air handling unit 1, 2 and 3. And we know that we have a chiller of 200 TR and GPM is 480 GPM, as you can see over here, 480 GPM, and the pipe size is 5 inches, and each air handling unit with the 50 ton of refrigeration capacity. And how much is the GPM over here is 120 GPM with a pipe size 3 inches for each air handling unit. So as you can see, the pipe size over here is 5 inches, flow rate changes to 360 GPM because 120 move over there, again 120 move over there to air handling unit 2. So we are left with 240 GPM 4 inch pipe size, and 120 GPM over here in air handling unit 3, and 120 GPM here to the air handling unit 4. So if you want to know how did we get this GPM and tonnage, you can see my previous tutorials. regarding pipe sizing and heat load calculations. As you can see that we have divided this piping into different sections from A to B, B to C, C to D, and F and G, H, I, J, K, and L up till L. And you can see the section length for secondary chilled water pump over here: A to B 5 feet, B to C 5 feet, and so on up to K to L, that is 16 feet. So we have divided this piping into different sections to calculate the pump head. But before starting the calculation, you need to know one more thing. In order to calculate the pump head, we need to find the most hydraulically remote circuit in our chilled water system. As you can see that this is the supply piping for secondary chilled water pumps from there to point K to L. And we know that K to L 16 feet, and I did not write over here, but from K to air handling unit 4 length is 10 feet. So this is our longest run of piping up till point L. So this is our most hydraulically remote circuit over here up to point L. So let's move back to our Excel sheet to start pump head calculations. As you can see that I have divided the piping into different sections: A to I, I to J, J to K, and then K to L. Why did I write from A to I directly? Because if you see that over here, our GPM and pipe size is constant up till point L, up till point I. So after point I, our GPM and pipe size is changed. So that's why we keep the same from section A to section I. Here we have 480 GPM and 5-inch pipe size. From section A to section I, 5-inch pipe size, 480 GPM. So as you can see over there, we have a pipe size 5 inches. So what we have over here from section A to I, we have a straight pipe, we have a gate valve, we have butterfly valve, strainer, elbow, NLV, and DRE. I will explain you each one of this in detail, how we get these fittings section A to I. So let's start this first one. Pipe, we have a straight pipe, this one up till point I. We have a total length. How much is the total length we have from section A to section I? As you can see that A to B 5 feet, B to C 5 feet, C to D 5 feet, and then up to section I we have that much. So 5, 10, 15, 20, 21, 36, 36 and 20, 56, and then 10, 66. So section A to I we have 66 feet length of the pipe. So move back to our Excel sheet. You can see that the length over here is 66 feet. And if you want to convert this length into meter, you need to multiply this length with 0.3048. you will get in meter. And we know that we have a 5-inch pipe size, 480 GPM is the flow rate. We already checked from there, 480 GPM, 5-inch pipe size. So if you want to convert this into liter per second, you need to multiply it with 0.06208. you will get in liter per second. Now I will tell you how did we get this friction. So in order to show you, I will open this pipe sizer for you. So the pipe which we are using over here is flat steel schedule 40, and you see that pipe size is 5 inches and flow rate is 480 GPM. So flow rate and pipe size is 5 inches and flow rate is 480 GPM. As you can see, the head loss over here is 3.895 feet per 100 feet. So this is how we get this friction, that is feet per 100 feet in the straight pipe, the flow rate of 480 GPM and pipe size is 5 inches. So move to our next column, that is equivalent length. Since we already got the straight length of the pipe, so there is no equivalent length for this pipe. This is only for the fittings and the walls, so it will be 0, number of fittings 0. If you multiply and if we move to next column, that is total equivalent length in the straight pipe. So how did we get this total equivalent length in the straight pipe? We need to multiply this equivalent length time number of fittings plus the length which we have calculated over here, the linear length of the pipe, that is 66 feet. Since this one is 0, so we have only 66, that's why total equivalent length in a straight pipe is 66 feet. So moving to our next column, that is head loss. How did we get this head loss? We simply need to multiply this our friction, that is feet per 100 feet, that is 3.895, with this total equivalent length in the straight pipe. You will get this head loss. So as you can see that friction over here is 3.895 and equivalent length in a straight pipe is 66. If you divide it by 100, you will get the head loss. With 5-inch pipe size and that much friction rate, we will get the head loss of 2.57 feet. So this is 2.57 feet. Now I will show you the fittings which we have from section A to I. So this from section A to I, what are the fittings we have? So in order to give you a better idea, let me show you in this chiller yard drawing. Since we are working with the secondary chilled water pumps, and we can see that this is the section of the secondary pump. This is the pump header, if you can see over here. And what are the fittings do we have on the suction side and the discharge side of the secondary chilled water pump? As you can see, on the suction side we have this butterfly valve and we have a strainer. On the discharge side we have a swing check valve and the butterfly valve. So we have a one butterfly valve and one strainer, one swing check valve and one butterfly valve. So total 2 butterfly valves, one strainer and one swing check valve. Also we have a one gate valve over here from the supply side of the chiller. As you can see that this is a motorized gate valve over here on the supply side of the chiller. It is supplying from here and going into the secondary chilled water pumps. So we have a one gate valve over here, and other things I have already explained you on suction and discharge side of the chilled water pump, secondary chilled water pumps. That is 2 butterfly valves, one strainer and one check valve. Let's move back to our Excel sheet. You can see that gate valve over here, that is 1, butterfly valve we have 2, strainer 1, NRV, that is non-return valve or swing check valve, that is 1, and elbow, we need to check the elbows. So if we move back to our drawing, from section A to section I, how many elbows we have? 1, 2, 3, 4, 5. So up till section I we have 5 elbows. So elbows we have 5 over there. So only one thing is remaining, that is DRV, double regulating valve. So on the pump side we will have one DRV, that is double regulating valve, to balance the chilled water flow rate across the secondary chilled water pump. So we will have one DRV from section A to I on the secondary chilled water pump side. So now pipe size is same, that is 5 inches for all these fittings, and linear length for these fittings is 0. We need to get the equivalent length from here. So linear length is 0 for these fittings, and flow rate we know that for 80 GPM for all of them up to section I. If we need to convert this into liter per second, we can convert by this conversion. And now we need to know, the important thing over here is we need to get the equivalent length of this fitting or the wall. The wall over here is gate wall, and how much is the size? 5 inches gate wall over here with 480 GPM. So we need to calculate the equivalent length in a feet. So I will open the table over here to give you the idea how to calculate this equivalent length. Okay, this is the wall over here. As you can see that the gate wall over here, and we have a 5 inches gate wall. So you move to the right side 5 inches gate wall. 5 inches gate wall over here. You see the equivalent length is 6 feet over here. So this is how we get the equivalent length of 6 feet. Number of fittings, we have only one wall over there. If you multiply this equivalent feet with the number of fittings, you will get equivalent length. Again, you need to multiply this equivalent length with number of fittings and add this length. Since this is 0, so we have total equivalent length in the straight pipe is 6 feet. Same way you will get the head loss. You need to multiply this total equivalent length in a straight pipe with this friction. Friction will be same. Already told you how to calculate this friction by using a pipe sizer. You need to multiply 3.895 with this total equivalent length divided by 100. You will get head loss, that is 0.23 feet head loss across this gate wall. Now move to the butterfly wall. We have 5 inch pipe size, the 5 inch butterfly wall over here. So we need to calculate the equivalent length. Since butterfly wall is not over here, we can go for the gate wall. Same 5 inch pipe size, that is 6. So again 6, but we have 2 butterfly wall over here, as we already checked that on the section of the secondary chilled water pump. We have a 2 butterfly walls. So 6 into 2, that is 12. Same way you get the head loss. So move next, strainer. We have a 1 strainer over here, 5 inch strainer, 480 GPM. So we need to get the equivalent length. How much is the equivalent length for 5 inch strainer? As you can see that we have a Y type strainer over here. We have a 5 inch strainer. If you move over there, we have a flanged end strainer, Y type. How much is the equivalent length? That is 80 feet. 5 inch, 80 feet. So we can use 80 over here. Since we have 1 strainer, so 80 into 1, that is 80. Again, you need to multiply this equivalent length with friction, that is feet per 100 feet, divide by 100, you will get this head loss. So move back to our elbow. We already know we have 5 elbows over here. So we need to calculate the equivalent length in a feet for this elbows, 5 inch elbows. Since we are using long radius elbows over here, depending on the site condition, we can use standard elbows, but we are using long radius elbows, 5 inches. So we need to get this equivalent length. As you can see that we have this one, as you can see that we have long radius elbows over here. This is a standard elbow, this is the long radius elbow, 90 degree. So we have a 5 inch pipe size. You can see that 5 inch pipe size with the long radius elbow, that is 8.2. 8.2 is the equivalent length for 5 inch elbow, 90 degree long radius. You can see over here 8.2. So this is how we got this equivalent length, 8.2, 5 inch pipe size. So since we have 5 elbows, 8.2 into 5, that is 41. Again head loss is 41, that is equivalent length in the straight pipe. Multiply by friction rate, you will get this head loss. This is how you can calculate the head loss to the elbows. Now the next fitting which we have over here is NRV, non-return valve, or the swing check valve, that is 5-inch pipe size. So let's move back to our chart to get the equivalent length for this NRV. As you can see that this swing check valve here, 5-inch pipe size. So move back to the right, move to the right side, 5-inch pipe size with the swing check valve. How much is the equivalent length? That is 50 over here. So we can use this 50. You can see that number of fittings we have 1 and equivalent length is 50. Same way you can get the head loss. So next we have a DRV, that is double regulating valve, 5-inch pipe, 5-inch size. So move back to our chart to get the equivalent length for DRV. This is our DRV, that is double regulating valve. Since we are using 45 degrees DRV, 5-inch pipe size, 45 degrees DRV, we got 58 equivalent length. So DRV, 5-inch pipe size, 480 GPM, got 1 DRV, that is 58, that we already checked from the chart. So total equivalent length in the straight pipe is 58. Same way you can calculate the head loss. Simply need to multiply this equivalent length in a straight pipe with this friction. You will get the head loss. Divide by 100, you will get the head loss. So the next section is I to J. Next section is I to J. I to J, there is no fitting, only straight pipe is there. As you can see that pipe size is same, only the flow rate is changed. So flow rate is 360 GPM and pipe size is 5 inches. 5 inches pipe size and flow rate is 360 GPM. And how much is the length we have over here from I to J? That is 12 feet. From I to J you can see that we have a 12 feet length. So we have a 12 feet, that is equal to 3.66 meters, flow rate 360 GPM, that is 22.71 liter per second. And again we need to calculate the friction, that is feet per 100 feet. How did we get 2.261? Again we go to the pipe sizer tool. We have a 5-inch pipe size with 360 GPM this time. So how much is the head loss? 2.261 feet per 100 feet. You can see that 2.261 feet per 100 feet. So this is the straight pipe. We already calculated the linear length, that is 12 feet. So total equivalent length in the straight pipe will be 12 feet, that is over here. And head loss will be, you need to multiply this total equivalent length in a straight pipe with friction rate divided by 100, that is 2.261 multiplied by 12 divided by 100, that is 0.27 feet. That is 0.27 feet over here. Now if we move to the next section, that is J to K. From J to K you see that we have a straight pipe. Also you notice that from 5 inches to 4 inches, so pipe size is changed. So we will have a reducer over here, 5 to 4, 5 by 4 reducer. And the GPM over here is also changed, that is 240 GPM. Also we have no reducing T over here to the point K, no reducing T at the point K. So we have a 4-inch pipe size, 480 GPM with the straight pipe, reducer, and the no reduction T. So move back to Excel sheet. See that we have a pipe, 4-inch pipe size, 240 GPM, reducer, 4-inch, 240 GPM, no reduction T, 4-inch, 240 GPM. So what is the straight length of the pipe from J to K? Is 14 feet. From J to K, 14 feet. Okay, that is 14 feet, 240 GPM. And we need to calculate the friction rate again with 4-inch pipe size, 240 GPM. 4-inch pipe size, 240 GPM. How much is the head loss? 3.255 feet per 100 feet. 3.255 feet per 100 feet. since this is a straight pipe, so no equivalent length, no, for it will be 0, and total equivalent length will be same as the linear feet over here, that is 14 feet. Head loss you need to calculate, you need to multiply this with this divided by 100. Now we have a reducer, 5 inches to 4 inches reducer. For reducer, how did we get this equivalent length 3.8? So let's move back to our chart. Okay, this is the table we are going to use to calculate the equivalent length for the reducer. As you can see that we have a sudden enlargement, sudden contraction, and two other. So since we are calculating the secondary chilled water pump head, so pipe size is reduced from 5 inches to 4 inches. So we have a sudden contraction because pipe size is reduced. In this case, capital D is representing our big size, small d is representing our small size for pipe dia. So 5 inches is capital D, 4 inches is the small d. These are the different ratios over here, 1/4, 1/2 and 3/4. So since we have 5 inches and 4 inches reducer, 5/4 reducer, so 4/5, small d by capital D, I already told you, small d by capital D, and ratio is 0.8, 0.8, that is nearly equal to 3/4, that is 0.75. So we can get this ratio 0.75, that is 3/4 over here, and we have a reducer 4 inch size over there. So move to the right side with the 4 inch size, and 3/4 ratio, we got 3.8 is the equivalent length over here, 3.8. So this is how we got the equivalent length 3.8 for the reducer, 5/4 reducer, 4/5 reducer. Since we have one reducer, so total equivalent length in straight pipe is 3.8. So head loss, again you need to multiply total equivalent length with the friction rate divided by 100, you will get the head loss. And the last one from section J to K is no reduction T. So move to our chart again to find the equivalent length for no reduction T. So this is the chart we are going to use for no reduction T. As you can see that this is the no reduction T over here, and we have a 4 inch size over here. If we move to the right side and 4 inch no reduction T, we got 6.7 equivalent length. 6.7 over here is the equivalent length. So see, 6.7 is the equivalent length for no reduction T. Only one T is there, so we got the head loss over here is 0.22 feet. So now move to our next section, that is K to L. K to L. To understand K to L section, we have I will open one image for you to get the better understanding. As you can see that this is the supply side of the air handling unit, and this one is the return side of the air handling unit. Since we are calculating the pump head, secondary chilled water pump, that is supplying water from chillers pushed to the building. So this is the supply side we need to consider for secondary chilled water pump. So what are the fittings we have on the air handling unit supply side? This is the gate valve, and this is Hvac type strainer. So we have two fittings, and this one is a two-way valve. You can use this for primary chilled water pump head calculation, and this is the DRV double regulating valves. So right now we consider only this two things, that is Hvac type strainer and gate valve over here, because we are calculating the secondary chilled water pump head right now. we have two fittings over here, as I already showed you in the image, that is gate valve and the strainer from point K to L. Also notice one thing, the pipe size is reduced from 4 to 3 inches, so we will have a reducer over here also. If we move back to our Excel sheet, you can see over here we have a pipe size 3 inches, gate valve, strainer and reducer. So these are the three things which we have in this K to L: pipe, gate valve, strainer and reducer. So we have a 3-inch pipe size over here and 120 GPM, and equivalent length over here we will calculate now. First, linear feet of this pipe is 16 feet, just confirm from there. K to L 16 feet, okay, 16 feet which we have used over here for this pipe, 3-inch pipe size. Again we need to calculate this friction for this 3-inch pipe size with 120 GPM. Go to the pipe sizer tool, 3-inch pipe size, 120 GPM. Head loss is 3.433 feet per 100 feet. 3.433 feet per 100 feet. So total equivalent length is 16 feet. You need to multiply with friction rate, divide by 100 to get the head loss. 3.433 multiply by 16 divided by 100, you will get the head loss of 0.55. 0.55 is the head loss. Now the fittings which we have over here is from K to L is gate valve, strainer and reducer. First, gate valve 3-inch pipe size, same GPM. We need to get the equivalent length of this gate valve, 3-inch gate valve. Okay, we have a gate valve over here and 3-inch gate valve. Move to the right side, we got 3.2 is the equivalent length. So 3.2, only one gate valve, so total equivalent length 3.2 in the straight pipe, and you can calculate the head loss in the same way I have explained. So next fitting which we have over here is strainer, 3-inch strainer. So this is a wire type strainer over here and 3-inch. We move to the right side, and since we are using a flange and strainer over here, so equivalent length is 42 over here for the flange and strainer, 3-inch 42. So 42, and we have one strainer, so total equivalent length is 42, and we can calculate the head loss by multiplying this equivalent length with this friction, divide by 100. So last one is reducer. Same way we'll calculate the equivalent length for the reducer. Since the pipe size is changed from 4 inches to 3 inches, move back to the chart. Okay, again there's a sudden contraction from 4 inches to 3 inches. 3 inches representing small d and 4 inches representing as capital D. If we get the ratio of 3 by 4, we will get 0.75. That is 3 by 4 ratio over here. As you can see over here, sudden contraction 3 by 4. And 3 inches, we move to the right side, we get the equivalent length for this reducer is 2.6 over here. Move back to the Excel sheet. The reducer equivalent length is 2.6 feet, only one reducer, total equivalent length is 2.6. Again you need to multiply this total equivalent length in the straight pipe with this friction rate, that is 3.433 multiply 2.6 divided by 100, you will get 0.09 feet, that is 0.09 feet. So all sections head loss has been calculated. Now what we need to do, we need to sum all of this to get the total head loss in the feet. So 15.45 is the total head loss in the feet, If you want to convert this into meter, you can use a conversion rate. So 15.45 feet is the head loss, and we need to add some safety factor. We will add 15% safety factor doing it, and total head loss after adding this 15% safety factor. 15% safety factor is 2.32 feet. So total head loss in the feet is 17.77 feet. So secondary chilled water pump head loss is 17.77 feet. So if you want to calculate this brake horsepower of this pump, you can calculate by using this formula, that is GPM into head into specific heat of the water into 3960 into efficiency of pump. Efficiency of pump, normally we are taking 85%, and specific heat, that is 1. If you will put all the values and GPM, we know that total 480 GPM. So if you put all these values, 480 GPM, 17.77 feet into 1 into 3960 divided by 3960 into efficiency is 85%, you will get the brake horsepower, that is 2.53. And you can get the horsepower by just multiplying this with 1.15, and if you want to convert this into kilowatt, you need to multiply this horsepower with 0.746. So the pump head loss is 17.77 feet and the kilowatt is 2.17 kilowatt. So this is how you can calculate the secondary chilled water pump head. In the same way you can calculate the primary chilled water pump head. The only difference between primary and secondary chilled water pump head, you will get the sudden enlargement over there. So you guys can do it on your own. If you find any difficulty, you can let me know, I will help you. In this video I will tell you guys how to calculate the chemical quantity required for the chilled water system. So let's start. Here I have made an Excel sheet for chilled water system volume calculation. Before starting the calculation, I will explain you why for chilled water system chemical is required. Why do we need to put the chemicals? So we need to put the chemical because we need to prevent the system from corrosion, scaling, fouling and microbiological growth. We are doing this basically in 3 ways. First, the chemicals react with the pipes to form a protective thin inside layer. Second, the chemical help in maintaining the pH level. And third, the chemical remove the corrosive dissolved oxygen in the water. So we are using the dosing pumps to supply the chemicals in chilled water system. I will show you over here in the drawing. There I have one drawing for the chiller yard. There you can see that we have 4 chillers over here, 1 2 3 4, and this is the chemical dosing pot installed over here. Let me zoom in. So as you can see that this is the chemical dosing pot. We are using automatic and manual chemical dosing pot over here. So basically these dosing pots with the dosing pumps are used to supply the predetermined quantity of the chemicals at regular intervals. So as you can see, that is how this chemical dosing pot is connected with the chilled water lines. This is our basically chilled water supply line that is coming from the chillers, a chilled water supply, and this is our bypass line. And this chilled water is basically supplying from the chillers into the secondary chilled water pumps. Here there are 3 secondary chilled water pumps, and then this chilled water is supplying from here to the buildings. And similarly this chilled water is coming back to the chillers from the buildings through these lines, and then going into the primary chilled water pumps, and through this primary chilled water pumps it's returning back to the chillers, and the whole process repeats. So this is our chemical dosing pot installed over here, as you can see that. So let's start the calculation over here. So this is the Excel sheet. First you have to write all the piping you have used in your project over here, all the dias from your drawings, and then you can convert this into radius, this one in inches, and this column same radius, and it is in meter. You can use the conversion to convert this in meter. So this is all the piping we have used in our project, that is 1.25 inches to 14 inches. So you have to calculate the area of the pipe for 1.25 inches. Similar, it's like pi r square. You can calculate the area of the pipe for each and every dia. So let's move to the next column, that is pipe length. You can get this pipe length from your drawings. So 1.25 inches dia we have used 130 meter in our project, and 3.5 inches we have used 90 meters, and 8 inches we have used 30 meters, and 14 inches we have used 20 meters. So all of the lengths are given here. So now we have to calculate the volume for this pipe. So we know that area of the pipe is here, length is here. We just need to multiply this column with this column. We'll get the total volume to 1.25 inches dia pipe, which we have used in our project. In the same way you have to use for all of the pipes which you have used in our project. 14 inches, same way you need to multiply area times length, and you will get the volume through 14 inches pipe which you have used in our project with 20 meter length, that is 1.99 cubic meters. So now you have to sum all of these volumes and you will get 11.89 cubic meter volume that you have used in your project. So the total chilled water volume which we have calculated is 11.89 cubic meter. So now we are going to use some safety factor, that is 20%. So we need to get the 20% of 11.89. So there is 2.37 cubic meter. The total chilled water volume becomes now is 14.7, simply 11.89 plus 2.37, so it is 14.27 cubic meter. Now the chemical which we are using over here is corrosion inhibitor, that is A0029, and the second one is microbiocide A2400. So this is file from Waterbird Chemical Treatment, is one of the reputed company in UAE. So we are going to use the chemicals provided by this Waterbird Chemical Treatment company. So this is A0029 corrosion inhibitor chemical. As you can see that the concentrated liquid blend of corrosion inhibitor designed to control the wetting and corrosion in a closed chill water system and hot water system. It will protect all commonly found in closed system from corrosive attack. I will send you this file and you can read it yourself. So the main thing, the dosage rate for A0029 system, how much is the dosage rate recommended by Waterbird Chemical Treatment. They are recommending 3 kg per cubic meter of system volume is required for your chilled water system. So A0029 corrosion inhibitor, we needed 3 kg per cubic meter of system volume. As you can see that the chilled water volume which we have calculated over here is 14.27 cubic meter. So 1 cubic meter required 3 kg as per recommendation of Waterbird Chemical Treatment. So how much chemical we need for our system? Because we have 14.27, we simply need to multiply this quantity with this quantity. So we need for our system is 42.81 kg of A0029 corrosion inhibitor chemical. Similarly, we have another chemical we are using over here. This is recommended by Waterbird Chemical Treatment, that is microbiocide A2400, and this is the description and advantages. So the dosage rate recommended by Waterbird Chemical Treatment is 100 ml per cubic meter of system volume. So our system volume is same 14.7. We just need to multiply this 14.7 with 100 because 1 cubic meter requires 100 ml. So 14.27 multiplied by 100 will get the chemical needed for our chilled water system, that is 1427.28 ml of microbiocide A2400 is needed for our system, chilled water system. So this is how you can calculate the quantity of the chemical required for your chilled water system, and we are using these dosing pumps to supply these chemicals into a chilled water system. In this video I will tell you guys how you can calculate heat load using E20 form. So let's start. Here I have opened this E20 heat load sheet. Here I have to give inputs so that it will automatically give me heat load. So let's start filling up. Start from here. This floor is ground floor, space reference, whatever the name you want to give. Over here, if you will see, we have calculated for master bedroom. So whatever the name you want to give, you can give over here. So master bedroom, so you can change it to master bedroom. Okay, then move down. You have area in a square feet. So if we go over there and see what's the area, it is 18 by 20, that is 360 square feet. And ceiling height, we know that it's 12.5 feet. So it will give us the volume, because this formula is applied over here, give us the volume. So now we have to give the inputs for thermal conditions of that area. Design condition, we know that in Dubai, if we move back to our app software and go to weather properties, we see that Middle East, UAE and Dubai, the city, we see that dB dry bulb, summer dry bulb is 107 and wet bulb is 75. So we can use over here. Outside dry bulb is 107 and wet bulb is 75. Now we have to use psychrometric chart to find this relative humidity and humidity ratio. So I have a psychrometric chart over here. I will tell you how you can use psychrometric chart. So on x-axis I have dBT, that is dry bulb temperature. On the y-axis I have humidity ratio, that in grains moisture per pounds of dry air. And here you can see this is vertical. These lines are for wet bulbs, and the one in the curve lines, that is for relative humidity, as you can see here. So what are our input? We know that dBT, dry bulb temperature, ambient outside temperature for Dubai is 107. So on x-axis we will see and go over here, that is 105 and 110. So 107 will be here. So if we move up like this and go up to wet bulb, as I told you, these are the wet bulb temperature lines. So I need to go from here, dry bulb 107 up to 75 wet bulb. This line is touching over here, it's intersecting over here. So as you can see, what is the humidity ratio over here? It is 80. The humidity ratio over here is 80, as you can see here. This is the humidity ratio 80. So I can use this humidity ratio as 80. And relative humidity I also need to check from the chart. So move back to psychrometric chart. What is the relative humidity? As I told you, these curved lines are for relative humidity over here. So if I will move, this is the point, a section point. 1 second, 107, move up. So this is the intersection point. At that side I got relative humidity, this is nearer to 25. So this is before 25, so we can use 24% like this, 23 or 24% relative humidity. So we can use 24 over here. Now we know that indoor design temperature is 75 degree for human comfort, and relative humidity is about 50 to 60% for human comfort. So we are using 50 over here. Now we have to give input this output, wet bulb and humidity ratio over there, to fill this thermal condition. Okay, move back to psychrometric chart. We know that 75 is the dry bulb and 50% is the relative humidity. These are the relative humidity lines. So you can see this point. These are the relative humidity, 50%. This is the point intersecting over here. So at this point, what is my humidity ratio? If I move over here, I got a humidity ratio is in between 60 and 70, but it's very close to 70, so I can take around 68 like this. Okay, let's take 68 from humidity ratio 68. And wet bulb, similarly we can check from here. These are the wet bulb lines. This is in between 60 and 65, so we can say this is 60 and 65 is in between them, so we can take 63 like this as a wet bulb. Okay, let's take 63. So we have filled this thermal conditions for that area, and we got a difference: dry bulb like this and wet bulb 12, relative humidity 26 and humidity ratio 12. So bypass factor, as I told you, it is coming from the supply. Normally it is 0.12, so we are using the same 0.12, and this contact factor should be 1 minus bypass factor, so it will automatically come if you will fill the bypass factor over here. No, now as I told you, here we have to give number of people for the bedroom. We assume 2 number of people for the bedroom. And how much is the CFM per person? If we will go back to our app software and open the space master bedroom and go to this ventilation requirement, what is the CFM per person? 5, and CFM per square feet, that is 0.06, so we can use these values. So number of people we already gave it, and CFM per person is 5, and CFM per square feet we know that 0.06 is from the app software. So okay, up till now we are done. So infiltration, there is no infiltration because the construction we considered over here is very tight construction, so no air will come in like this. So it's a tight construction, doors are properly sealed, windows properly sealed, so there is no infiltration load. So if I will move back over here, this is my first I will fill here for the glass. If we'll move back to my drawing, how many glass we have here? One here window, one here window, and what is in the schedule? For see, this window 1 is 5 cross 3, 15 square feet. So how much is the total window area for this bedroom? Is 15 for each window. We have 2 windows, so 15 cross 2, we got 30 square feet. So we can use 30 square feet over here for windows, and this is the transmission load for the windows glass. 30 square feet is the total area, and I told you for glass transmission will be outside ambient temperature, that is 107, that is dBT outside, minus inside design temperature is 75, minus it will be 5 degree less than the outside, so we can use 27 degree over here for floor and for partition. But for glass we have to say 107 outside dBT minus 75 inside design temperature is 32. It's a glass transmission load, we have to use 32 degree Fahrenheit. Okay, and glass U value, as we already know that glass U value, that is 0.30, so we can use 0.30 over here. Okay, now for the partition and for the floor area is same as the area we already described over here, that is 360 square feet. And I told you for floor delta T, that is outside ambient minus inside design minus 5 degree, so 27 it will come over here. And floor U value, we will go over here and check what is the floor value, that is 0.1. 0.1 is the floor value, so we can use 0.1 U value for the floor. And for the partition, if we will go back to our partition, okay, so moving back to the partition area, this is our partition wall, and length of this wall is 12 feet. So 12 feet multiplied ceiling height is 12.5, we got 150 square feet is the partition wall area, so we can use 150 square feet partition wall area over here. Okay, and partition wall U value we can see over here, that is 0.5, so we can use 0.5 U value for partition. And so it's done. For the roof, that is same area as the floor area, 360 square feet, and delta T I will tell you First we will add the U value for the roof from here. What is the U value for the roof? 0.045. So we can use this U value for the roof 0.045 directly 0.045. Okay, now here this is a transmission load through walls and the roof. So now we have to write delta T for the roof. In order to write delta T for the roof, that is we have to add some correction factor in this one. So I will tell you how you can do that delta T by using different chart. So let me open this first for you. Okay, here it's for roof. Okay, as you can see that our roof is exposed to sun, and I told you the building weight is average medium weight, that is 80 lb per square feet. So this one we have to use, and we know the peak time for the design is 3 p.m. So 3 p.m. is the peak time for the design, and 80 lb per square feet is the building weight. So over here we'll go and it will intersect over here, and we got a value of 28. So 28 we have to use over here, plus, now remember this figure 28, plus we have to add some correction factor due to the material specification. So we'll add 28 plus some correction. So for the correction, what we have to do is another chart over here, correction to the equivalent temperature in degree Fahrenheit. We know that outside design for the month at 3 p.m. minus room temperature. Outside design dry bulb is 107, and we know that inside design temperature is 75. After subtracting we got 32 degree Fahrenheit, and we know that daily range for Dubai is 17.5. If I'll go back over here and show you the weather properties, summer daily range is 17.5, that is around 18. Okay, so we can use daily range of 18 because 17.5 is very close to 18. We'll use over here, and here we got outside 107 minus inside 75, 32. So 30 and 35 will move to 35, and 18 we got 21 over here. So this figure should be added into the figure 28 which I calculated before. So what is the delta T value? We got 28 plus 21. Total delta T value is 49. We have to use over here. So move back to our E20 form, and we will use delta T value of 49. So we use 49 delta T over here. Okay, now we know that the wall that is exposed, some walls are exposed to sun, and these walls are north side exposed and this side is west side exposed. So north side exposed, we know that how much is the area, 18 feet is the length, multiplied 12.5 is the ceiling height, 225, and we know that west wall, that is 20 multiplied 12.5, 250 square feet. Move back to E20 form. So north wall got 225 square feet and the west wall got 250 square feet, and we know that U values for wall, that is 0.05. Just double check again, U value for the wall, that is 0.05. okay, use that one over here, 0.05, same over here, 0.05. Now we have to use delta T values. In the same way we have calculated for the roof delta T, we will calculate delta T values for the wall. So if I move back to other chart, there it is. This is equivalent temperature difference. As we know that wall average weight is 80 lb per square feet, and peak time is 3 p.m. So one of the wall is facing north side. If I move to north side, like this is the north side, and we know that building weight is 80 lb per square feet. So 60 and 100, it will be in between them, and we know that 3 p.m. is the peak time for the design. So this is the 3 p.m. as you can see over here 3, and move over here in between 60 and 100. 60 and 100 got 8 and 3. My value should be in between them, that is 60 and 100. 80 should be in between them, is the average of 2. So what I will do, I will add 8 plus 3 divided by 2. I will get the value for 80 at the per square feet. So 8 plus 3 divided by 2, I got 5.5. so after, remember this figure 5.5. in this figure I will add the correction temperature, and this correction temperature is same as we calculated before. Let's move back to the other again. I will show you once again. Here this is the correction. It is same because outside temperature is 107, inside is 75. So we got 32 over here, and daily range I told you that is 18. So 21 need to be added into 5.5 plus 21 is the correction for material specification. So we got 26.5 degrees Fahrenheit delta T. So move back to our E20 form. For the north side we got 26.5 delta T. As you can see, load is calculated to 98. Okay, now move back to our, and one of the wall is facing west side. As you can see, north side is done and another wall is facing west side, so we have to check for the west side also. West side, okay, here is the west, and we know that the building weight is 80, average building weight is 80 lb per square feet. It should be in between them. So if I move over there, and 3 p.m. is the peak time, for 3 p.m. peak time we will move up and west side 60 and 100, 80 in between them. So we'll take a mean value for this one, that is 19 plus 10. 19 plus 10 divided by 2, mean value is 14.5, plus we will add the same correction factor, that is 21 we use for the north wall and the roof. So we got 35.5 delta T for the west wall. So we'll use 35.5 for the west wall. Okay, 35.5 for the west wall. Now load is calculated over here. Now let's move to radiation load for the glass. We know that total glass, okay, north facing glass, one window is facing north, one window is facing west. This facing north, this facing west. And how much is the area? Window 1, 15 square feet. We can do 15 square feet or E20 form. So north facing 15 square feet and west facing 15 square feet. And we know that delta T for the glass 0.30, yeah, 0.30. We can use this one over here. Delta T is 0.30. Same we can use delta T 0.30 over here. So now we have to check delta T for the glass. Before checking delta T for the glass, let us check one more thing in the weather properties. 30 degree north latitude. Okay. As we know that in Dubai, this latitude is 30 degree north latitude. So if we move back to our chart over here, yeah, this one, this is for 30 degree north latitude. This is a solar heat gain through ordinary glass. So as we know that the maximum load is occurring during July and the May. So we'll select this one, 21st May to 23rd July, and we know that the peak time is 3 p.m. So, and we know that one of the glass is facing north and one is facing west. So at 3 p.m. north, how much we got over here at 3 p.m.? That is 13. So for the north side we have to use 13 value, and for the west side we have to use at 3 p.m. that is 145. So north side 13 and west side 145. Here the delta T values. North side 13 and west side 145. So here is the load calculated for the north side and for the west side. So all of the inputs are done, almost. Some of the inputs remaining that are over here. As we know that if we'll go back to our app software and open the space and go to internal, we know that sensible heat per person is 230 and latent is 120 for the people seated at rest. So we can use 230 and 120. 230 and 120. Okay, this is the sensible, that is 230, and number of people we know that 2. And lightning, as I told you, general rule is 1 watt per square feet, and we know that the total square feet is 360. And for the equipment, we have assumed that 200 watts. Only one equipment is there, so we can add one equipment over here. And 2 people, and the latent we already checked from the app, that is 130. Latent from the app is 120. 120 we can use over here. 120 which is per square feet. Okay, now everything is done. Infiltration, I told you there's a tight construction of this building, so there's no infiltration, no outside air will come inside. Okay, it's done. Okay, now what we have to do next is one more thing. As we have seen that effective room sensible heat factor is 0.97. Move back to one more chart. So here, okay, we know that dBT inside design temperature is 75 and relative humidity is 50%. So this is dry temperature 75 inside and design temperature 75, and this is relative humidity 50. And we know that this is effective sensible heat factor is 0.97. So if I'll go over here, 75 inside design temperature, 50 relative humidity, and 0.97 is the effective sensible heat factor. So our ADP will comes out to be in between them. So it will be around maybe 54 is here, 55.2 is here. So it will be around 54.7 like this, 54.7. So we can write 54.7 over here, or 54.6, 54.7, whatever. Okay, now if you see that this is the calculated CFM, that is 478 effective room sensible heat, and CFM is 478, and tonnage is 0.92 TR, and load is 11 MBH, and TSMBH is 10,198, and TS kilowatt is 2957. If we'll go back to our app and we'll compare the result, let me generate the report again and say preview for the report. Here how much we got, total tonnage is 0.9 ton. Here we got 0.92 ton. See, approx it's almost near. So if we move back to our app again, and how much is the coil load, that is 10.6 MBH over here, and how much is the coil load, is 11 MBH over here, TMBH is here. Okay, this is also near. And if we move back to here again and see the CFM, that is 427 CFM, and how much we got over here is 478 CFM. So it's not big difference for our calculation. So this is how you can calculate heat load by using E20 form. In this video I will tell you guys how you can calculate the heat load. So here I have drawing open. In this video I will tell you how you can calculate heat load for master bedroom. In the same way you can calculate heat load for store, living room and kitchen area. So before starting the heat load, you must know the local codes followed by that region. For example, I'm going to work in UAE, so I must know the U values and the local codes followed by that region. So as you can see that the window schedule is also there, that is window 1, it's over here, window 1 and window 1, and you have window 2 schedule used over here, here and here, window 2. So, and the U values are also given over here. U value for the wall is 0.05, for roof is 0.045, for floor is zero point 0.1, for glass 0.30, and shading coefficient for the glass is 0.29, and the U value for the partition wall is 0.5, and the average ceiling height in this area is 12.5 feet. So let me show you the U value which you're going to use in UAE Dubai. So open this Chrome factor and move down over here. As you can see, for the warehouse structure non-conditioned space, external wall U values is this and roof is this. For conditioned space U value is this, roof this and floor this. And for the office structure and residential area, what is the external wall U value? That is 0.05, and for the roof 0.045, and for the floor 0.1, and for the glass penetration U value is 0.30, and the shading coefficient maximum is 0.29. As you can see, this is the same values which I am using right now, because the area or the region in which I am working right now, it's Dubai. So these are the local codes which I need to follow in order to calculate the heat load for the particular area. So let's start this heat load calculation for the master bedroom in the app software. So let me open this app for you. So new installation standard 2010, energy 2010. Okay. So first of all, we have to give some input. We have to give wall U values, roof U values, and window U values. So let's go to wall U values. Default new wall. Here in app, you will not find, you cannot give direct U values for the wall. So in order to give the U value for the wall, as you can see over here, is that is 0.05. I need to give over here. So let me make this 0.05 by selecting different layers. So if I will go over here, default wall assembly, and let me select face width of 14, board insulation, that's 8-inch high weight concrete block. Okay, now if you will play with these layers, you as you can see, U value is 0.056, so I'm near to 0.05. So let me change this layers in order to make it 0.05. So if I will move it, okay, now 0.053 were more nearer. So let me move this one also 8-inch. 8-inch lightweight concrete 0.051, okay. R14 board insulation, okay, and 4-inch face brick will change this to common brick. As you can see, overall U value is 0.05. So this value we can use to calculate the heat load. So we just select OK over here, and then now we'll move to roof. Same thing we'll do over here. As you cannot, what is the U value over here for the roof? That is 0.045. So we have to make this value as 0.045. Let me change this one to fall shingle plus plywood R22 that. Okay, as you can see, 0.040. We have to make it 0.045. So 3x8 plywood. If I will select 3x8-inch plywood, okay. Then R19, that insulation is very near to 0.045. Then airspace, then half-inch plywood or half-inch. With some plaster, 0.045. So we got our value 0.045. So we can use this u value of the roof in our heat load calculation. That's okay. Now go to window, new window, give it a name like window 1, and give it height and the width. As if we move to our drawing, and from the window schedule, 5 feet by 3 feet. 5 feet is the height, 3 feet is the width, so we can use over here 5 by 3. As you can see here, we have window 1 in the master bedroom, both sides, window 1, window 1. So we have to use this dimension of the window, that is 5 feet by 3 feet. 5 feet is the height and 3 feet is the width. It's already there, no need to change. And over here you will find u value for the glass is 0.30 and shading coefficient for the glass is 0.29. We can use these values, 0.30 u value and 0.29 shading coefficient. So select OK. Then we have to move to the space, default new space. But before that we have to select this region in which we are working right now. This is very important. So just select this one and change the region which you are working right now. For example, the region which I am working right now, it's Middle East, and the location it's United Arab Emirates, and city is Dubai. So all of the values are here, latitude, longitude, elevation, summer driver, and daily range, everything is there. And just select OK, and then move to spaces. From the space, select default new space. What is the name of that area? You can give over here. It's a master bedroom. What is the floor area? As you can see over here, it's 18 by 20 feet. So how much is the area? 18 by 20. You will get 360 square feet area. 360 square feet area. And average ceiling height, as I already told you, 12.5 feet. And building weight is medium, and medium weight is 80 lb per square feet. What is the usage of that space? This is for ventilation purpose. So if I'll move down, I need to select this bedroom. You can see hotel bedroom and living room. You can select this one. So CFM per person is 5 and CFM per square feet is 0.06. Then move to next tab, internal. Here you find light fixtures, that is recessed, unvented. As per general rule, if you don't have any data from electrical first it's better you will get data from electrical engineer, so you can use that wattage over here. If you don't know, then you can use by default 1 watt per square feet. This is a general rule. Over blast multiplier you have to use, that is 1.07. And then you have to give a schedule over here. Just give it a name, that is light. Select OK. Then move down, task lighting, no need. Then electrical equipment. If you can get this electrical equipment bought from the electrical data, that's better. If not, then you have to use your general rule or predefined rule, that is 8 watt per square feet needed if you don't know. So let me use, it's a bedroom, it's not too much, so we can use 200 watts. That would be enough for the bedroom. It's okay. So how many people occupied in this room? 2 people. So we can give over here. It's activity level is seated at rest, and then over here you also give schedule, that is like so. Here also you have to give a schedule, name of electrical equipment, for example it's this one. So occupancy of the people, there's 2 people in the bedroom. Okay. What's the activity level? They are seated at rest. Okay. Then same way you have to select a schedule for this one people. Okay. Then move to walls, windows and doors. If we will move back to our drawing area, you will see this wall. We should know the orientation of the building. So this wall that is facing north side, and this wall that is facing west side, and this wall, what's the dimension? It's 18 foot. So, and we know the ceiling height is 12.5. So what's the gross wall area? Is 225 feet square feet. And how many windows over here? Only one window, that is window 1. So 225 square feet is the wall gross area facing north side. So move back to half. North exposure, and 225 is the wall gross area, and window quantity is window 1 quantity is 1. And if you will move back over there, and you will see another wall that is exposed to sun, and its dimension is 20 feet is the length. So 20 feet multiplied 12.5 is the ceiling height. We got 250 square feet is the gross area of that wall, and it's facing west side. You see over here, west side, and only one window over here. So move back to half. Give this as a west side exposure, and 250 square feet is the gross area, and window quantity in window 1 is 1. Window 1 is already selected here. So go back to roof. Its exposure is horizontal, and gross area is the same as the floor area. Then infiltration, no need for this one. Residential, okay. And go to floor. If you will go to floor, as you, there are 4 types over there: floor above condition, unconditioned, slab floor on grade, slab floor below grade. In this example, we have this on the ground floor, so we have this floor above unconditioned space. If it's on the first floor, our ground floor is conditioned, then we have to select this floor above conditioned space. As we are on the ground floor and it's a floor above unconditioned, so we have to select this one. Floor area is the same. U value we already see over here, that's floor U value is 0.1. It's already there. So unconditioned space maximum temperature, ambient at space maximum. As you know, ambient at space maximum, we are working in Dubai, so ambient at Dubai is 107, and this unconditioned space maximum will be 5 degree less than ambient space. So 107 minus 5 degree, you will get 102, and the unconditioned space minimum is 53.6 here in Dubai, so 53.6 same. So now move back to our partition. So we have wall partition over here. Let me see. Yes, we have wall partition over here. As you can see, master bedroom is our conditioned space. This master bath is a non-conditioned space. So whenever you have a conditioned space and non-conditioned space adjacent together, that wall will be your partition wall. So this is your partition wall, and what's the length of that partition wall is, that is 12 feet. 6 feet wide and 12 feet is the length. So 12 feet is the length of that wall, multiply ceiling height is 12.5. So 12 multiply 12.5 ceiling height, we got 150 square feet is the gross wall area. So go over here, select wall partition, 150 square feet. U value for the partition, we already know that it's 0.5 value, 0.5 U. Okay, we select over here, and same ambient at space maximum is 107 in Dubai, and this will be 5 degree less than the ambient, that is 502.0, and this is 53.6 and 53.6. So everything is done, so just select OK, then move to system and go to over here, new default system. So give this system here name. This is master bedroom AC1. Okay, equipment type, or if we're going to use split air handling unit over here, okay, split air handling unit. And system air type, it's a single zone, so we have constant air volume single zone. Then move to ventilation. Everything's just as selected, constant airflow, and ventilation sizing method is sum of space outdoor airflows, and unoccupied damper position is closed. Okay, then move to central cooling. Supply temperature want 55 degrees, and bypass factor normally we're getting from supplier, and it's normally 0.12, so we just select 0.12. And if we move back to heating, we don't need heating in this one, so we just uncheck it, and we move to duct system. Okay, then move to zone components. Zone components, you just need to select this space and then add into your zone like this. Then move back to your thermostats. It's okay, everything. Yeah, throttling then. Move to supply terminals. Okay, and go to your sizing data. One thing more, over here in system, zone components, thermostats, you have to give a schedule name over here for thermostat, like any name whatever you want, you can give it thermostat. Okay, then go to sizing data, you will find cooling. We have to give some safety factor over here. For sensible we will give 15%, and for latent we will give 5%. The reason why I'm giving 15% for sensible is 10% due to the motor heat of that equipment, and 5% due to the safety for sensible, and 5% here for the latent is the safety factor we need to add over here. So just like okay over here. Now if I will go over here, master bedroom, right click and print view design result, it will give me the load calculations. So just click it, and whatever you want in your report you can add it. So what I need over here is psychometric system properties. Okay, system load calculation. Okay, let me select this one for you. And space load is also you want to select over here, or if you want hourly air system load you can get it over here from January to December. Same, you can get the graph over here, then select preview in order to get the result. So it will generate the report for you. Just wait a bit, it will generate the report. So as you can see, app has generated the report. As you can see, location is Dubai, United Arab Emirates, and floor area 360 square feet. The master bedroom, calculation from January to December. You can see total coil load is 0.9 tons, and sensible heat load is 10 mph, and coil CFM is 427. So we got everything over here. We got the CFM, we got tonnage, we got mph. So and you can see that load occurs at July 15, so July 3 p.m. we got a maximum load. And over here you see relative humidity is 47%, and bypass factor we already gave. Coil ADP is 53.8 degree Fahrenheit. This is the operator's dew point, and outdoor ventilation required for that room is 32 CFM. So this is how you can generate report in the app. Here you can see this is a design cooling, and all of the load is calculated over here for the windows, roof, wall, partition, ceiling separately, and then calculated over here total. So this is how you can calculate the heat load in the app software. In this video I will tell you guys how to use psychrometric chart to get the relative humidity, dry bulb, wet bulb, temperature values. Because when we are calculating the heat load, this is very important parameters that need to be input. So here you can see that I have a train psychrometric chart software open over here. So before starting I want to show you the basics about this chart. So let me zoom in. As you can see that this is the x-axis, where there we have a dry bulb temperature in degrees Fahrenheit, and then y-axis we have a humidity ratio in grains per lb, and these curved lines is 10%, 20%, 30%, 40%. These are the relative humidity lines, and last one is the wet bulb temperature line. As you can see that this line is a wet bulb temperature lines. So if you remember that in my turn number 16 and 17 where I was calculating the heat load, so there I have the E20 sheet, same E20 sheet, So as you can see over here, we need to input the design conditions, outside design and indoor design. Let's say this is the building located in Dubai, and outdoor design condition of Dubai, the average temperature is 107 degrees Fahrenheit and wet bulb is 75 degrees Fahrenheit. These values you can get from local authorities in your location. This is provided by Dubai municipality, so you can get in your location from the local authorities. So as we know that outdoor design temperature for Dubai is dry bulb 107 degrees Fahrenheit and wet bulb is 75 degrees Fahrenheit. So we need to get the relative humidity and humidity ratio from psychrometric chart. So let's move back to our psychrometric chart. Let me zoom out this one. Okay, if we go to chart and go to set points and then add points. As we know that outside design driver temperature for Dubai is 107 degrees Fahrenheit and wet bulb is 75 degrees Fahrenheit. As you can see that the other parameters are also calculated over here. So we our concern is about humidity ratio and relative humidity. So if we have a dry bulb 107, wet bulb is 75, then our relative humidity is 22.4% and humidity ratio, this W is representing the humidity ratio. So humidity ratio is 79.5 grains per lb. So as you can see in our Excel sheet E20 form, we have input our relative humidity as per psychrometric chart is 22.4% and humidity ratio is 79.5 grains per lb. So now for indoor design conditions, for the most comfort system, we know that for human comfort system, indoor design temperature is from 75 to 78.5 degrees Fahrenheit. So we have selected 75 degrees Fahrenheit indoor design temperature. And for most comfortable system, indoor design relative humidity is about 50 to 60%. That's why we have selected 50% relative humidity. So we know that indoor design dry bulb temperature is 75 and relative humidity is 50%. So now we get the wet bulb temperature and humidity ratio from psychrometric chart. So let's move back to our psychrometric chart. So we know that indoor design dry bulb temperature is 75 degrees Fahrenheit and we know the relative humidity, indoor design relative humidity is 50%. So as you can see that we have these two parameters. So the wet bulb is 62.5 degrees Fahrenheit and humidity ratio calculated over here is 64.9 grains per lb. So as you can see that we have used the same values over here, humidity ratio and wet bulb temperature. 62.5 is the wet bulb and 64.9 is the humidity ratio. So this is how you can get the parameters from the psychrometric chart while designing your HVAC system. So this software is fairly easy to use. You can get the accurate values. In this video I will tell you guys how to calculate the overall heat transfer coefficient U value for the wall, for outer wall and for the inner wall or partition walls. So let's start. Let's say we have a building where outside wall composition is given as this. That building consists of combination of different layers, that is 230 mm common brick plus air space plus 230 mm common brick and 26 mm, that is 13 mm both sides sand cement plaster. So as you can see in this figure, if you will see, this K1 is basically representing as our brick 230 mm. This H0 is over here representing as the outside film coefficient. Then we have a Ka, that is the air space over here or air gap over here, and then we have K2 representing the second brick over here, that is 230 mm. Then Hi is the inside film coefficient. So this is the general formula which we basically use to calculate the overall heat transfer coefficient U value. So as you know the composition of the wall, so this is the thermal conductance values which are given over here. These values you can find most probably in ASHRAE Fundamental 1997 or any version. You can find the thermal conductance values. So you just need to pick these values and then calculate the overall heat transfer coefficient. So let's say we have this building composition, outer wall combination. Then thermal conductivity of the brick is given as K brick 0.77. Thermal conductivity of plaster is given as 8.65, and thermal conductance of the air gap is given as 5.8. Outside film coefficient is given as 23. Inside film coefficient is given as 8.5. And this x1 and x2 values, x1 is basically 13 mm over here. As you can see, 13 mm is the sand cement plaster on both sides of the brick. So in order to convert this into meter, you need to divide by 1000. You will get 0.013. So x2 is basically the thickness of this brick, that is 230 mm. In order to convert this into meter, you need to divide by 1000, so you will get 0.23. So these are the thickness of the plaster. x1 is the thickness of plaster, x2 is the thickness of the brick. So as you see, this is the formula which we are going to use. This is general formula: 1 divided by 1 by h0 plus x1 divided by k1 plus 1 divided by k plus x2 divided by k2, so on up till 1 divided by hi. You know that this h0 and hi are the outside and inside film coefficients, and this x1 and x2 already explained you. These are the thickness of the plaster and brick. So if you have any insulation material or anything is added in your wall, you need to add these values to get the overall heat transfer coefficient. So this is the formula: 1 divided by h0. So if we are going to put the values over here, so 1 divided by 1 by h0. h0 is given as outside film coefficient is 23. So we have used 1 divided by h0 is 23 plus this the second. If you see this is the wall composition over here. Then we have sand cement plaster over here. Then we have brick. So sand cement plaster over here, this side, and sand cement plaster, its thickness is 0.013. So 0.013 divided by its thermal conductance value. Plaster conductance value is 8.65. So 13 divided by 8.65. 13, convert this into meter. 0.013 divided by 8.65. Then the next one, we have this after plaster we have the brick over here, and brick thickness is 230 mm, that is 0.23. so 0.23 divided by thermal conductance of the brick, that is 0.77. so 0.23 divided by 0.77. and then we have the air gap over here, that is Ka. So 1 divided by Ka in this formula. So 1 divided by Ka. Ka value is 5.5. You can see the thermal conductance of the air gap is 5.8. And then we have this again, we have a brick over here, then sand, cement, plaster, and then inside film coefficient here. So brick first, 230 mm. 230 mm divided by 1000 divided is equal to 0.23 meters the thickness, divided by thermal conductance of the brick is 0.77 plus, then we after brick we have this cement over here, and cement thickness is 0.013 meter divided by thermal conductance of the plaster is 8.65 plus 1 divided by hi. Hi is the inside film coefficient and its value is 8.5. So 1 divided by 8.5. So we have applied all the values over here. So after putting all the values, U overall heat transfer coefficient U of the wall is calculated as 1.07 watt per square meter Kelvin. As you can see, if I double click, I already applied the formula here. So this is how you can calculate the overall heat transfer coefficient U value of the wall, and this is for outside wall. So next is I will show you, it is the same procedure, but still I will show you the inner wall, partition wall. U value calculation. So as you can see that our interior or partition wall consists of 230 mm common brick with 26 mm 13 mm sand cement plaster on both sides. So in this case there is no air gap, we have just outside film coefficient, then sand cement plaster, then brick, and then sand cement plaster, and then we have this inside film coefficient. So there will be no there's only one brick over here. You can consider this part only like outside film coefficient, sand cement plaster, then the brick, and then sand cement plaster, and then we have this HI inside film coefficient. This is not here. So same formula which we are going to use over here. So 1 divided by 1 by H naught, outside film coefficient value 1 divided by H naught, that is 8.5. you can see over here outside film coefficient is over here, that is 23. Sorry, this is 23. One divided by 23. So plus we have cement thickness over here, that is x divided by k1. Cement thickness is 13 mm on this side, one side, and 13 mm on the other side. So 13 mm, convert this into meter, you will get is 0.013 meter divided by thermal conductance of the plaster, that is 8.65. so inside film coefficient is outside film coefficient is done, then we have sand cement plaster is done, then we have a brick, and then sand cement plaster layer. So brick thickness is 230 mm, just one brick, so 230 divided by 1000, that is 0.23 meter, divided by thermal conductance of this brick is 0.77. you can see 0.77 thermal conductance of the brick, plus cement on the other side, that is 13 mm, divided by thermal conductance of cement is same 8.65, plus 1 divided by HI inside film coefficient. Inside film coefficient is 8.5, so 8.5 over here. So this is how you have to put all the values, and you will get the inside wall U value or partition wall U value overall heat transfer coefficient. So as you can see that this is the formula I have already applied here. So after adding all the values in here, you will get the overall heat transfer coefficient U value of the inner or partition wall is 1.86 watt per square meter Kelvin. So this is how you can calculate the overall heat transfer coefficient U values. In the same way you can calculate, if you know the material for the roof, floors, doors, you can calculate the U values for every single material, because these values, U values, overall heat transfer coefficient, these are the things we are going to use in our HVAC system design. While we are designing our system, this is very important parameter that needs to be calculated first to calculate the heat transfer, to calculate your heat loads. So in the last video I told you about psychrometric chart, and in this video I told you about the overall heat transfer coefficient U values. So these things we are gonna use in next videos to calculate our heat load for some particular project. In this video I will tell you guys about the equipment selection as per your calculated heat load. So this is the sheet I am going to use over here. If you have seen my previous tutorial number 16 and 17, in which I have already explained how to calculate the heat load using E20 form and HAP software, so I will continue by following the same procedure from there. So let's move. So first you have seen there I have 4 different rooms over here. I'm going to select the AC machine as per this calculated heat load. So there I have a catalog by Hvac. So I'm going to select a machine from this sheet. So first we have a recreation room, and in the recreation room, as you can see that we have already calculated the heat load, and TMBH over here is 18.13 and T kilowatt is 5.26, TSMBH is 16.9 and TS kilowatt is 4.9. So, and CFM is 826 and 388.5 liter per second is the airflow rate. So all of the values I have already put here. The first one is in TMBH and the second one 5.26 is in the T kilowatt. Same in this column, same in this column, that is CFM. First one is the CFM 827 and second one is 389 liters per second, that is the airflow rate. So I have already put all the values over here. So I'm gonna show you how to select the machine. So let's move to this catalog. First focus on this CFM airflow rate, that is CFM or liter per second. I'm going to select the machine as per 389 liters per second. So if I move to this chart 389, okay, if we go to this airflow column in liters per second, 389, it's exactly not there, so we will select the nearest one, that is 442 is the nearest one. Or we can do one more thing, we can select two FCUs. This is FCU2 198 liter per second and FCU3 198 liters per second. So 198, two FCUs, if we will select, it will be 396 liters per second. And how much is over there? 389. So it's okay, we can select this one with 396 liters per second. So we are going to select two FCUs for recreation room, that is 198 liter per second and 198 liters per second. So it will be 396 liters per second. In this column I will put only liters per second. Okay, so how much is the TS kilowatt or T kilowatt, we will also see over there. This column is for kilowatt, there is total duty kilowatt and the other is sensible duty kilowatt. So it will be 3.88 because we are selecting 2, so it is 7.76 total duty kilowatt, 7.76. And TS kilowatt, how much, that is sensible duty, it is 2.68, 2 times because we are selecting two FCUs over here. It is 5.36 sensible kilowatt, 5.36. So this is how you can select the machine. So 389 liter per second is our calculated, and obviously we have to go for the higher, we will not go for lower. That's why we have selected 396 liters per second. Okay, in the same way we are going to select the machine for showroom 1, showroom 2 and Majlis sitting area. So what we have over here is 1406 liters per second is the airflow rate. So let's move to the catalog again. 1406 liters per second. As you can see that maximum over here is 938 liters per second. Okay, we will select 938 liters per second. 1406 is the total, so we are left with 468 liters per second. 468, so 468 is not there, 442 is there, and higher number after 442 is 518. So we are going to select two machines for showroom 1, that is 938 liters per second and 518 liters per second. That is 938 plus 518. So total 1456 liters per second. Okay, so what is the TMBH and TS kilowatt? Same we can check over there. For 938 T kilowatt is 15 point, that is total duty kilowatt is 15.36, and 518 liters per second machine it's 9.85. So total 25.2 total duty kilowatt, 25.21. And then TS kilowatt, that is sensible duty kilowatt, how much for 938 liter per second, that is FCU2 and that is FCU5. So FCU2 it's 11.48 and FCU5, that is 518 liter per second, is 6.91. So 18.40. And so you can see that calculated heat load is that much, and the airflow rate for that machine is 1406, that is calculated, and from the catalog we have selected 1456, that is 1456 liters per second. As I told you, we will select machine on the higher side, will not go for the lower side for safety. In the same way we will select showroom 2. As you see that 1624 liters per second, that is the calculated airflow rate. So let's move to the catalog again. 1624. As I told you, 938 liters per second is the maximum available there. So we will select 2 or 3 machines. So 938 1624. So one machine if we select for 938 liters per second, so we are left with 686 liters per second. So 686 liters per second. 628 is there. Okay, if we will select 2 more machines of 371 liters per second, how much it will be? 686. It will be 742 minus 686. So okay, so we are on the higher side, so let's select this machine. 2 FCU number 1 quantity 2, that is 371 liters per second, plus one machine FCU2, that is 938 liters per second. So 1680 liters per second. So 3 machines we have selected for this area. 1680 liters per second. And same way we'll go and check TMBH and TSMBH, or T kilowatt or TS kilowatt. So as we have seen that 938, that is FCU2, total duty is 15.36 plus, and we have selected FCU1 2 quantities, that is 371 liters per second, and its total duty is 6.53. 2 times we have selected 2 machines, so total 28.4 total duty kilowatt, 28.42. And then we have to check TS kilowatt. So FCU2 938 liter per second, sensible duty is 11.48, and FCU number 1 we have select 2 quantity, that is 371 liter per second, and sensible duty is 4.82. So total sensible duty is 21.1. So as you have seen that the calculated airflow rate is 1624 liter per second, and we have selected 1680 liters per second. So we have to use 3 FCUs over here to fulfill this requirement of 1624 liters per second. So this is how you can select your machines as per your calculated heat load. So there I have prepared an Excel sheet in which I will show you guys how you can select your indoor units and outdoor unit based on your air conditioning load, whether it is cooling or heating load. So we'll see how we will select indoor and outdoor units. So there are different steps which we have to follow in order to finish the selection, and in the end we will check whether the machines which we have selected over here justify our heating and cooling load or not. So let's start. We'll start with one example. As you can see, this is the system I'm going to discuss with you guys. So let's suppose we have 11 zones over here in our system on the ground floor. As you can see, the spaces over here: office, meeting room, locker room, and different spaces over here. And the load which we have calculated over here is also given. You know that how to calculate the load using Hvac software and using E20 sheet. So using this process you can calculate the heating and cooling load. So let's say this is the cooling load which we have calculated and heating load for our spaces. So total cooling load is 51.4 kilowatt for all the spaces, and total heating load is 52 kilowatt for all the spaces. So we are going to select the indoor unit for each space. So before starting the selection of indoor unit, we need to know the indoor design conditions. So when cooling, indoor temperature is 27 degrees centigrade dry bulb, and wet bulb is 19 degrees Celsius. And when heating, indoor temperature will be 20 degree dry bulb. And outdoor temperature conditions, let's suppose we are working on the location where outdoor temperature when cooling is required is 35 degree dry bulb, and in the same place when heating is required, the outdoor temperature of that location is 6 degree dry bulb when heating is required, and 3 degree wet bulb. And two more things which we have to use over here as input. Let's suppose the equivalent length of the piping is, refrigerant piping is 46 meter we have used over here, because we have to use this in our selection and calculation. And the height of the outdoor unit, so the height of the outdoor unit to the outdoor unit to indoor unit is we have used 20 meter over here. We will gonna use this height also in our selection and calculation. So these are just input parameters. We know the location, so according to the location we have selected the outdoor temperature, that is 35 degree dry bulb, and for when cooling is required, when heating is required, this is the temperature. So first step, you have to select the standard capacity based on your air conditioning loads. So this standard capacity which we are going to select over here, I want to tell you one thing. This is a preliminary selection, not a final selection of the indoor units. Final selection we will do over here. This is the corrected capacity of all indoor units, cooling or heating. This is our final selection. So this is just a preliminary selection of indoor units. So we are going to select the machine for this office space, having a cooling load of 6 kilowatt and heating load of 6.2 kilowatt. So let's move to indoor unit models over here. We have a 6 kilowatt for cooling and 6.2 kilowatt for heating over here. So this is all the indoor unit models over here. Let's say I'm going to use 4-way air discharge cassette type. So our loads are 6.0 for cooling and 6.2 for heating. So 6.0 for cooling and 6.2 for heating. So if we are going to select this one, this will satisfy the heating capacity, but this machine will not gonna satisfy the cooling capacity, so we cannot select this machine. So we are going for this machine with the cooling capacity 7.1 and heating capacity 8. So this is the model of this unit, MMU AP0242H. This capacity which we are going to select for the machine should be higher than our air conditioning loads for both heating and cooling. So as you can see that 7.1 is greater than 6 and 8 is greater than 6.2. So we are going to select this A24 type MMU AP0242H. So this machine we have used over here. As you know that the cooling which we have selected over here is 7.1 and heating is 8 kilowatt. So 7.1 and 8 kilowatt which we have selected over here. So in the same way you have to select for all the rooms over here. Let me give you another example. Say for restroom, our cooling load is 4.6 and heating load is 4.8. 4.6 and 4.8. As you can see over here again, heating load capacity it's okay, but cooling is not okay. So we cannot select this machine. We have to go for higher load. Our standard capacity of the machine should be higher than our calculated heating and cooling load. So we are going to select this machine because 5.6 is higher than 4.6 and 4.8 for heating. So we are going to select this machine MMU AP018 2H, that is 18 type. 18 type means 18,000 BTUs. This is the capacity rank. I already explained you about the capacity code and capacity rank in my second video, part 2. Capacity code is basically the horsepower of this machine and capacity rank is BTUs, 18,000 BTUs. So we are going to select MMU AP0182H. So this is the machine which we have selected, and the load of this machine is 5.6 for cooling, 6.3 for heating. So in the same way you have to calculate for all rooms cooling and heating loads, and then you have to sum over here for all the loads for cooling and for heating also. So now we will calculate the corrected capacity A for each space. So how you will gonna calculate this corrected capacity A? There is a formula which we have to use. Corrected capacity A is equal to standard capacity of this space for cooling, because we are here working on cooling over here. So this standard capacity for cooling into temperature correction for the cooling, that is 1. So now I'm gonna show you or tell you how did I get this temperature correction factor for cooling and heating 1. So we are going to use this factor over here to calculate the corrected capacity A. So I'm gonna move to this PDF file, and there we have some tables and charts which we have to use to calculate the temperature correction factors. So this is for the cooling capacity calculation. In the same way we have a charts and tables for heating capacity calculation. So first I'm going to show you for cooling capacity calculation, this correction chart which we are going to use. In the beginning we have assumed that the indoor condition which we have used is 27 degree dry bulb and 19 degree wet bulb. So we are going to use this when cooling is required. So we are going to use this indoor temperature condition when cooling is required, 19 degree wet bulb. So as you can see over there, x-axis we have indoor wet bulb temperature for cooling, and y-axis we have a capacity correction value. So as you see that our for cooling, our wet bulb temperature for indoor design condition is 19 degree wet bulb. So 19 degree wet bulb. This is 15, 16, 17, 18, 19. This will be 19. So all the way up over here, when you touch over here, go to the left side. So what is the correction factor over here for this capacity is 1. So that's how I got this 1. If you have a different temperature, like if you have a 16 or 17, let's say 17, so go over here, 15, 16, 17, 17 touch over here, then it will be around 0.94, something like this. So in our case we have 19 degree wet bulb for indoor design conditions. So all the way up 19, and then move to the left side, we have 1 degree. Our correction temperature is 1. So that's how I got this 1 over here for cooling. So I'm gonna show you for heating also how did I get 1. So move to our heating chart, heating capacity. Yeah, over here, as you can see over here, this is our correction chart for the heating capacity calculation. So over here you can see that when heating is required, our indoor design temperature condition is 20 degree dry bulbs. So we have to use this one in the chart, 20 degree dry bulb when heating is required. As you can see that x-axis we have indoor dry bulb temperature, and y-axis we have capacity correction. So we have a 20 degree dry bulb, indoor dry bulb. So all the way up here and move to the left side, 1. So again you can see over here we have temperature correction factor for heating capacity calculation is 1. So that's how I got 1 over here for heating conditions. So this is how we got this temperature correction. So using this temperature correction in our Excel sheet, as I told you about the formula for calculating the corrected capacity A, you just need to multiply the standard capacity with this temperature correction. So in the same way you can calculate the corrected capacity A for heating conditions, same formula which we have used over here, but for heating of this standard capacity. So heating of this standard capacity of this particular space, multiply this heating factor which we have calculated over here, that is 1. So this is how you can calculate the corrected capacity A for indoor units. So in the end you have to sum up for cooling over here, and you have to sum up for heating over here. And why we have sum up of here? Because on this basis we have to select our outdoor unit. So now we are going to select our outdoor unit, and there's a note again, this is a preliminary selection of outdoor unit which we are going to do over here. Final selection we'll do later. So this is just a preliminary, just like the indoor unit. So as you know that the load which we have calculated for corrected capacity A, the sum which we have calculated here is 61.3 kilowatt, and for heating it is 68.9 kilowatt. So preliminary selection of outdoor unit, it is basically the standard capacity no less than the total value of the corrected capacity A for heating and for cooling. At the same time we have to check both connectable indoor unit numbers and outdoor unit diversity. So we are going to select this outdoor unit based on over this corrected capacity sum for cooling and heating. So let's say we have calculated over 61.3 kilowatt for cooling and 68.9 kilowatt for heating. So move to our outdoor unit models over here. How much we have calculated here? 61.3 and 68.9. As you can see over here, 22 horsepower unit, which is a combined unit of two models, that is 2214 HT8 and 2214 T8, that is 10 horsepower and 12 horsepower, two outdoor units. So it's a combination of two outdoor units. So as you can see, the cooling capacity for this model is 61.5 and heating is 69 kilowatt. So our calculated corrected capacity is 61.3 for cooling, and here is 61.5. so 61.5 is greater than 61.3, so we are safe. And for heating, as you can see, for the same unit, heating is 69 kilowatt, and one which we have calculated here is 68.9 kilowatt. So both are greater, both heating and cooling for this unit is greater, the one which we have selected. So model is this one, MMY AP2214HT8. So this model which we have selected over here, the standard model of 22 horsepower. As you can see, this is 22 horsepower model with cooling 61.5 and heating 69. So this is how we did the preliminary selection of outdoor unit with cooling 61.5 kilowatt and heating 69 kilowatt. So this is how we did the selection. Now we move to another step, that is corrected capacity B for cooling and heating. Same way we will calculate for cooling and heating. So as you remember, for corrected capacity A we have used this indoor correction temperature for cooling and heating for corrected capacity A. But in corrected capacity B we are going to use this piping correction factors for both cooling and heating. As you can see the formula over here, corrected capacity B is equal to corrected capacity A for cooling multiplied by this piping correction factor for cooling. In the same way, corrected capacity B for heating will be corrected capacity A for heating for that particular space multiplied by this heating piping correction factor. So now I'm gonna tell you how did I get this 0.92 piping correction factor for cooling and 0.97 piping correction factor for heating. So if you know these piping correction factors, it's easy, just need to multiply and you will get this corrected capacity B for each indoor unit. So let's go back to our charts over here. This is for cooling. As you see over here, for cooling the piping correction factor is 0.92. And this is all the charts for cooling capacity calculation. So as you know that the outdoor unit model which we have selected here is 22 horsepower outdoor unit model. So 22 horsepower model will be here, and the standard model we have selected for this one. So according to this outdoor unit model, which graph we have to use for the piping correction, that is A2. So these are the graphs. This is A1 for outdoor unit model, this is A2 for outdoor unit model, and this is for cooling capacity correction. So we are going to use this A2 graph. So according to this A2 graph, which we have on the x-axis, we have a piping length, equivalent length in meter on the x-axis. Y-axis we have the height of the outdoor unit. As you know that we already know the equivalent pipe length of our project is 46 meter, and height of the outdoor unit, that is from our indoor unit to the outdoor unit, height is 20 meters. So length 46 and height 20. And chart, we already know that we have to use A2 chart across this 22 horsepower outdoor unit standard model. So 46 is our equivalent length. Over here, must be somewhere here, go over here, and 20 is the height. 20 is the height, so it will be somewhere in between 90 and 92. So this is how we have used this correction factor 92 for cooling, 0.92, that is 92%. Over here on the x-axis, that is 46 46 meter, go up, and 20 is the height, so it will cross somewhere here, so it will be like 92%, so it's 0.92. so this is how we have calculated this piping correction factor for cooling, that is 0.92. now we are going to calculate this piping correction factor for heating. So go to our heating capacity calculation charts, and this is the graph which we have to use. As you see that for heating there is only one graph. Yeah, there is only one graph which we have to use for all the outdoor units from 8 to 48 horsepower. It's only one graph. So same condition, equivalent length is 46 meter, height of the outdoor unit to the indoor unit is 20 meter, between indoor unit and outdoor unit height is 20 meter, so 46 and 20. So as you can, and this is the equivalent length as you can see over here to the furthest indoor unit, outdoor unit to the furthest indoor unit, it's like this, and the height you can see over here. So this is the graph we are going to use. 46 must be somewhere here, go up all the way here till 20, so it's gonna touch somewhere here 97%, so it will be 0.97. so this is how we have used 0.97 piping correction factor for heating. So this is how you have to calculate these correction factors depending on your piping equivalent length and height between outdoor and indoor unit. So you just need to multiply this cooling capacity corrected A with this correction factor for cooling to get this corrected capacity B for this particular space. Same way you have to calculate the corrected capacity B. You need to multiply this corrected capacity A with this heating piping correction factor 0.97. so in the end you have to sum up corrected capacity B over here, and for cooling and for heating also you have to sum up over here, and make sure that the corrected capacity B which you have calculated over here for cooling and heating, that should be greater than your air conditioning load for each space. It should be greater than your air conditioning load for each space. So if it is not like this, any one of this is less than your air conditioning load for heating and cooling, what you have to do, you need to increase the indoor unit capacity. So standard capacity you have to increase again, and then you have to calculate again. So make sure that these values should be higher than this air conditioning load. And one more thing which I should have told you when I was doing the preliminary selection of outdoor unit, when you are doing the preliminary selection of outdoor unit, at the same time you have to check few more factors. So one of the factor is as you can see, this is the example which we are working. So you can see that 11 units over here, indoor units, 2 3 4 5 6 7 8 9 10 11. So and the unit, outdoor unit which we have selected is of 22 horsepower system, and this is based on two outdoor units, one with 12 horsepower and second is 10 horsepower, as we already see over here. 22 horsepower is subdivided as two units, that is 12 horsepower and 10 horsepower, and the number of, so thing which I should have told you before is the number of connectable indoor units. This should be checked at the same time when you are doing the preliminary selection of outdoor unit. As you can see, for this model maximum number of connectable indoor units are 37, and in our system we have total 11. You see over here we have total number of indoor units are 11, and the capacity code over here, this is 12.5 for these 5 units, and this 6 unit is 9.5, so total is 21.95. so total capacity is 21.95 and number of indoor units are 11. So as you see that the number of indoor units in our system over here should be less than this model which we have selected over here. So this is 37 and our system is 11, so we are good. So if it is more, then you cannot select this system, you have to go for another unit. Also one more thing, I have to tell you about the outdoor unit diversity. So as you or I will discuss it later when when we do the selection of outdoor and indoor unit. As you know that we did the preliminary selection over here. Now over here we will do the actual selection of our outdoor units and indoor units. So same time I'm gonna discuss this outdoor unit diversity factor, and one of the friend, he asked me what is diversity, outdoor unit diversity, so I'm gonna explain it over here. So now we are going to calculate the corrected capacity of the outdoor units and indoor units, or the actual capacity, corrected capacity of outdoor units. So the formula which we are going to use over here is, as you can see, that is a corrected capacity of the outdoor unit for heating and for cooling and heating. So as you can see that this is the final corrected capacity of the outdoor unit for cooling and for heating. Formula which we are going to use for cooling is we need to as you know that the preliminary selection of the outdoor unit cooling which we have calculated is 61.5, and the heating of the outdoor unit preliminary selection is 69. So this is the same value which we have used, as this is the standard capacity of the outdoor unit or with the preliminary selection. So these four factors which we have to use to calculate the corrected capacity of the outdoor unit: indoor temperature correction factor, outdoor temperature correction factor, connecting piping largest length, and the largest length and the longest height, which we have to use over here. This is and outdoor unit diversity. So we need to multiply these four factors with the standard capacity to get the corrected capacity of the outdoor unit for cooling. In the same way, we need to multiply these four factors with corrected capacity, preliminary selection corrected capacity for heating of the outdoor unit, standard capacity, with these four factors to get the final corrected capacity of our outdoor unit for heating. So standard capacity, you know that for outdoor unit 61.5 and 69 preliminary selection, and temperature correction factors. As you know that I already told you about the temperature correction factors, and these are indoor temperature correction factors. We have used over here 1 and 1. We already calculated it before. So that's how I write cooling 1, heating 1. And outdoor temperature I will tell you later. First let me tell you about this connecting piping length and the lift factors. So this is also, we know that equivalent piping length, largest piping length is 46 meter in our system, 46 meter largest length, and the height from outdoor unit to indoor unit is 20 meter. So this is length, and the lift length is 46 and the lift is 20. We already write over here. So the correction factors for piping correction for cooling, we already calculated when we use this one in our corrected capacity. We know that for cooling it's 0.92, for heating it's 0.97. So we already write over here 0.92 for cooling, 0.97 for heating. So now I'm going to tell you about the outdoor temperature correction factors for cooling and heating. How did we get 1 and how did we get 0.95? So let's focus on cooling first. Outdoor temperature correction for cooling. As you know that outdoor temperature correction of the location on which we are working on is 35 degree dry bulb. So move back to our chart. You know that this is the capacity correction charts, and our outdoor temperature is 35 degree dry bulb when cooling is required. So this is the chart we are going to use: outdoor air dry bulb temperature versus capacity correction for cooling. So x-axis we have dry bulb, outdoor dry bulb, and y-axis we have capacity correction values. So our outdoor dry bulb is 35, you can see over here. So 35, go up, move to the left side, when it touches this line, move to the left side, 1. So our capacity correction factor is 1 for cooling due to the outdoor air dry bulb temperature. So you see, this is how we got outdoor air dry bulb temperature. Correction factor is 1 for cooling. Now for heating, how did we get 0.95? This one also I will tell you. Go for heating, yeah, this one, correction chart for heating capacity calculation. As you know that for the location in which we are working, when heating is required, 6 degree dry bulb and 3 degree wet bulb. So 3 degree wet bulb temperature is for 35 degree outdoor dry bulb temperature cooling. So now for heating we have wet bulb temperature, outdoor wet bulb temperature for heating will be 3 degree wet bulb temperature, wet bulb. So this is our outdoor air wet bulb temperature on x-axis. Y-axis we have capacity correction. So this is a outdoor air wet bulb versus capacity correction. So our outdoor air wet bulb is 3 degree wet bulb. So this is we have to use. This is -5, this is 0, this is 5. So 3 will be somewhere here. Go up over here, touch over here, and move to the left side, somewhere between 0.9 and 1. So it will be around 0.95. So capacity correction for heating due to the outdoor air wet bulb temperature is 0.95. So this is how we got this 0.95 over here. This is the correction for heating. So the only thing left over here now is outdoor unit diversity. So what is outdoor unit diversity? Outdoor unit diversity is basically it is the ratio of connected indoor unit to the outdoor unit horsepower. As you can see in our example, we have connected indoor units. This is the sum of these 5 indoor units, that is 12.5, and this is the sum of these 6 indoor units. So how much it is? That is 12.45 plus 9.45. So indoor unit horsepower is around 21.9. That's we already write over here. That is 21.95 for indoor unit, and the outdoor unit which we have selected over here is 22 horsepower. So it is basically the ratio of horsepower, indoor unit to the outdoor unit horsepower. So this 21.9 divided by 22, that is 99.5, is approximately 100%. So move back to our chart. This is the outdoor unit diversity. As you can see that this is x-axis, we have a standard capacity ratio, indoor units total capacity ratio, and this is the correction factors. In our case it is 100%, and this chart is for cooling. So 100%, go up to the left side, you have 1, so correction is 1. And for if you go for heating, you can see this is for heating, it will be same. So standard capacity on x-axis ratio for indoor to outdoor unit is 100%, which we already see in our example. So 100%, go up, again it's 1. So this is how we have used this outdoor unit diversity, 1 for cooling and 1 for heating. So outdoor unit diversity is basically the ratio of connected indoor unit to the outdoor unit percentage. So in our case it is 21.95 divided by 22, that is almost 100%. That's why we have used one correction factors. So as we know all of these factors for cooling and for heating, we just need to multiply these correction factors with preliminary selection of the standard capacity of the outdoor unit for cooling and for heating. So this is how we get this corrected capacity of the outdoor unit, that is 56 kilowatt. This is the corrected capacity of outdoor unit for cooling, and for heating we got 63.58 kilowatt. So now we have to calculate the corrected capacity C for all indoor unit. Before that it was a preliminary selection, now this is the final selection or corrected capacity C. Outdoor unit we already calculate corrected capacity, so now we are going to do for indoor units based on our outdoor unit corrected capacity. So how we are going to calculate this corrected capacity C? Corrected capacity C, as you can see from this formula, corrected capacity C for this space is corrected capacity of the outdoor unit, that is 56.58 into F7, and this is F7 divided into standard capacity of this indoor unit divided by total standard capacity of all the indoor units. So this is how you can calculate the corrected capacity C of indoor unit for cooling, and for heating in the same way you can calculate. You can see the corrected capacity of this outdoor unit which we have calculated is 63.58 kilowatt. So corrected capacity C for this space for heating is this F37. This is F37, that is 63.58. So this corrected capacity C for heating, this sum into this is standard capacity for this space divided by total capacity of all the spaces. So this is how you can calculate the corrected capacity C. All the formulas are applied here. So this is how you can calculate the corrected capacity C of all indoor units. So in the end what you have to do, this is your air conditioning load, same as above, and these are all the models which we have used for indoor units, and this is the same corrected capacity C for cooling and for heating. So these are the same values which we have to write over here, and this is the sum of corrected capacity C and for cooling and for heating, and this is same as this one which we have calculated for corrected capacity of the outdoor unit. So this is our final selection or corrected capacity for the outdoor unit. So we have to select this model with corrected capacity of the outdoor unit for cooling is 56.6. So we are going to select the machine with the cooling capacity required is 56.6 and heating capacity required is 63.6 for heating for the outdoor unit model, and this is the individual indoor unit models for all the spaces. And make sure that the corrected capacity C which we have calculated here for cooling and for heating, this should be greater than your calculated air conditioning load. If this condition is satisfied, then I applied the formula here. If this condition is satisfied, then it will be okay for each unit for heating and cooling. If this condition is not satisfied and your either heating or cooling load for corrected capacity C of each indoor unit is less than your air conditioning load, then it will not be okay. Let's say I'm gonna decrease to show you an example. Let's say this is 2.8. As you see over here, the air conditioning load is 3, but corrected capacity is 2.8. That's why it's not okay. If it is like this, you need to increase the outdoor unit capacity, and then you have to calculate again the corrected capacity of this indoor unit to satisfy this condition. So make sure that your heating and cooling loads which you have calculated air capacity C should be greater than your air conditioning load for each room. So this is how you can select your outdoor an indoor unit model based on your air conditioning load for heating and cooling. So it depends on your outdoor temperature condition on your location in which you are working. So according to that you have to write these temperature conditions and you have to calculate these correction factors for heating cooling. So there I have the main screen of the VRF system selection tool software, and here in the Excel sheet as you can see that we are going to use these loads to design our VRF system. This is the cooling load and this is the heating load for all the spaces mentioned over here. So total cooling load is 51.4 kilowatt and total heating load is 52 kilowatt, and these are the outdoor design conditions which we are going to use when we design our system. So let's move back to our VRF selection tool software. But before starting this VRF selection tool software, let me show you one thing over here. This is the flow chart of the selection tool software which you have to understand over here. Basically we start to create the project first and then we select the method. Basically two types of methods are available here in this VRF selection tool software. One is a wizard type selection, that is detailed design method, and the other one is drag and drop drawing method. So in wizard type selection we select and set indoor. After adding this outdoor temperature information, we will select or set indoor units in the wizard type selection. So after selecting our indoor units, we will move to the next tab that is related to selection of outdoor units. So when you finish the selection of outdoor unit, you will link them, indoor and outdoor unit, you have to link them, and then you have to create the piping will be created automatically depending on your indoor and outdoor unit capacity. But in drag and drop drawing method you will create the refrigerant piping first and then you will select or set your indoor units, and then you will move to the next tab and select your outdoor units. So in the end you will select the central control device and then you will create the output project of your data. So only difference between these two methods is here you will select first indoor unit, outdoor unit, then link them, and then piping diagram will be automatically created. But in drag and drop drawing, first piping diagram, refrigerant piping diagram you have to create, then set your indoor and outdoor units. So today I'm going to discuss this drag and drop drawing method to create our system. Later we will discuss about this wizard type selection. So let's move back to our selection tool software over here. So as you can see that this is the main screen of our VRF selection tool software and the different options available over here. First you have to create the project. So in order to create the project you can either click here, that is create project, or you can go to edit, this option here, that is create project. So we'll create project first and this screen will appear, and then you have to give the information over here. So let's say I'm going the project number as 111 and project name, whatever the project name you have to specify here, and customer name maybe like CC, and make sure that all the entries with the star it's necessary to fill up. Other entries it's up to you whether you want to fill or not, it's up to you, but when you start your project you have to fill all of them. So and then you can also give the address, you can specify the installer, whoever the installer, you can specify the name or company name, you can specify the installation date, let's say it's 31st or 28 February, and commissioning date, let's say it's 28 March, whatever the date you can select over here. So after selecting everything you just have to save here, and if you want to edit your project data again, So you just select your project over here and then go over here. This is the edit project, or you can go over here, edit, and then edit project. So you can edit the entries once again once this window is open. So once this step is finished, creating your project or editing is finished, you can either double click this one, just select the project and double click to move to the next step, or you can select from here also, this is the next step, or go edit and go to the next step. So I'm going to the next step by double clicking. Once you double click this one, it will ask you about the method, which method you want to use. You know that the method which I told you, one is a wizard type selection, other is a drag and drop drawing method. First one is a wizard type selection, second is drag and drop. Today I'm going to discuss drag and drop drawing. So I'm going to select this one, and then I will select this next button, or you can go to edit and next button. So I'm going to select this next step. Once you select the next step, then this new window will appear. Here you have to give the outdoor information, outdoor temperature information over here. Remember that I talked to you about the location in which I'm working right now. The outdoor design temperature conditions are this one for cooling and for heating. So move back to our software and I will click outdoor temperature information. So in our location, outdoor cooling dry bulb temperature is 107. So I'm gonna select 107 cooling dry bulb temperature, and heating wet bulb temperature is 37.7. So 37.7. So once you select these temperatures, cooling dry bulb and heating wet bulb, you can save it and then exit here. So after selecting your outdoor temperatures, you have to go to here, that's new. New means you will create a new refrigerant piping diagram over here, or you can go here also in the edit tab and you can select new. So I'm going to select new to create a new refrigerant piping diagram. So I will select here new. Once you select new, this window will appear. As you can see on the left side, all different types of indoor units are available in this software which we are going to use, and branches are also available. Whether we want to use a Y-shaped branching joint, we want to use 4 branching header, we want to use 8 branching header. So there are different types of indoor units are available here, and outdoor model, as you can select from here also, or when you will double click this outdoor unit, then you can select your outdoor unit. As you can see, this is our outdoor unit in the refrigerant piping diagram, and this is our indoor units, but these are dummy units. We will have to select the indoor units from here and then drag into the dummy units. But before starting this refrigerant piping diagram, let's move back to our Excel sheet. So as you can see that based on our Excel sheet load calculation, heating and cooling, we'll select our indoor units. So first I'm gonna draw the piping diagram first. As you can see that we have a total 11 indoor units here in our system. So I have to use 11 indoor units over here. So let me create this piping diagram first. So I'm gonna use this Y-shaped branching joint and 4 branching header combination in my refrigerant piping diagram. So I have to use 11 indoor units first. So let me create this Y branching here also. When you click this dummy unit and right click on this one, there's option insert. You can insert Y-shaped branching joint, 4 branching header, or 8 branching header. So I'm gonna use Y branching header here, 1. So now I have 3 indoor unit, depending on what type of configuration you are going to use. So according to your you can select a Y-shaped branching header, or you can select 4 branching header or 8 branching header. So I'm gonna use one more Y branching joint here. and one more here, and then again I'm gonna use Y branching joint here, and one more Y branching here, one more Y branching here, and then I will use one 4 branching header here. So how many indoor units I have now? 1 2 3 4 5 6 7 8 9 10 11. So I have created my refrigerant piping diagram, and I have 11 indoor units available here in my refrigerant piping diagram system, VRF system. So now I am going to use the indoor units based on my load calculation, cooling and heating load. So first move back to our software. Let's suppose I'm gonna use this for this office, which has 6 kilowatt cooling load and 6.2 kilowatt heating load. Office 1. I'm gonna use this 4-way air discharge cassette type unit. You just need to select and drag over here and then leave it. So your indoor machine will automatically come over here. As you can see that there are different models available here. You can select from them also, like slim duct type, concealed duct, high static pressure type, or 1-way air discharge, high wall 2 series, 4 series. So whatever you want, you can select the indoor unit from here. So I'm gonna use this 4-way air discharge cassette type unit, and the indoor unit name which I'm going to use here is VRF1, and space name, as you can see, the office 1. So I'm gonna name it office 1, and floor, we have a ground floor there, so it's GF. And there you have one option, that is indoor unit selection method. If you will select this auto, then it will gonna select your capacity rank of the machine, which is basically the horsepower of the machine based on our calculated load. If you will uncheck this one, you can select the machine from all the models available over here. So I'm gonna use this auto method over here, and the indoor design condition which I'm gonna use over here, indoor cooling dry bulb, I'm gonna use is 75. That's okay, that is 23.8 degrees Celsius, and indoor wet bulb temperature, that is automatically calculated when I will give the humidity value. The humidity value which I'm going to use here is 50% for design. For indoor design comfort, it is recommended to have 50% relative humidity. As you see that if I change this to 40, our cooling wet bulb temperature will be changed. So I'm gonna use this 50 as per design recommendation. So I'm gonna use 50. So wet bulb over here is 62.6 degrees Fahrenheit, and the indoor heating dry bulb temperature I'm gonna use over here is 70 degrees Fahrenheit. And now I have to mention my cooling and heating load. So cooling load I'm gonna mention over here now, that is 6 kilowatt. So I'm gonna use 6 kilowatt here, and sensible, let's say our sensible is 4.6, and what is our heating load over here, that is 6.2 kilowatt for office 1. So I'm going to use 6.2 kilowatt here. So as you can see that based on our these loads 6 and 6.2, this machine is automatically selected based on our heating and cooling loads. So now I have to give the piping length from the joint equivalent. So from this joint to the machine I have to mention the pipe length. So let's suppose we have this length is, we have to mention equivalent and actual length. Let's say our equivalent length is 2.8 meters and actual length is 2.5 meters, and we have to mention the height difference between indoor and outdoor units also. Let's say our outdoor unit is installed at the roof, and the height difference between our roof and the ground floor ceiling is 4.5 meter. Whatever the height is, you have to mention here. Let's say it's 4.5, so I will mention 4.5 meter here. So this fan speed, I'm gonna select is high. Okay, I don't want to use any heater here. Or okay, so all input are done. So once you select the machine and all inputs are done, so you just need to save it. If any input is missing, it will give you some error, so you need to specify that input. So I'm gonna close this one, and now I'm gonna select the second machine over here. So this time I'm gonna use, what is the space here, meeting room. So meeting room, now I'm gonna use this duct concealed duct standard type unit. I'm going to use over here indoor unit. So just drag and drop here. Once it's done, in the same way you have to fill this or give all the inputs. This is our meeting room, and room name is this is VRF2, and room name is meeting room, and floor is ground floor. I'm gonna select auto again. These conditions are same, only this I'm going to change. So this one, you remember that I have used the same condition for the first indoor unit, same I'm going to use for the second indoor unit. And the loads for the meeting room are 4.6 kilowatt for cooling and 5 for heating. 4.6 and 5. So 4.6 for cooling and 5 for heating. Let's say its sensible load is 3.9 and heating is 5. So now I have to specify the piping length from the joint equivalent. So from this joint to the machine, I have to specify the length. Let's say I'm gonna use equivalent is 2.8 and actual 2.5 meter, and height difference between indoor and outdoor units same 4.5 meter, and then save it and then close it. So now I'm going to use I'm going to specify the third indoor unit for third space, that is office 2. So this time I'm gonna use the same 4-way cassette type unit. So instead of again drag and drop here, I'm gonna copy the same data. If you will just right click on this machine and copy, and then here right click again and then paste. So same data will be pasted here, so I'm just gonna modify it. Just double click this machine. I'm gonna select here VRF3, office space 2, ground floor, auto selection, and this 70. Okay, and what is our load here? As you can see, for office, cooling 3.8, heating 3.3, 3.8, 3.3. So 3.8 kilowatt cooling. Let's say this is 3, and heating how much? 3.3. 3.3. So we have specified our heating and cooling loads, and now we have to specify the length again. Let's say it's same 2.8 from here to here it's 2.8 equivalent we are going to use, and 2.5 is the actual we are going to use, and height will same, that is 4.5 meter. So save this one and then close it. So now I have to specify the fourth indoor unit for number 4 space, that is locker room. So this time I'm gonna use this high wall type unit over here, 3 series or 7 series. So I just have to drag and drop here into the dummy indoor unit, and then I'm gonna use its name as VRF4. Room name is locker room, and floor is ground floor, and I'm gonna use the auto selection method over here. Same everything except this last one I'm gonna change to 70 heating dry bulb temperature, and now I have to specify the load. Locker room 1, it's cooling 3 and heating 3.1. 3 and 3.1. 3, let's say the sensible is 2.4 and 3.1 is the heating load. So 3 and 3.1 we have specified here, and now we have to specify this length again. So let's say I'm gonna use same 2.5, 2.8 equivalent and 2.5 actual length, and height difference again I'm gonna use same between indoor outdoor unit is 4.5 meter, because this one is on the ground floor and our outdoor unit was on the first floor, and this is locker room 1. Here locker room 1. Then after specifying all the inputs, then save it and close it. So now I'm gonna select one more indoor unit for our next space, that is meeting room 2. So let's say I'm gonna select the same unit which I have used here, standard duct type, for meeting room 2. This is for meeting room 1. We should mention this one as meeting room 1. Save this one. So instead of drag and drop another, I want to copy the same data, just edit this one. So right click this one, copy this machine data, and right click, paste. So now I'm gonna edit the data for this meeting room 2. So this VRF is 5. This is our VRF 5, and meeting room 2, same ground floor, auto method. This is all okay, and now we have to specify our loads. Let's say our cooling load is 11.8 kilowatt and heating is 12. 11.8 kilowatt is cooling, and let's say our sensible is 10.2, and our heating load, that is 12 kilowatt. 12 kilowatt. So I'm gonna use the same length from the joint to the machine, that is 2.8 meter equivalent and actual 2.5, and this is 4.5 height between indoor and outdoor unit. So just save it, then close this tab. So now I will input the data for another space, that is locker room 2. So first locker room I have used this 3 series high side wall. So I'm gonna copy the data from here and then paste here on this dummy indoor unit. and then I will double click to modify the data. This is our VRF6 and locker room 2, ground floor, auto selection method, and now I have to add the cooling and heating load. So cooling load is 3 and heating load is 3, both are 3 kilowatt. So 3, let's say this is 2.4 and this is also 3. So cooling is 3 kilowatt, heating is 2 kilowatt, and same piping length I'm gonna use from this joint to this machine, equivalent and same actual. And height between indoor and outdoor unit, it's same 4.5. I'm gonna use save and then close this one. So one more indoor unit for next space, that is our restroom. So for restroom I'm gonna use this 4-way cassette type. I will copy the data and then I will paste here. Then double click this one to edit the data, and this would be our VRF7 and its room is restroom. So on the ground floor, auto selection method we are going to use, and its cooling load is 4.6, heating is 4.8. 4.6, 4.8, and let's say our sensible is 3.6 here, it's 5. So this is our cooling 4.6 and heating is 4.8. Okay, so the length, pipe length from the joint, from this joint to this machine is 2.8 equivalent and 2.5 actual. So we can save this one and then close it. So there are 4 more indoor units which we have to add over here. So what is our next space? That is smoking room. So I'm gonna use cassette type here again, copy data and paste on this dummy unit. Then double click to edit the data. This is our VRF8, that's okay, and this is our smoking room, same ground floor, auto selection method, and we have to specify the loads, 3 for heating and 3 for cooling and 3.1 for heating, 3 and 3.1. So 3.1, and let's say sensible is 2.4. so we have specified, and length, so the length which I'm gonna use now from this header, 4 branching header till this machine is 2.8 equivalent and 2.5 actual, and height is same because this is on the ground floor and our outdoor is on the roof, so it's 4.5 meter. So I'm gonna save it and then close it. Again I'm gonna, so next space is reception room. So I'm gonna copy this data, paste on this dummy unit, double click this indoor unit and edit your data. This VRF9 and this is our reception room. So I'm gonna change this name to reception room. Reception room, it's on the ground floor, and these conditions are same. Now I have to specify the loads, Let's say our cooling we have calculated is 3.8, heating is 3.9, 3.8 and 3.9. So this is 3.8 and this is 3.9, and let's say our sensible is 3. So now I have to specify the length from the joint. So let's say the length from this joint to this machine is 5.8 equivalent and 5.5 actual. So I'm going to use 5.8 equivalent and 5.5 actual. So this height is same, and save the data. Then close it. Then move to the next space, that is office 3 space. With the cooling load is 4.8 and heating load is 4.5. So I'm gonna copy this data from office 2 over here, paste, and double click the indoor unit. This will be our VRF10, and this is our office 3 ground floor, and then we have to specify the cooling and heating loads. Cooling is 4.8, heating is 4.5, 4.8 and heating is 4.5. Let's say our sensible is 3, sensible cooling load is 3.8. So now I have to specify the piping length from the joint. So let's say from this joint to this machine the equivalent piping length is 8.8 meters and actual is 8.5 meters. And then save it, and close this one. So now the last page is here, that is reception area. So I'm gonna use standard duct type here for reception area. So I'm gonna copy this data and paste over here. Then I'm gonna double click this indoor unit, modify the data. This is VRF11 and this is for reception area. It's on the ground floor, auto selection method. So capacity for cooling is 3 and heating is 3.1. So it is 3 for cooling, 3.1 for heating. So sensible cooling I'm gonna use, let's say it's 2.45, and again I have to specify the piping length from the joint equivalent and the actual. So let's say the length of this piping from our A4 branching header to this machine is 11.8 equivalent, and the actual I'm gonna use here is 11.5, and this is 4.5 meter. Then save this machine data and then close it. So now all the indoor units data has been specified. Now we're gonna move to our outdoor units. As you can see that since we have specified all the capacities for our indoor units, so based on our indoor units capacities, outdoor unit is automatically selected over here. And the unit which is selected here is MMY AP2416 HT8P, that is 24 horsepower system is selected based on our load calculation for all indoor units. So if you wanna modify the data or edit the data, you just double click outdoor unit. So the unit type which I'm gonna select over here is SMMSE. There are different series available here in Toshiba. So I'm gonna select this SMMSE. Since I have checked this auto, that's why this machine is selected based on my indoor unit capacities or load calculation. So and the maximum selection percentage which I have selected here is 100% based on my indoor and outdoor unit capacity ratios. So there are few more things I have to specify here, that is the main piping length. As you can see that this is 0 right now, so I have to specify this main piping length. If you remember my first video, I have told you about the main piping of the refrigerant VRF system. The main piping length is from this T connection to the first branching section. This is our main piping length over here, as you can see. So I have to specify this main piping length actual and equivalent. So let's say my main piping length actual is 6 meter and equivalent is 6.5 meter. So I have used this length over here. Now I have to specify the T-shape outdoor unit distance LA and LB. As you see, this is our outdoor units here. This is first one and this is the second one. So LA is the distance from outdoor unit till this pipe, and LB is the distance from here to this main pipe. So this is LA and this is LB. We have to specify these lengths. So let's say the LA actual which I have used here is let's say it is 2.7 for LA, and LB is also 2.7, and equivalent, let's say it is 3 for LA and 3 for LB. And one more thing we have to specify here is the height difference between these two outdoor units. Since I want both of them on the same floor, same level, so I'm gonna use 0 meter here. If you have height difference between them, then you can specify that difference in a meter over here also. So since I'm gonna use both of them on the same floor, so I have specified 0. There's no height difference between these two outdoor units. So after editing this data, you just save it. And then exit this one. So as you can see that we have specified this main piping length, but there are few more entries which we have to add over here. So as you know that we have added this pipe length, refrigerant piping length, from this Hvac branching joint to the machine, but we did not add the length from branching joint to the branching joint. As you can see, it is 0 here, 0, it is 0, it is 0. So we have specified this length, but we did not specify this length. So now I'm gonna specify the length between the joints, Y-shaped branching joints. So I'm gonna select this branching joint to specify the length between this joint and this joint. So just double click this Y branching joint, and its name is Y2. So now I'm gonna mention the actual length and equivalent length. Let's say our actual length is 2.7 meter here and equivalent length is 3 meter. So okay, so as you can see that the lengths are mentioned here, 2.7 and 3. So now I'm gonna specifying this length between two joints. So I'm gonna select this joint, and let's say the length which I'm used here is 3.2 meter actual and 3.5 meter equivalent. So it will come here. Now I have to specify between this joint and this joint. So let's say same, I'm gonna use 3.2 and equivalent is 3.5. So whatever your lengths are here, you have to specify here in your project. And if you don't select these lengths, then you will get an error. Why will you will check your system information. So let's say I will go over there. As you can see that this is an error, so we need to fix that one. Total pipe actual length is not mentioned. It's 0 meter pipe length exist. So when I specify all the lengths over there, so this error will be gone. So we need to specify all the lengths over here. So now I have to specify the length between this joint and this joint. Right now it's 0. So I'll select this one. Let's say the actual length is 6.2 and equivalent is 6.5 for this Wi-Fi joint. So this length will appear here, and now I will specify this length from this joint to this joint. Just double click this joint Y6 and mention the length. Let's say actual is 2.7 and equivalent is 3. Okay, now between these two joints, same, I'll suppose this is 2.7 and this one is 3. So now I have to specify the length between this Y branching joint and this 4 branching header. So I have to specify the length. So let's say it's 2.7 actual length and equivalent is 3. So it will appear here. Okay, so all other lengths I have already specified there. So this is how you have to specify all the refrigerant piping length. So as you can see that we have put all the information in our project, and we have designed our VRF system based on our load calculations. And you can see this dia is automatically calculated both for liquid and the gas piping based on our load calculations. As you can see that by specifying the length between the joints, that is Y-shaped branching joint and all the joints, we have specified the length. Before that, the outdoor unit capacity was 24, but now it is 26 horsepower. As you can see over here, one outdoor unit 14 and the other one is 12, so total 26 horsepower. So all these factors matter a lot while selecting your indoor and outdoor units. We specified the length over here between the joints. So this is 26 horsepower system of the outdoor unit, that is divided into 14 horsepower and 12 horsepower. And this one is header and this one is follower. If you remember, I told you about the header and the follower. Header is that unit that is nearest to the first branching section, that's why this is called header, and the other is called follower. And they should be arranged in the capacity according to their capacity. 14 horsepower should come first and 12 horsepower should come second, sorry. So this one comes first, this is second, this is header, this is follower. And if you want to study these piping diameters and lengths, you can see the piping legend over here. The first one is for the gas pipe diameter, second liquid pipe diameter, third is actual length, fourth is equivalent length. So this first one is gas pipe, that is 7 by 8 inches. Second is liquid pipe diameter, that is half inches, and 2.7 meters the actual length and 3 meters the equivalent length. So this is how you can study the legend for piping. In the same way, legends are mentioned here for outdoor units and indoor units. So this is how you can design your VRF system based on your load calculation. You have to specify your load calculation for indoor units, and using auto selection method you can select your indoor you can select your outdoor units based on your indoor load calculations and selection. So in the last I will, but before that I will click the system information. So if I click the system information, you can see that this is the specification column, and this one is a design column, and this is the result column. So make sure that all of them should be tick in the end. If it is not tick, then you need to correct that error. So as you can see, this is the design column, and in our project this is basically the limit from the supplier. This SPEC specs or specification from the supplier. This is the limit from the supplier. So we need to our design should be less than this specified limit, because this is the limit. So for example, total piping length actual allowed by supplier is 300 meters. In our case it's 80.3. So 80.3 is less than 300, that's why it's tick. Same over here. Maximum equivalent length of the outdoor unit connecting pipe is 10 is allowed maximum, and we have 3 over here, so we are good. So as additional refrigerant charge amount that's automatically calculated for our whole system is 14.76 additional refrigerant amount is required to charge. And outdoor unit capacity is 26. As you see over here, there is 26 horsepower, and two outdoor units we have used, one 14 and the other 12, and indoor units are 11 we have used. Indoor unit capacity is 24.45 is the total capacity of the indoor units, and indoor unit to the outdoor unit capacity ratio, that is outdoor unit diversity, is 94%, because indoor unit is 24.5 and outdoor unit is 26. So 24.5 divided by 26, outdoor unit diversity will be 94%. So 94, this is the design, this is the allowed limit, that is 50. It should be between 50 to 135%, and our is 94%, so that's why it's good. And the furthest pipe equivalent length actual that is allowed from the supplier is 180 meters, and in our case, our project, that is 34.5 meters, so we are in the safe range. So this is how you have to compare your design with the limitations from the supplier. So in the end, we will generate an output from our project. So you just need to click this output over here, or you can go to edit and you can generate an output data. Also you will get the electrical results also here. When we generate the report, we will get the detailed design of this electrical. So let's go to the output tab and select this one. So whatever the things you need, you can select and you can generate the output. You can generate report, table, piping, wiring, and price list, everything. So whatever you need, you just select this one. If you need Excel, you can, for all this you can select Excel. If you need CAD, you can select the CAD. If you need PDF, you can select PDF. So right now I'm gonna select only PDF. So now I'm gonna save these reports, tables, and piping and wiring diagrams, and we'll discuss the results. Let's say I'm gonna save here. Okay, just wait a moment, it will take maybe 1 minute. Once everything is saved there, I will discuss the results related to the VRF system design. We will discuss the report, table, piping and wiring diagrams, and the price list also. Just wait a little. So in my next video I will discuss with you guys about the additional refrigerant charge calculation, and we'll also use the other method for refrigerant piping design over here for the VRF system, that is wizard type selection, later in another video. Just wait a moment. Okay, it's done. So move here. Okay, these are all the PDF files which we have selected over there. So I'm gonna open this first one, the piping diagram, refrigerant piping diagram for the VRF system, which we have designed there. So as you can see that this is the refrigerant piping diagram which we have created over there. So you can take a print of this refrigerant piping diagram because everything is mentioned here. All inputs are there, load is mentioned there, and machine size is also mentioned there. Pipe sizes are mentioned, liquid gas pipe size mentioned, their lengths are mentioned, what are the accessories used here, Y-shaped branching joints, and their types are also mentioned. For example, this is RBMBY105E and this is RBMBY205E. So let's go to piping and wiring diagram in the combined state. So as you can see that this is our outdoor unit which we have selected for our system, that is 26 horsepower system. As you can see, this is blue one is the refrigerant piping over here, and this red one is the electrical cabling here for from outdoor unit to the indoor units. So as you can see that we have all the indoor units over here, total 11 indoor units, and you can see that their gas and liquid pipe sizing are mentioned there, and the lengths are also mentioned there from this joint to this machine, then this joint to this machine. All lengths are mentioned there, and these lengths are also mentioned from joint to joint lengths, and refrigerant piping dias are also mentioned for liquid and gas pipe. And as you can see that electrical wiring for the cables, their sizing is also available here. So if you go over there, you can see the outdoor unit name and its capacity, that's horsepower, and indoor unit total capacity, outdoor unit capacity, everything is mentioned here, and how much is the additional refrigerant charge calculation is required for our project is 14.76. So this much additional refrigerant is required for our project. And if you go over there, you can find the indoor and outdoor units and accessories, Y-shaped joints, header, whatever we use in our project is mentioned here, and their quantities are also mentioned here. And this is the wiring size and length for the electrical data. Over here you can see what kind of wire we can use. It's mentioned here for the outdoor unit, for the indoor units, and for remote controls. Everything is mentioned here, their wiring, labeling, polarity, their size, length, everything is mentioned here in our report. And you can see the price list also here, our project name, everything is mentioned here. Then outdoor unit, only one we have used, and indoor units, there are different types of indoor units and their quantities available, whatever the price you can mention here. And outdoor unit connection kit which we have used is this model, only one quantity. Then Y-shaped branching joints, we have used these types, this quantity, and then header, and then accessories. So this is the pricing list which you can use, and it's easy for you to order the equipments and accessories for your VRF system. So also you have a equipment list, and you have a report drawing. So this is the same thing which we already discussed before. The electrical wiring is there and refrigerant piping is there, and you have equipment catalog for indoor units and outdoor units. So this is how you can generate your report after finish your design of the VRF system. So it will be easy for you to interpret the results later after your design. If you have these reports, you can easily proceed for installation of the machines and everything. Today I'm gonna continue the VRF topic, designing and selection. If you remember, last time I discussed regarding VRF system designing and selection using software, and today I'm gonna discuss VRF system additional refrigerant charge calculation. So there I have prepared an Excel sheet to show you the calculation for additional refrigerant needed for your system. If you remember that last time I have used this software VRF selection tool to design and draw our system, and we have made the PDF file also in the form of results. So our machines like outdoor units and indoor units, these indoor units and outdoor units are pre-charged from the factory. So their refrigerant is already calculated there, but we want to calculate the additional refrigerant due to the piping which we have draw over here. So right now I'm gonna calculate the additional refrigerant due to this piping, because indoor units, outdoor units already pre-charged from the factory. So let's start the calculation. Here I have an Excel sheet. So there I'm gonna use two tables for refrigerant charge calculation, and here is the formula which I already applied here to calculate the additional refrigerant. So this first table is you can see over there, dia is mentioned 6.4, 9.5, 12.7, 15.9, 19 and 22 mm. So, and this is the additional refrigerant needed per meter length due to 6.4 mm dia. So 0.025 kg additional refrigerant is needed per meter length of the pipe due to 6.4 mm dia. So all of these lengths are mentioned per meter. Per meter we need 0.055 kg additional refrigerant due to 9.5 mm dia. So in the same way 0.35 kg refrigerant is needed per meter of dia 22.2 mm. So this is the formula which I am gonna use to calculate additional refrigerant, that is L1 into this additional refrigerant 0.025, because this is due to dia 6.4, and then L2, this is L2, and L2 into additional refrigerant needed is 0.055. So this is the values which I will give over here: L1, L2, L3, L4, L5 and L6. These are the real lengths. As you can see over here, real total length of the pipe dia 6.4 mm, real length of the pipe dia 9.5 mm, and till L6, that is real total length of liquid pipe dia 22 mm. So these are the calculation we have to perform for liquid side, not for the gas side. So that's why it's written that real total length of liquid pipe dia 22 mm L6 length. So all of the lengths we will provide over here, whatever the lengths which we have used over here, real lengths in our software. So I'm gonna use these lengths over here. So L1, which we will provide over here, into 0.025 kg of the additional refrigerant needed per meter. So in the same way, that is L5, this is our L5, L1, L2, L3, L4 and L5. So L5, how much refrigerant do we need over here? That is 0.25 kg per meter due to dia 19 mm. So, and one more thing in this formula is we need to add additional refrigerant due to the system compensation, system horsepower compensation. As you can see over here, this formula, as you already understand. And second thing, you have to add the compensation by system horsepower. So this value will take from these tables. This is the compensation due to the horsepower of the system outdoor unit which we have selected. This is for the standard efficiency models, and this is for the high efficiency models. So whatever the value of your outdoor unit horsepower, let's say our outdoor unit horsepower is 14, and additional refrigerant needed due to the 14 horsepower outdoor unit is 8.5 kg. So we need to add this one also here. So let's move back to our software. And if you remember that I have made PDF files in my last video to interpret the data. So I'm gonna open this table. So as you can see that when we were making our VRF system design in my last video, I have created a PDF file from our design. So we know that the outdoor unit capacity which we have calculated over here is, that is 26 horsepower, and we use two outdoor unit. As you can see over here, there are two outdoor unit. One is 14 horsepower and the second is 12 horsepower, total 26 horsepower. And as you can see that through the software we have calculated 14.7 kg additional refrigerant. So I will compare this value with the value in my Excel sheet. So I'm gonna, let's go back here, and you can see that this is all the diameters which we have used in our project. And you have to know one thing. This first one is for gas. These are the real lengths in meter, and the first one is for the gas pipe and second one is for the liquid. Same, first one for the gas, second for liquid. First for gas, second for liquid, and this is the total length for 3/8 including gas and liquid size, that is 27.4 half inches for gas and liquid both, that is 38. So we are going to use the liquid side length. So first we have dia 14 dia is nothing but it's 6.4 mm. So this is our length L1. So what is the length L1? 1/4 is 6.4 mm. So liquid size, as you can see that 32 meter is the length, this length in meter. So 32 meter is the length which we have used here. So I'm gonna give 32 meter length here. And now second is 9.5 mm. As you can see, 3/8 inches is 9.5 mm. If you convert this in inches to mm, it will be 9.5 mm. So how as you can see, the length which we have gas side is 7.5. Since we are using the liquid side, so it's 19.9 mm, 19.9 meter, sorry, not mm, 19.9 meter due to 9.5 mm diameter. How much length? 19.9 meter. So 19.9 meter. Now I'm going to take the third length, that is half inches. Half inch is nothing but it's 12.7 mm, as you can see over here. And here it's half inches, and first one is for the gas, second is for liquid. So liquid size, how much is the length? That is 13.5 meter due to half inches, that is 12.7 mm dia, 13.5 meter length. And now go to L4. L4 is due to the dia 15.9 mm. 15.9 mm is same as 5/8 inches. If you convert this in mm, it will be 15.9 mm. So 5 by 8, how much is the length on the liquid size? That is, total is 28.8, gas side is 19.9 meter, which we have and you know that these lengths which we have calculated from this project which we have created before in my last video. So every data is in the table form which we have created in last video. So now this is L4 due to the dia 15.9, that is 5 by 8 inches. So liquid side length is 8.9 meters. You can see over here 8.9 meter. So 8.9 meter, and L5 is the length due to the dia 19 mm. 19 mm. 19 mm is nothing but it's 3 by 4 inches. As you can see that gas side there is no length, that is 0. We did not use any dia 3 by 4 for the gas, but for liquid it's 6 meters length we have used for 3 by 4 inches, so 6 meter. And the last one is L6. L6 is due to the diameter 22.2 mm, and if you convert this into inches, 22.2, it will be 7 by 8, and as 7 by 8 inches, 22.2 is 7 by 8 inches. As you can see that gas side we have 10.8 and liquid side is 0, so we did not use any liquid pipe with 7 by 8 inch, so this length is 0 used in our project. So I'm gonna give this one as 0. So as you see that I have provided all the lengths, and I have applied the formula over here, all lengths we have. Let me tell you again, this L1, the formula which we have used here is, that is length L1 due to the dia 6.4, because this is the real length of liquid pipe, dia 6.4. This is 32 meters. As you know that per meter due to the dia 6.4, how much additional refrigerant charge is needed? 0.025 kg. So we have 32 meters, so 32 into 0.025, you will get the additional refrigerant needed due to the dia 6.4 having length 32 meters. So in the same way, length L3, that is 13.5 meter used here, and this is the additional refrigerant needed 0.105 per meter, 0.105 kg per meter length of dia 12.7. Since we have 13.5 meter used in our project, so 13.5 into 0.105, so this will give you the additional refrigerant charge needed due to the dia 12.7 mm having length 13.5 meters. So all of this you have to add, and then in the last, as I told you, you have to add the compensation by the horsepower of the system. So since we have if you go over there and you will see we have selected 26 horsepower system here. As you can see over here, outdoor unit is 26 horsepower, and it's break down into two outdoor units, that is 14 horsepower and 12 horsepower. And you know that this is the standard efficiency model we have used, not a high efficiency model. So this is the standard efficiency model table, and outdoor unit which we have used over here is 26 horsepower, and you know that it's 14 and 12 break down into two outdoor unit, and you see that compensation by the horsepower is 8.5. so this 8.5 you need to add over here to get the additional refrigerant needed for your piping. As you can see that I have added this G17. G17 is this value due to the system horsepower, 8.5 kg additional refrigerant needed. So you can see over here the additional refrigerant needed is 14.7 kg, which we have calculated over here. And if you go over there from our software, we have calculated here is additional refrigerant is 14.76 kg additional refrigerant, 14.7. so here also 14.7. so we just compare this one with the software result. So this is how you can calculate the additional refrigerant needed for your system. In this video I will tell you guys how you can calculate the refrigerant line size. So in this example particularly we will calculate the liquid line size. Also we will calculate subcooling required at TX valve for proper operation. So let's start. As you can see in the figure, we have a condenser over here and the evaporator over here that is higher than condenser with a riser of 20 feet. And you can see that this green color is a liquid line, and the liquid line is consists of following components over here. You can see that is 22 feet of piping, 7 long radius elbows, 1 filter dryer, 1 side glass, and 1 globe type isolating wall. How we have 7 long radius elbows? As you can see, this is the 1 elbow, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. So we have 7 long radius elbows over here. So let's move back to our Excel sheet over here. So this is our design parameters. Evaporator operated at 40 degree Fahrenheit, condenser operated at 120. Material we are going to use is copper. Refrigerant of 10A we are going to use, and the system capacity is 60 tons. And the system capacity we have calculated, we have already calculated using Hvac software, so we know that system capacity is 60 tons. So over here refrigerant of 10A, we have write the components and the number of components used over here. Then before giving this equivalent length for each component, let's move forward and first calculate the estimate pipe size over here for 60 ton capacity. So let's move over here. There we have a refrigerant line size table R410A refrigerant. So as you can see that this is for suction line, this is for discharge line, and this is for liquid line. And you see over here we have a pipe dia in inches, and over here inside this is the system capacities. So we have to follow this liquid line, and our system capacity is 60 ton. We know it will be in between 45.8 and 79.7. As you can see over here, I have highlighted here. So we will not go for 45.8, we will go for 79.7, higher side, safer side. So for 79.7, as you can see, 1 3/8 is the pipe size, so we can use this 1 3/8 inch pipe size. So let's move back over there and see 1 3/8 inch is the pipe size we are using over here, and actual system capacity, you know that it's 60 ton. And the table capacity is the same. We know that it's 79.7 ton. This is the table capacity we have used over here for 1 3/8 inch. So we have to write this table capacity 79.7. So we have write 79.7, and this table is for 100 feet length. So we have to write this table length also 100 feet over here. Now we'll move to equivalent length now. As you can see over here, down there I told you this 22 feet piping, straight piping length. So we have write 22 feet over here. So long radius elbows we have 7. So what is the required length for each long radius elbow? Let's move back over here. And there you can see required length for the fittings. Smooth elbows 90 degree elbows for 1 3/8 inch. This is the required length 2.3 for 1 3/8 inch. So this one we are going to use 2.3. As you can see, 2.3. So for filter dryer, side glass and solenoid valve we have to check. This is the equivalent length for the valves and other devices. As you can see, one 3/8 inch, 38 feet is for global solenoid valve. So this is a 38 for global solenoid valve. Now go for side glass. For side glass, for filter dryer core it is 35 and side glass it is 2.5 for one 3/8 inches. So 2.5 for the side glass and 35 for the filter dryer core. As you can see, 35 for filter dryer core and 2.5 for side glass. So if you multiply this number of items with this equivalent length, you will get fitting equivalent length for each and every component. So simply multiply this with this, you will get to the fitting equivalent length. And if you will sum all of these components equivalent length, you will get total equivalent length in this column, that is 113.6. So up till here it's done. Now table length it's done. Now table delta T. What is the table delta T? It's 1 degree Fahrenheit. How it comes, I'll tell you. Let's move back over here. As you can see, for the liquid line we have used this 1 degree Fahrenheit delta T. So we have to write for table delta T, that is 1 degree Fahrenheit. These are the system capacities. So this one we have used over here, 1 degree Fahrenheit. So this one we have to write 1 degree Fahrenheit. Now actual delta T, this is calculated by using a formula. I will show you what's the formula I have used over here to calculate actual delta T. This is the formula I have used over here for calculating the actual delta T. We know the actual capacity, table capacity, we know actual length, we know table length, we know table delta T. So all of these components we know. So by putting the values we can calculate delta T actual. So this is the formula I have applied over here to calculate delta T, actual delta T. Now we have to calculate the pressure drop from the table. So this is 4.75. How it came I will tell you. As you can see over here, for 1 degree Fahrenheit, what is delta P? As you can see that pressure drop. This is the pressure drop. This 4.75. So 1 degree Fahrenheit, what is the pressure drop for R410A refrigerant? That is 4.75 psi. So this one we have to use for the table. Delta P 4.7 psi. This is the 4.75 psi. Now actual piping pressure drop we have to calculate. This also calculate by using a formula. I'll show you the formula. This is the formula we have used over here for pressure drop actual calculation. So pressure drop for the table, delta T actual divided by delta T table. Actual delta T we have already calculated from this formula. Delta T table we know that it's 1 degree Fahrenheit, and pressure drop from the table we already checked from the table, that is 4.75 psi. So putting all these values you will get actual delta P. So this is how you can calculate actual delta P. As we know that riser height, we'll move back to our diagram over here. Riser is also used over here. So what is the riser height used over here? That is 20 feet riser. So we have right 20 feet riser height, refrigerant pressure drop per feet. Again we have to use a table for this one. What is the refrigerant pressure drop per feet? Since we are using R410A refrigerant, so we have to check what is the pressure drop for this refrigerant per feet. So move back over here, go down. There's a one more table, this one, pressure drop in liquid line by refrigerant. As you can see, we're using R410A refrigerant, and there is a pressure drop that is 0.43 psi per foot for R410 refrigerant. So we have to write this one, 0.43 psi. So we have write this 0.43 psi per foot. So if we multiply this refrigerant pressure drop per feet multiply with this riser height, will get a pressure drop from the riser. So multiply these two, will get pressure drop from the riser 8.6 psi. So multiply 0.43 with 20, will get 8. So let's move forward. We have calculated this pressure drop from the riser. Now we have to calculate what will be the total pressure drop in the liquid line. So in order to calculate this total pressure drop, you have to sum from the riser and actual pressure drop. So you have to add these together, actual piping pressure drop plus pressure drop from the riser. These two add together, you will get total piping pressure drop. So 3.23 plus 8.6, you will get 11.4 psi, 11.84 psi. So move forward. Saturated pressure at 120 degree Fahrenheit. We know that condenser operate at 120 degree Fahrenheit. So this is the saturated pressure at condenser. So we want to calculate now saturated pressure. What will be the saturated pressure at 120 degree Fahrenheit? We can calculate this by using PT chart. So let's move back over there. Here we have a PT chart. We will go for R410A refrigerant. So this is R410A refrigerant, as you can see. So this is the temperature in Fahrenheit. So we are going to use 120 degree Fahrenheit. What is the pressure for R410A refrigerant? As you can see, this is the pressure 418 psi is the pressure at 120 degrees Fahrenheit. So this is we have to use over here 418 psi. So we have used 418 psi over here. Now saturated pressure of refrigerant at TX valve. How we'll calculate this one? We have to subtract 418 minus, we have to subtract this 418 minus total pressure. You will get saturated pressure of refrigerant at TX valve. So saturated pressure at 120 degree Fahrenheit minus total pressure, you will get saturated pressure of refrigerant at TX valve. So move forward over there. Now saturation temperature at TX valve. How you will calculate this one? Now we know what is the saturated pressure of refrigerant TX valve, that is 406. So from the PT chart we can calculate the saturation temperature at TX valve. So move back. What is the pressure? 406. 406. As we can see that we have 391 and 418. So we have to perform iteration in between 115 degree Fahrenheit, 120 degree Fahrenheit, 391 psi and 418 psi. I hope you guys know how to perform the iteration. It's quite easy. If you don't know, then let me know. I will tell you how you can perform the iteration to calculate this delta P, that is pressure drop. So this is how you can calculate. Move back. Okay, so after performing the iteration, you will get 117.8 degree Fahrenheit saturation temperature at thermostatic expansion valve by performing the iteration. If you don't know about the iteration, let me know. I will tell you how you can do it. So let's move back over the actual saturation temperature for the condenser is 120 degree Fahrenheit, we know. So this is now we are the final step of calculating the subcooling. Now the subcooling for saturated liquid at thermostatic expansion valve is 2.2. How it comes up? So we have to actual saturation temperature minus saturation temperature at TX valve. You will get subcooling for the liquid at TX valve. So as you notice, this 2.2 degree Fahrenheit is the amount of the subcooling required to have saturated liquid refrigerant at TX valve. it is less than 2.2, refrigerant will start to flash and TX valve will not operate properly. For TX valve to operate properly and to avoid diaphragm flutterings, there should be an additional 4 degrees Fahrenheit of subcooling. So the minimum system requirement we have to add over here. We have to add additional 4 degrees Fahrenheit for thermostatic expansion valve to work properly. So the minimum system requirement is 4 degrees Fahrenheit. So what is the actual subcooling for the proper operation of TX valve? It will be minimum system requirement plus is subcooling for saturated liquid at TX valve. So this is 6.2 degrees Fahrenheit is the subcooling required for proper operation of thermostatic expansion valve, so that refrigerant will not flash. So this is how you can calculate this liquid line size and subcooling. In this video I will tell you guys about the fresh air CFM calculation. So there I have opened the drawing for the school project. I will show you our different areas for fresh air CFM calculation. So let's start. So first I will calculate the fresh air CFM for this chemistry and bio lab. So in order to calculate the fresh air CFM, I have made this Excel sheet as you can see over here. What we need over here is the room area, CFM per square feet, number of persons and CFM per person, and total fresh air will be the sum of CFM1 plus CFM2. So let's start for chemistry and bio lab. As you can see the area of this chemistry and bio lab from here. This much is the width, 10.9 meter is the width of this lab, and 13.2 meter is the length of this lab. So area will be 8.4 times 13.2. That is 110.88 square meters. Also this area is also included, so this is 300, that is 3 meter by 1.6 meter is this area, plus 1.5 meter into 1.4 meter is this area. So that total area will also be added in the chemistry and lab, because this is a part of this chemistry and bio lab area. So let us add this area, that is 3 meter by 1.6 meter, that is 4.8 square meters, plus 1.5 into 1.4 meters, 4.8, 1.5 into 1.4 plus 4.8, that is 6.9 square meters. 6.9 square meters, plus we have already calculated that area, 8.4 into 13.2, 8.4 into 13.2, 110.88 plus 6.9. So the total area is 117.78 square meters, but we have to put that area over here in the square feet. So in order to convert that square meters into square feet, we will multiply it by 10.76. So 1267 square feet is the area of this lab, 1268. Okay, now go for computer lab and classroom. So I will show you one more over here, that is computer lab. As you can see, the length of the room is 1.2 meter, 12 meters sorry, and width is about 8 meter. So total area will be 8 meter by 12 meter, that is 96 square meters, but we need to convert this into square feet, so multiply it by 10.76. So we'll get 1033 square feet. 1033 square feet. Now I will calculate one of the classroom also. As you can see, this is the classroom, and its length is 12 meters and width is 8 meters, so it's same as computer lab. So area will be same as computer lab. So let's move to the next column, that is CFM per square feet. For this I have opened this Hvac software. If you will go to the spaces and then go to new default space, from here we can select the ventilation requirement as per ASHRAE standard 62.1. So what we have over here is science lab, that is chemistry bio lab. So if we'll scroll down over here, as you can see, education science lab, that is chemistry bio lab. So we can select this over here, and you can see the CFM per person over here is 10 as per ASHRAE standard, and CFM per square feet required for science chemistry lab is 0.18. So 10 CFM per person and 0.18 CFM per square feet. So 10 CFM per person, and how much? 0.18? Yeah, 0.18 CFM per square feet. 0.18 CFM per square feet. As I have already applied this formula, this room area into CFM per square feet will get first CFM. You can see over here, this and this will get the CFM1, that is 228. Now if, how to get the number of persons? Usually from the architecture you can get the number of persons, how many persons will occupy this chemistry and bio lab and computer lab and classroom. So let's assume the number of persons in chemistry bio lab will be 15. So this CFM2 will be calculated as follow: this number of persons into CFM, you will get this CFM2. So total CFM, how you get this total CFM? Total CFM will be the sum of this first CFM, room area, into CFM per square feet, plus number of persons into CFM per person. So total CFM will be CFM1, that is 228, plus CFM2 150. So total is 378 CFM for chemistry and bio lab. In the same way you can calculate the computer lab and classroom. So I will show you again. Let's go for computer lab. In the education, so there it is, education computer lab, you can select from here. So CFM per person is 10, and outdoor air requirement is CFM per square feet is 0.12. So this is 0.12, and 10 CFM per person, and we use the same number of persons here also. So again, this CFM area of this lab into CFM per square feet will get CFM1, and number of persons multiplied by CFM per person will get CFM2, and total CFM for computer lab will be the sum of this CFM1 and CFM2, that is 273.96, 274 CFM. So let's calculate for classroom also. So this is the education classroom for grade 6 students. So let's go for classroom age 9 plus, and the CFM per person is 10, and CFM per square feet for classroom is 0.12. So it's again 0.12, and this one is 10 CFM per person, and number of person will take same, or we can check from architecture. So total CFM required for classroom is again 274. So if you need to calculate the total CFM for these three areas, chemistry bio lab, computer lab and the classroom, it will be the sum of these three CFM, that is calculated over here, is the sum. So this is how you can calculate the fresh air CFM for each and every room. So in the same way you can find the CFM for other classrooms In this video I will tell you guys how you can do AHU room sizing. So let's start. There's simple steps which we have to follow. First step which we have to follow is we have to find dehumidified CFM through heat load using Hvac software or E20 form. So after using the Hvac software, let's say we got 9000 CFM through heat load calculation. So we have to add 5% safety factor into this one to keep safe side. So in order to add this 5% safety factor, multiply 9000 with 1.05, you will get 9450 CFM. So for this CFM we will select AHU. There I have a catalog for air handling unit. It's a double skin modular air handling units provided by this Hvac air conditioning. So let's move down and select our air handling unit for that CFM. So let's say we are going to select this horizontal typical configuration air handling unit. Okay, as you can see that this is the liter per second, so you can convert this into CFM. This is our flow rate, and this is the height of the machine, this is the width of the machine, and this representing as length. So if you notice over here for this diagram, here A is representing as a fan motor compartment, B is representing as a coil compartment, and this C is representing the filter compartment for primary and secondary. And this is you can see that this is the returns duct area, this is the fresh air duct area, and this is the supply duct area. And you can see that E is representing the whole length of this air handling unit. So as we know that how much is the CFM, we got 9450 CFM. If I want to convert this CFM to liters per second, I will get 4459 liters per second. That's around 4460 liters per second. So move back to our catalog. Over here we got 4026 liter per second and 4598 liters per second. So we'll go for the higher side, will not go for the lower side. As you see that CFM liter per second we got is 4460, and over here we got 4598 liters per second. So this one is closer, so it's like this one 4598. So for this liters per second we got height of machine is 1.4 meter, that is 1400 mm, and width is 1900 mm, that is 1.9 meter. And as I told you, E is representing the whole length of this machine. So if we scroll down over here, this is the E, and how much we got over here is 3.9 meter. So this is our AHU dimensions. Length is 3.9 meter, width is 1.9 meter, and height is 1.4 meter. So move back over here. As you can see, AHU which we already selected from the approved supply data sheet for our calculated CFM of 9450 CFM. So width we got 1.4, height we got 1.9, and length we got 3.9 from the supply data sheet. So if we'll add 1.5 meter in all dimensions of air handling unit, we will get the room size for this air handling unit. As you can see that I have added 1.5 meter in the width, and 1.5 meter in the height, and 1.5 meter in the length. So total AHU room size will be 2.9 meter is the width, 3.4 meter is the height, and 5.4 meter is the length. In this video I will tell you guys how you can calculate duct size using a duct sizer program. So there I have opened a duct sizer program provided by the Hvac. So for the duct sizing, you must give this input like flow rate and the head loss in order to get your duct size. So for example, from the heat load calculation, I have calculated CFM 600, like 600 CFM for the particular room, and I want to calculate what will the duct size that is coming out from the machine. So for this purpose of 600 CFM from the supply data sheets, let's say we have selected a ceiling ducted fan coil unit FCU. So if we will go and give our CFM of 600 over here, and we move to the head loss of second input. Just keep in mind that for the head loss for the fan coil unit, it should be less than equal to 0.05 inches of water column per 100 feet. So this is your design value for the head loss. Head loss should not exceed 0.05 inches of water column per 100 feet, so that you will not get noise issues in your duct. Okay, we give this input of head loss 0.05 inches of water column per 100 feet. Now let's move to this duct size, and if we'll say 1 over here, and it will give the value for the other. For example, this is the width and this is the height. If I will change this one to 10, let's say 10 is the width and 15 is the height. So one thing you need to remember that for the duct size, you always need to get even numbers in the duct size. You will never see the odd number in the duct size like 13 inches by 15 inches or 9 inches by 15 inches, because this is a standard. So you always have to use even numbers in the duct. And second thing you have to keep in mind, aspect ratio during duct sizing. What is the aspect ratio? Aspect ratio is basically width to the height of the duct. And what is the best aspect ratio? Best aspect ratio is 1:1. Let's say our duct width is 400 and duct height is 250. So I told you aspect ratio is width to the height of the duct. So width is 400, height is 250. Let's say 400 divided by 250. So what's the aspect ratio? 1.6. So that's not bad, that's good. And what is the maximum allowable aspect ratio? Maximum allowable aspect ratio is 4:1. Don't exceed this more than 4, because if you will exceed more than if you exceed 4, then what will happen? You will get noise issues and more friction losses inside your duct. So maximum allowable aspect ratio is 4:1. So let's move and change this size to 12. As you can see, 12 by 12 we are getting the 1:1 aspect ratio. But one thing more we need to see over here, this is the calculated head loss, that is 0.05 inches of water column per 100 feet. And what is our specified? 0.05. So just keep in mind, this calculated head loss should be less than our specified head loss. So we still need to change the duct size over here. So what we'll do, we'll change this to 14. Let's say 14 by 10. 0.05 is still more than this, so we'll change this to 16. 16 by 9. So we don't want an odd number, as I told you before. Standard we have to give even number. So let's change this one to 10 inches. So this is the 600 105. Let's change this one to 10. So as you can see, the head loss calculated over here is 0.04, that is less than our specified head loss, 0.05 inches of water column per 100 feet. So this duct size is perfect to use over there. So what would be 16 inches by 10 inches? 16 inches, that is 400 mm, and 10 inches is 250 mm. So what would be the aspect ratio in that case? 400 divided by 250, that is 1.6. So aspect ratio is good, no problem. But sometimes you have to play with this aspect ratio because of the ceiling height issues. Sometimes ceiling height is very less. For let's say the ceiling height is 500 mm. So you will keep your duct height maybe restricted to 200 mm or 250 mm, because you need to give space for the other services to pass through. Like if any sprinkler pipe is passing over there or any chill water pipe passing over there, you need to give space to that service too. So, and from here you can change the units too, from metric to IPS units. So this is how you have to you can calculate duct size using a duct sizer program. In this video I will tell you guys how you can calculate this diffuser size, and you can select diffuser from the supply data sheets. So let's start. Let's take an example of this FCU 3FC L1. As you can see that we have got three diffusers over here, three supply and three return, three supply and then three return, two, and this is the third return. So I will tell you how you have got 9 by 9 inches for that diffuser. As you can see, the machine CFM is about 199 multiplied by 3, it's 597 CFM. So if you want to check the size of the diffuser for 199 CFM, because machine CFM is 597 and 597 divided by 3 we got 199. So we have got 3 supply return diffusers 9 by 9 inches 199 CFM each. So this is the formula we are going to use to calculate this diffuser or air terminal size. What the CFM we got over here is 199. So CFM divided by 400 multiplied by 144, and if you will take the square root of this one, you will get the diffuser size in inches. So how much we got over here is 8.46 inches. And if you know the standard size for the industry, it's 6 inches, 9 inches, 12 inches, and 15 by 15 inches, 18 by 18 inches, like this. So the diffuser which we can use over here is in between 6 inches and 9 inches. If you will go for 6 inches, it will be undersized. So we'll go for the higher side, so 8.5 inches. So we'll go for 9 inches. So this is how this diffuser size is coming. So 8.46 inches we are going to use, 9 inches, 9 by 9 inches supply return diffuser we are going to use over here. So let's move to another FCU to do the same exercise once again. As you can see that here we use 5 diffusers 179 CFM each, 9 by 9 inches. So let's check this one also. CFM divided by 400 multiplied by 144 and take a square root of this one, we got 8.02 inches. As I told you, standard size is 6 inches by 6 inches, 9 inches by 9 inches. So we'll go for 9 inches by 9 inches for this one. So as you can see that we have used 9 inches by 9 inches over here. So let's move to the supply data sheet, how you can select diffuser from the supply data sheet. As you know, the different type of diffusers we can use: ceiling diffusers, one way, two way, three way, or perforated ceiling diffusers like this, and different decorative type ceiling diffusers we can use. As you can see that this supply air ceiling diffuser 4-way is here, and this is the size in mm. 9 inches equivalent to about 225 by 225. So we'll go over here and let me zoom this one, and as you can see that this is the velocity in meters per second, this is the flow rate in meters per second, this is the velocity in meter per second, this is the pressure drop in the pascals, and this NC is the noise criteria in decibels. So we will have to go for 225 by 225, and we know that's flow rate for this one. If we want to convert this, as you know in the drawing how much it says, 199 CFM. So let's convert 199 CFM to liters per second. It will be 94 liters per second around. So if we'll go over there for 225, the 94 liters per second, it will be in between 92 and 104. So this is how you can select diffuser from supply data sheet, and noise criteria will be, if you will go for it will be less than 15 decibels. So between 92 and 104 it will come somewhere here. So you can also get the noise criteria in decibels, and you can also get the pressure drop in a pascals in between 9 and 11. It will be like 10 pascals. So it will also be helpful for you to calculate the fan ESP later on. So this is how you can do the diffuser sizing, and you can select diffusers from supply data sheet. In this video I will discuss about plenum box sizing. So before start calculation for plenum box sizing, I want to tell you what is plenum box and why we need to install the plenum box, and where we have to install the plenum box. So what is plenum box? Plenum box is a wide but short length duct that is used to properly or uniformly distribute the air throughout the system. Also, why we need to install the plenum box? There are many reasons that we need to install the plenum box. First, to ensure the air is uniformly distributed throughout the system. Second, to reduce the velocity of discharging air. And third is also to reduce the hissing sound created by discharging air just by dropping the velocity pressure. And also this plenum box also facilitate the fresh and return air mixing when system is designed for the return air circulation. So now the question arises, where we need to install the plenum box. We need to install this plenum box before air terminals, could be supply diffusers or linear slotted air diffusers. So we need to install before this supply diffusers or linear slotted air diffusers. These plenum boxes need to be installed before them. Also we need to install these plenum boxes at the suction side, at the suction end of the air side equipments like air handling units and fan coil units for the return and the fresh air. Also at the discharge and or the mouth side of the air side equipments. So we need to install these plenum boxes to air side equipments, also at the suction side of the exhaust air fans. So let's start the calculation of the plenum box. So what's the size required for the air handling unit? So here you see the procedure. Over here we are going to use the simple equation, that is Q is equal to VA. Here Q is the flow rate, that is in cubic feet per minute, and V is the velocity, that is feet per minute, and A is the area of the plenum box, that is in square feet. So this simple equation we are going to use to size the plenum box. So as per ASHRAE standard, the velocity required for the air handling unit plenum box sizing is 800 fpm, feet per minute. So we are going to use this velocity to size our plenum box. So let's say we have calculated the heat load, and according to our heat load the tonnage which we got is 8 TR. If you want to know how we have to calculate the heat load, you can check my tutorial number 16 and 17, in which I have explained how you can calculate the heat load using Hvac software and E20 form. So we are going to use our rule of thumb here, that is 1 TR required 400 CFM. So we have a 8 TR system, so how much is the CFM we needed over here for 8 TR system? That is 8 into 400, that is 3200 CFM that we needed over here. So according to this equation, Q is equal to VA. Now we have flow rate 3200 CFM, and we know the velocity required for plenum box sizing of the air handling unit is 800 fpm. So as per this equation, Q is equal to VA, we know Q and we know V, so we can calculate the area by A is equal to Q divided by V. Q is the flow rate, that is 3200 CFM, and V is the velocity, that is 800. So 3200 divided by 800, We got the area 4 square feet. So area of the plenum box that needed over here is 4 square feet. So before moving to this equation number 2, the area of the plenum box, that is width into height, I'll show you one figure over here. This is the figure. So let's say this is the plenum box of the air handling unit. As you can see that this is the width, this is the height, and this is the depth of the plenum box, and this is the opening that will be connected to the air handling unit side, suction side. So this is the width, this is the height, and this is the depth. So we need to calculate these parameters, width, height, and depth of the plenum box. So let's move back to our equation 2. So area of plenum box is given as width into height. So now we have to assume the height as per site condition. We need to assume the height. So let's say we have a space above ceiling and below slab is 2.5 feet or something. Let's suppose we have 2.5 feet space between the ceiling and the slab. So according to this, we need to assume the height of the plenum box. So let's say we are assuming the height of the plenum box is 1.6 feet. So this is the height we have assumed over here. So as we know the area of the plenum box, that's already calculated, 4 square feet, and height we assumed over here is 1.6 feet. So using equation 2, we know the width, we know the height, and we know the area. So we are going to calculate the width of plenum box, that is given as A by H. So width of the plenum box is area divided by height of plenum box. Area is 4 square feet and height is 1.6. So width of the plenum box is calculated as 2.5 feet, that is 4 divided by 1.6. So now we have width of plenum box, that is 2.5 feet, and we have height, that is 1.6 feet. Now we have to calculate this depth of this plenum box. So depth of the plenum box is given by this equation, that is 2.5 times d. Now what is d over here? D is basically a diameter of the fan blower of the air handling unit. So let's say we have a air handling unit of 3200 CFM with the diameter of the fan blower is 12 inches, and this in this formula d equal to 2.5 into 3, it could be 3 times d. So 2.5 to 3 you can use over here. So we are going to use 2.5 over here, and we assume that diameter of the fan blower is 12 inches. So by using this value in equation 3, so depth of the plenum box is 2.5 times 12, that is 30 inches. If you want to convert this in a feet, divide by 12 and you will get the depth of the plenum box 2.5 feet. So now we have calculated width, height, and depth. So depth is 2.5 feet, width is 2.5 feet, and the height which we have assumed is 1.6 feet. So this is how we can do the plenum box sizing for air handling unit. So if you want to do the plenum box sizing for the fan coil unit FCU, so you can do that also. The only thing over here is velocity, that is limited to 500 feet per minute, 500 fpm. So the whole procedure is same except the velocity, that is 500 feet per minute. So by using this velocity 500 feet per minute, you can do the plenum box sizing for the fan coil units. So this is how you can do the plenum box sizing. So a plenum box we need to install for properly or uniformly distribution of the air throughout the system. So this is how you can do the plenum box sizing of the fan coil unit and air handling units. So if you want to do the plenum box sizing of supply diffusers or linear supply diffusers, you can do in the same way. The phase velocity required for supply diffusers or linear slot supply diffusers, it is 2.5 meters per second, that is equivalent to 500 feet per minute. So you can use the same procedure above as explained above here in order to do the plenum box sizing of supply diffusers and linear slotted diffusers. In this video I will tell you guys about exhaust CFM calculation. So there I have a drawing in which I will show you for one of the toilet. As you can see that this toilet, its length is 200 centimeter and width about 130 centimeter. So it's 2 meter by 1.3 meter. This is the area of this toilet. So for exhaust CFM calculation, we know that the area of this toilet is 2 into 1.3. So it will be 2 into 1.3 2.6 square meters. So as per architectural drawing, we can see the height of the toilet wall is about 3 meters, so it's 3 meter. So in order to calculate the volume, that would be area into the height of the toilet. So as we know that area is 2.6 and height is 3. So 2.6 into 3 will get 7.8 cubic meter is the volume of that toilet. So in order to calculate the exhaust CFM, we have to use this formula, volume into air changes per hour divided by 60. But this volume, it should be in cubic feet. So in order to convert that volume into cubic feet from cubic meter, we need to multiply it by 35.28 conversion factor. So 7.8 into 35.28 will get 275.18 cubic feet. So as per ASHRAE standard for toilet, pantry, kitchen, we are taking air changes per hour is about 8 to 12. So this ACH is basically air changes per hour. So as I told you about from the ASHRAE standard, toilet, pantry and the kitchen, it's about 8 to 12. So we are going to take air changes per hour over here is 10. So this is the volume which we have calculated above. So we have to use this volume over here. That is 275.18 into air changes per hour, that is 10 for the toilet divided by 60. So how much we will get into 10 divided by 60, that is 45.86 CFM. So this is the CFM, exhaust CFM required for 2.6 square meters area of the toilet. So if you have seen my previous videos regarding duct sizing calculation, I can show you over here again by using this duct sizer program. So the flow rate, you know that 45.86, will use around 46 CFM, and head loss, as I told you, 0.06 inches of water column per 100 feet. If you have seen the previous videos, I have explained it over there. So as you can see that we have put this two parameters, flow rate and head loss. We can get the duct size over here. Let's say 6 by 8 by 3, no, 6 by 3, no, 4 by 6, yeah. If we change this one to 4, because we have to keep this in even numbers, so 6 by 4 inches is the good size for this duct. Or if you go for round, it will be 4.9 inches. Oops, sorry, 46 cfm 136. So it will be around 5 inches. So 5 inches will be round out, will be round off, and it will get 6 inches. So you will use 6 inches over here for that much cfm. So this is how you can calculate the exhaust cfm for the toilets. In this video I will tell you guys how you can calculate GPM for fan coil unit or air handling unit. So let's start. They have open drawing. As you can see that there I have a schedule for fan coil units. This is a schedule provided by carrier company. So as you can see that this is the unit description, this is the area served by the unit, the type of the unit, quantity, model, total capacity in MBH, airflow in CFM, water flow in GPM, ESP, that is external static pressure, motor power, and unit dimensions. So this is a summary or performance sheet for every block I have over here. This is for third floor and the fourth floor I'm showing you. So let me show you how we got this 2.43 GPM for this FCU. So before showing that, I want to tell you something over here. If you can see, in a case of district cooling, you can see that we are normally maintaining delta T of 16 degrees, and by using this formula 1 TR is equal to 24 GPM divided by delta T, we got 1 TR is equal to 1.5 GPM in a case of district cooling. And in a case of chillers, we are normally maintaining 9 to 10 degrees. So in a case of chiller, we got how much 1 TR equal to 2.4 GPM. So let's move back to our drawing. Just keep this thing in our case we are using water from district cooling, so we are going to use this formula 1 TR is equal to 1.5 GPM. Okay, as you can see that how much is the MBH over here for this machine, that is 19.47. So 19.47, if you divide this by 12, you will get the tonnage. So how much tonnage you got over here is 1.6225. As I told you, 1 TR is equal to 1.5 GPM in a case of district cooling. So this is the tonnage we got. Multiply this by 1.5, you will get GPM. So how much GPM we got? 2.43. As you can see that 2.43 is the GPM over here. So let's move to another FCU. This is another FCU with getting MBH of 49.32 MBH. So 49.32 MBH, 49.32 divided by 12, you got the tonnage. Multiply by 1.5, you will get the GPM. So how much GPM we got here? 6.165, that is 6.17. As you can see, 6.17 GPM over here. So in the same way you can do for air handling units and all of the FCUs over here in the same way. So this is how you can calculate a GPM for fan coil unit or air handling units. Today I'm gonna tell you guys how to do water balancing, or how many tons do we have to open DRV for water balancing. As you know that DRV is installed on the return side of the terminal unit and used for water balancing purpose. Usually air water balancing in the building is done by a third party, a testing commissioning company. Then they submit the report. As an engineer, we should know they balance DRV correctly or not, because if they balance DRV correctly, we will get the exact design flow rate. So the formula which we are going to use over here is this formula, that is delta P is equal to Q divided by 0.1 into kVS whole square. So what is delta P over here? Delta P over here is representing as signal or differential pressure, and Q is the flow rate, but remember this flow rate in cubic meters per hour, and this kVS is signal coefficient, and we'll get this value from the supplier. for double regulating valves for different sizes. So this is the formula which we are going to use over here to know that how many turns do we have to open DRV for water balancing. So let's say we got Q equal to 0.75 liters per second. As I told you, this Q in this formula should be in cubic meter per hour. In order to convert this Q into cubic meter per hour, we have to multiply this 0.75 by 3.6. So we'll get how much. We'll see 0.75 into 3.6. We will get 2.7 cubic meter per hour the flow rate. 2.7 cubic meter per hour is the flow rate we are getting over here. So if we'll put the values into this formula, but before putting the values, we should check the KVS from the supplier data sheets. So let's say that as you can see that this is the chart over here for double regulating valve for different sizes. This is for half inch, this is for 3/4 DN20, this is for 1 inch DN25, and this is for 1/4 DN32. So let's say that we have a pipe size over there is 1/4 DN32. As you can see that over here, what is the KVS for 1/4? It is 16.7. 16.7. So this is the value which we have to use over here. So let's move back to the formula. 16.7. okay, so 0.1 into KVS, that is 16.7. so we got 1.67. so Q divided by 1.67, Q is 2.7 divided by 2. How much we got before? 0.1 into 16.7, 1.67. 0.67. Now we have to give the square root of this one. So if we'll get the square root of this one, we'll got 2.6 answer over here. So delta P we got over here is 2.6. So what does that 2.6 means over here? That means we have to open DRV 2.6 tons to balance the water to that DRV. And let me tell you over here why water balancing is important. Water balancing is important to ensure that chilled water system deliver correct flows to all terminal units in our HVAC circuit, and so that our control valve will work properly, which in result correct output of the energy to the space. So this is very important to do the water balancing. So this is how you can check how many times we have to open DRV for water balancing in terminal units and coil units, air handling units. In this video I will tell you guys how to calculate the chilled water pipe size. So let's start. But before starting, I want to show you something over here. I already explained this thing in the previous tutorial, but I will explain you again. In a case of district cooling, we are using 1 TR is equal to 1.5 GPM, and how this comes by using this formula. TR is equal to 24 GPM divided by delta T. So in a case of district cooling, we are normally maintaining delta T of 16. So if we are going to use delta T 16 over here in this formula, so we will get 1 TR is equal to 1.5 GPM. That's the case of district cooling. So same formula we are using over here. If we are using chillers, so delta T will be 9 to 10 degrees. So by using this 10 degrees over here in this formula, 24 GPM divided by 10, you will get 1 TR is equal to 2.4 GPM in a case of chillers. So let's start this pipe sizing over here. There I have an Hvac drawing. I'm going to do the pipe sizing for few pipe segments over here. So before doing that, I will show you a schedule over here. for all the FCUs. As you can see that this is total capacity in MBH, airflow in CFM, water flow GPM, and ESP in pascals, and motor power unit dimension, everything. So let's start with this machine, corridor machine. As you can see that its serial number is 3FBL2. It's a corridor machine, ducted unit, and its MBH is 29.39, and CFM is 1049, and GPM is 3.67. So let me show you how this GPM comes out before start the pipe sizing. As you can see that 29.39 MBH is the heat load for this corridor machine of 3FBL2. So 29.39 MBH is the heat load. If we divide it by 12, we will get the tonnage. So 2.44 ton for this machine. So if we are going to calculate this GPM, how this comes out, as I already explained you over here, we are using a district cooling system over here. So how much GPM is required for 1 TR? It is 1.5 GPM is required for 1 TR, and we have a machine of 2.449 TR. So we need to multiply this tonnage with 1.5, so we will get the GPM. As you can see that the GPM is required for this machine is 3.67 GPM. You can see that 3.67 GPM. This is how you can calculate the GPM for each and every machine. In the same way you can do for other machines like Orchestrum 19 with 19.47 GPM. 19.47 is the MBH load. Divide by 12, you will get the tonnage, and if you multiply it with 1.5, you will get the GPM. That is 2.43 GPM is required for this machine. Over here you can see that 2.43 GPM. So let's move to the pipe sizing now. So I'm going to do for this corridor machine 3FBL2 corridor machine. Over here you can see that this machine is 3FBL2 corridor machine, the one I was talking in the schedule. So you can see that we already calculate the GPM for this machine, and the GPM required is 3.7 GPM for our calculated heat load. GPM required is 3.7 for this machine by district cooling system. So now we are going to see how this 3 by 4 inch pipe size is coming for this 3.7 GPM. So let me open this pipe sizer tool. So I have opened this pipe sizer. As you can see that we are using a black schedule 40 pipe over here. So we have already selected over here, and the fluid is at 50 degrees Fahrenheit water. So now we are going to check the pipe size required for 3.7 GPM. So if you can see that, but before starting this, I want to show you one thing, a design document, because we are going to do this as per our design document. So let me open this design document, general mechanical notes. These are the general mechanical notes. You have to open this and see what is the pipe sizing criteria mentioned over here. As you can see that for pipe sizes up to 50 mm, velocity of the water should not exceed 1.22 meters per second, and pressure drop not exceed 600 pascals per meter. And for pipe sizes 50 mm up to 200 mm, pressure drop should not exceed 400 pascals per meter, and velocity not to exceed 2.4 meters per second. So this is our limitation for do the water pipe sizing. We have seen this from our general mechanical notes. So we are going to do the pipe sizing as per this limitation. So whenever you are doing the pipe sizing, you have to keep this thing in mind. So let's move to our drawing. As you know, this machine has 3.7 GPM, So let's move to this pipe sizer. If we are using this half inches pipe size, and with the we are getting 1.4 US GPM over here. So if we are using our GPM, that is 3.7 GPM. As you can see, the fluid velocity is 3.91 feet per second. This is the calculated fluid velocity, and the head loss is 15 feet per 100 feet. As I already told you, our design document from the general mechanical note, it says if pipe size is less than 50 mm, velocity should not exceed 1.22 meter per second. If you convert this velocity in a feet per second, it will be 4 feet per second, and a pressure drop will be 4 feet per 100 feet. So if we move over there, fluid velocity is almost in the border, that is 3.91. Actually it is less than 4 feet, but head loss is too much, that is 15.039. that is not acceptable. So we are going to check 3-4 inch pipe size. If we use 3-4 inch pipe size and our GPM is 3.7, so we are going to use 3.7 GPM over here. As you can see, the fluid velocity now 2.23 feet per second. That is less than our specified fluid velocity, that is 4 feet per second from our this general mechanical notes. So fluid velocity is okay. Now move to the head loss. If we go for head loss, it is 3.757 feet per 100 feet. As I told you from design document, it is, if you convert this, it will be 4 feet per 100 feet. So head loss should be less than 4 feet per 100 feet. As you can see that this is 3.757 feet per 100 feet. So the pipe size which we have selected, 3-4 inches for 3.7 GPM, it is in the safe range. So we are good to go with 3-4 inch pipe size. You can also use this friction loss chart for closed piping system to check your friction loss. Let's say our GPM was 3.7 GPM over here. This is the flow rate, this is the head loss, and these are the pipe sizes over here. So our flow rate is 3.7 GPM, that will be below 4 GPM over here. And if we move to 3-4 inch pipe size, if this 3.7 GPM cross over here 3-4 inch pipe size, it will fall somewhere, it will fall over here just before 4, that may be 3.7 3.8 feet per 100 feet. So as you can see that we already checked over here, and the pipe sizer head loss is 3.757 feet per 100 feet, that is less than 4 feet per 100 feet. So we can use this pipe size 3-4 inch for 3.7 GPM. So let me show you one more over here. Okay, let's do a pipe sizing for these two pipe segments with the 22.9 GPM. Okay, go to the pipe sizer. If I select 1 inch 1/4 pipe size, and I am going to use 22.9 GPM, you can see that fluid velocity is 4.91 feet per second. That is more than 4 feet per second. 4 feet per second is our design limit. So, and also head loss 8.33 feet per 100 feet, that is more than 4 feet per 100 feet. So we are not going to select this pipe size for 22.9 GPM. Let's move to the higher side, that is 1.5 inches, and give our GPM 22.9 GPM. As you can see that fluid velocity is 3.61 feet per second and head loss is 3.874 feet per 100 feet. You can see that fluid velocity 3.61 is less than our specified fluid velocity, that is 4 feet per second, and head loss of 3.874 per 100 feet is less than our 4 feet per 100 feet. So we are good to go with this pipe size of 1.5 inches for 22.9 GPM. So if in the same way you can do the pipe sizing for other pipe segments, and you can use pipe sizer tool to calculate the pipe size.
In this video, I will tell you guys about the stairwell pressurization calculation or stairwell pressurization system design. So there I have prepared an Excel sheet, as you can see over there. So by using this Excel sheet, I will let you know guys how you can design stairwell system. But before start designing, you need to understand what is stairwell pressurization system. So stairwell pressurization system is basically intended to prevent smoke leakage through doors into the stairs by injecting a clean air into the stairwell, and the purpose is to provide the highest pressure in this stairwell area with respect to this adjacent space, so that we can provide a safe escape path to occupants and for firefighters, because in a case of fire, this area will be positively pressurized. There will be air sucked from the fans and it will be thrown into that area, and this area will be positively pressurized with respect to that area. So this area needs to be positively pressurized all the time in case of fire, so that no smoke will enter from these doors into the stairwell. So let's start the designing of the system. So first of all, you need to understand the design limitations. There I have prepared the design limitations that you need to understand. So stairwell pressurization system basically have the following design criteria. Delta P, minimum pressure difference between the staircase and adjacent space. As per NAFPA standard, it is 0.18 inches of water gauge, and the maximum pressure between the stairwell and the adjacent space, it should be 0.37 inches of water gauge. So this is the minimum pressure this pressure difference, and the maximum pressure difference with respect to the adjacent space. And the air, this is as per IBC, that is International Building Codes, and NAFPA standard 92A. So, and the airflow velocity should not exceed 200 fpm as per International Building Code. When the doors are open, airflow velocity should not exceed 200 fpm, and the maximum force required to open any door handle shall not exceed 30 lbs or 133 newton. So we need to keep these limitations in mind while designing the stairwell pressurization system. So there you can see the tables and formulas over here, which we are going to use to design the stairwell pressurization system. So let's take an example. So as you can see that this is the stairwell shown in this drawing. So there we have an office stairwell that runs 5 floors. Each floor has height of 17 feet. So total floor we have 5, and each floor has a height of 17 feet, and the width is 28 feet and length is 48 feet. So width is 28 feet and length is 48 feet. And we have as you can see, there are two single leaf doors, that is A2 and A3, and a one double leaf door that is 6 feet by 7 feet. This is a double leaf door, and single leaf door are 3 by 7 feet. So assume that the doors are open, and maximum differential pressure to maintain between the stairwell and the office is, this is the office space and this is the stairwell. So maximum pressure difference is 0.037, as I already told you over here. As per International Building Code IBC, maximum pressure difference between staircase and office space is 0.37, that is adjacent space is 0.37 inches of water gauge. So this is the formula which we are going to use to calculate the volumetric flow rate, that is Q1 plus Q2 plus Q3. So what is Q1, Q2 and Q3? Q1 is 2610 into A into leakage area. A is the basically leakage area of the building construction. It is the leakage area due to the walls and due to the floor. So this is the leakage area of the building construction, and delta P is the pressure difference which we have to use over here, as we already know that this is 0.037. So we have to use table 4 for the leakage area, and same formula we have over here, but this is due to the door, this is due to the building construction material, and this is due to the doors. When the doors are closed, then we need to calculate the flow rate through this equation, but table will be table 5 we are going to use. So this is table, this value will get by using table 4, and this value will get by using table 5. And Q3 is equal to V into A. This is simple formula. Q is equal to VA. Here A is the flow area in square feet, and delta P is the pressure difference in inches of water gauge, and V is the air velocity across open door. So as I already told you about, this velocity shall not exceed 200 fpm as per International Building Code IBC. This is the velocity we are going to use in this Q3. So let's move to our calculation. So first of all, we need to calculate the leakage area due to the building construction, that is due to the wall and due to the floor, that is Q1. And then we have to calculate the leakage area due to the closed doors. When the doors are closed, then we need to calculate the leakage area. So that is Q2, this is Q1, this is Q2, and Q3 will calculate later over. So first we'll calculate Q1 leakage area. First of all, we know that the height of the floor is that height of each floor is 17 feet. We have total 5 floors, and length is 48, width is 28. So first we will calculate the area. First we calculate the perimeter over here, perimeter of the walls. As you can see that this side is 48, this is 28, this 48, and this is 28. So perimeter of this stairwell area will be 48 plus 28 plus 48 plus 28. So perimeter of the stairwell walls will be 28 plus 48, 2 times, that is 152 feet. And we know that the height of each floor is 17 feet. So area will be 152 into 17, that is 2584 square feet. But we need to subtract the door area from the wall because we are going to calculate separately for the doors. So we need to subtract the door area. Door area is 84 square feet. How did we get this 84 square feet? Since we have 3 doors here, this is a double leaf, this is single leaf. 2 single leaf, that is 3 by 7, 21 square feet, 21 square feet. And double leaf door is 6 by 7, that is 42 square feet. So 42 plus 42, that is 84. So door area will be 84. So 2584 minus 84, the door area, we will get 2500 square feet wall area. So now we have to get the average leakage ratio, that is AL by A. How we will get this value? This value we get from the table 4. As you can see that this table is basically from NAFA 92 2012 book, table 4.6.1. Since the construction of our wall or the whole building, it's average construction, you can see that tight construction we need to use this value, average is this, loose is this. This is for exterior walls, this is for stairwell walls, this is for elevator shafts, and this is for the floors. So first we are going to calculate for the walls. So stairwell walls, average construction area ratio is 0.11 into 10 power minus 3. So same we have used over here, that is average ratio 0.11 into 10 power minus 3. So total leakage area will be calculated as, you need to multiply this average leakage ratio with the area of the wall which we calculated over here for the stairwell walls. So 0.11 into 10 power minus 3 into 2500 square feet. So total leakage area will be 0.28 square feet of the wall, stairwell walls. Now second, for the floor area, we know that it's 28 by 48. So floor area is 1344 square feet, and the average leakage ratio for the floor from table 4. So this is for the floors, and we know that this is average construction, so 0.52 into 10 power minus 4. So 0.52 into 10 power minus 4. So you just need to multiply area with this average leakage ratio. You will get the total leakage area due to the floor, that is 0.07 square feet. Now Q1 is done. Now we proceed for Q2, that is leakage area, leakage when the doors are closed. that is Q2. Since we know that height of single double leaf door is 7 and width is 6, and two single leaf doors we have, that is height 7 and width 3. So area calculations, this 33 is the, you can get this from table 5 here. 33 is basically the crack length. So this 33 feet is the crack length for the double leaf door from the table 5. So this is from the ASHRAE handbook. You can find these values in the ASHRAE handbook. There are a lot of doors are given in there. So according to the door size, you have to get the crack length, and then you have to use it in your calculations. So single leaf door crack length is 20 and the gap is 0.006. For double leaf door size 6 by 7, crack length is 33 feet and the gap is 0.006. So this is the crack length for double leaf door 33 and the gap is 0.006, and crack length for single leaf door, that is 20 and the gap is 0.006. We got these values from table 4 over here, table 5 over here. So how to get the leakage area when the doors are closed? We just need to multiply this crack length with the gap. So crack length into gap you will get for double leaf door, that is 0.20, and then for single leaf door, that is 20 crack length into gap 0.06, that will be 0.12. Since we have two doors over here, that is A2 and A3, two single leaf doors, so that's why we multiplied this with 2 to get the total leakage area when the doors are closed. So total leakage area, so what is the total leakage area? It will be the sum of all of these, that is due to the wall, floor, door. It will be 0.78 square feet. 0.78 square feet. So next, we already calculated this value area. So it, as I told you, this is Q1 and this is Q2, and this is the formula which we are going to use for Q1 and Q2. We already calculated, so we are going to sum this up. So we are going to use this same formula, 2610 into A, that is the total leakage area, into delta P power 1 by 2. So this is the constant value 2610, and the area we already calculated 0.78 over here, and delta P is the maximum pressure difference. As per International Building Code IBC, it is given as 0.37. So we are going to use this value. So after using these values, Q is calculated as 1243 CFM. This is for one floor only. So we know that we have 5 floors in this building. So total volumetric flow rate will be 5 into 1243, that is 6215 CFM. So total volumetric flow rate is 6215. But now we have to calculate Q3 also. Only then we will be able to calculate the total volumetric flow rate. So Q3 is given by area into V max. So A is the area of the door and the effective open area. So we know that we have 3 doors. A1 is the double leaf, A2 and A3 are the single leaf doors. So A1 is the double leaf, 7 into 6 feet, that is 42 square feet, and A2 and A3, that is 3 by 7, that is 21 square feet. So for doors situated in parallel around a pressurized space, the effective leakage area is given by this formula. Basically we have two formulas. When the doors are situated in parallel, we use this formula. When the doors are situated in series, then we use another formula. So I will show you over here. As you can see over here, we have two scenarios over here. First, leakage path in series, leakage path in parallel. So this is positively pressurized with respect to these adjacent spaces. So if it is positively pressurized, that means the air will flow from high pressure side to the low pressure side. So air will flow from here to here like this. So in order to, so it will not let any smoke to enter into the stairwell area. So this is the path in series. So if you have a situation like this, if your flow is in series, then you have to use this formula. A effective area is equal to 1 by A1 square plus 1 by A2 square plus 1 by A3 square. So it depends on number of doors. According to that you have to use the formula if you have leakage path in series. So this one, as you can see that stairwell is positively pressurized, air will flow from high pressure side to the low pressure sides, that is A2, A3, A4, A3. So it will continuously pressurize this area and it will not let any smoke enter into that area, lift lobby and stairwell area. So as you can see that this is the path, leakage path in the parallel, and we have the same situation or same scenario in our case. So we are going to use this leakage path in parallel. So leakage path in parallel, you have to use this formula, that is effective area is equal to A1 plus A2 plus A3 plus A4. So since we have this condition, that's leakage path in parallel, so we are going to use this formula, A equal to A1 plus A2 plus A3. So that's why we have used this formula, A equal to A1 plus A2 plus A3. So effective open area across doors is 84 square feet, that is the sum of these three doors area. Now the flow rate is given by Q3 is equal to Vmax into AE, that is Q is equal to VA formula. It's very simple and basic formula. So as I already explained you this thing in the beginning, that maximum velocity that needs to be considered when the door is open is 200 fpm. It should not exceed 200 fpm as per International Building Code section 909.7.2. So we are going to use Vmax 200. So we know that velocity, we know the area, so Q flow rate to the open door is given as Q is equal to V into A. So V we have here is 200 fpm and the area is 84. So total flow rate to the open doors will be 16,800 CFM. So now we will get the total air for pressurization system, that is leakage to the gaps in the building construction plus leakage around the door gaps plus leakage through the open doors, that is Q1 plus Q2 plus Q3. So we already calculate Q1 plus Q2, that is 6,215 and Q3 is 16,800. So total flow rate, volumetric flow rate required for stairwell pressurization system is 23,000 CFM. So this is the total flow rate we required for 5 floors. If we want to calculate for each floor how much is required, 23,015 divided by 5 floors, so 4,600 is the flow rate required for each floor. 4,600 3 CFM is required for each floor. So if you want to calculate the so we know that the volumetric flow rate for each floor is 4,603 CFM. So if you want to calculate the grill size, you can also calculate the grill size, because we need to place the grill on each stairwell area. Each stairwell area we will have a grill over here through which air will be thrown into that stairwell area to keep it positively pressurized. So we will have some grill over here. So fan will be at the top of the roof through which air will be induced or injected into that area with the help of a grill over here. We will have a grill over here like a supply grill. So if you want to do the sizing of this grill also, you can do that too. So velocity which we normally consider for grill sizing is 500 to 600 fpm. 500 to 600 fpm. So by using the same formula, Q is equal to VA. If you want to calculate the area is equal to Q divided by V. So Q we already know that for each floor, that is 4603 divided by velocity we are going to consider is 600. So total area is 7.67 square feet. Grill area is 7.67 square feet, will be approximately 8 square feet. So 8 square feet, that means it will be like we can say that 4 feet by 2 feet, or 4 feet means 48 inches by 24 inches. So the grill size which we need to place on each floor will be 48 inches by 24 inches size. So this is how you have to design your stairwell pressurization system.
Today I am going to explain you guys the duct traverse topic, like how to perform the duct traverse to get the accurate velocity reading, and then calculate the actual volume flow rate across the duct to compare it with the design airflow rate, and this we are doing for air balancing purpose. So let's start. As you can see that we have this duct, and if we want to perform a traverse on this duct, we need to make holes to get the flow rate, and the instrument which we are going to use to perform this traverse is the velocity probe or pitted tube. When you are using the pitted tube, it will give you the velocity pressure. Then the individual velocity pressure must be calculated for each velocity pressure reading and then averaged together to measure the velocity pressure and then converted into velocity in feet per minute. So as you can see that this is the duct which we have, and we have inserted the pitted tube inside to get the velocity pressure. As you can see that pitted tube basically measures the total pressure and the static pressure to determine the velocity pressure. So you can see that this is the manometer, and the positive port of the manometer is connected to the total pressure port. This is our total pressure, and this one is connected to the positive pressure port of this manometer, and the negative is connected to the static pressure. And when you insert the pitted tube inside, it basically senses the total and static pressure and the manometer over here, and it measures the velocity pressure. That is the difference between total and static pressure. When you insert the pitted tube inside the duct, make sure that this tip must be pointed directly in, and it should be parallel to the airflow rate. This is the airflow rate and this is the pitted tube. Make sure that it is parallel with the airflow rate. If you put the pitted tube accurately, then velocity pressure indications will be at its maximum. So when you are using pitted tube inside the duct, you will get the velocity pressure reading on this manometer. Then you need to convert this velocity pressure reading into the velocity, and then using Q is equal to V, a formula, you can get the actual flow rate. And so this is the table which we are going to use for duct traverse of rectangular ducts. As you can see that this is the whole quantity required, and this is the interval C, interval B, and this A is representing as the duct dimension. That is 10 inches, 12 inches, 14 inches. And this table, the duct size is applicable if duct size is less than 48 inches. And for this table we need to refer to figure 1. This is the figure 1, and the interval which I have explained above, that is B and C, you can check from here in this figure. This is the dimension of the duct represented as A, as you can see over here. If we have 10 inches duct size, then A will be 10 inches. Then we need to check how much is the interval B and interval C, and how many holes required for duct traverse. 4 holes required, and B is 1.25 and C is 2.5. So the B is a distance from the inner wall of the duct to the center of the first hole, that is 1.25. for 10 inches duct, and then C is from center of first hole to the center of second hole, that is 2.5 for 10-inch duct size, and the hole quantity is 4, we already know, so we have 4 holes, 1 2 3 4. So it depends on your duct dimension. If you have 30-inch duct size over there, then you need to make 5 holes with the interval B and C as B as 3 inches and C as 6 inches. And this table is applicable if duct size is less than 48 inches. If you have a duct size more than 48 inches, you still need to make 8 holes to perform the duct travels. But the interval B and C, if you need to calculate the intervals, that is hole to hole distances, and from the inner wall to the first hole and then from inner wall to the last hole distance, you need to get these distances from this figure. So as I already explained you, we can use either velocity probe or the fitted tube to perform this duct traverse. If you perform duct traverse with the velocity probe, you can get directly the velocity, but if you perform this with a fitted tube, you will get the velocity pressure, and then you need to convert this velocity pressure into the velocity by using this formula. That is, velocity is equal to 1096.7 into square root of hv divided by d, where v is the velocity in the feet per minute and hv is the velocity pressure in inches of water from the measuring device, and the measuring device which we use in the fitted tube, that is manometer, and d is the density of the air in pounds per cubic feet. If we are using this velocity probe, we can get directly the velocity readings like over here. So let's take an example. We have 48 inches by 40 inch rectangular duct, and we need to perform a duct traverse on this duct to get the actual flow rate and compare it with the design flow rate. So if you go for 48 inch duct size by 40 inch duct size, so let's take one dimension of this duct is 48 inches and move back to our table over here. So as per X-ray and SMACNA standards, for 48 inches duct size, hole quantity is required is 8, and the interval B and C is required as 3 and 6 inches. So number of holes required are 8. And for the second dimension, that is 40 inches over here, number of holes required are 7, and interval B is required as 2.85 and interval C is 5.71 inches. You can refer to this figure to calculate the intervals, that is B and C, for 40 inches and 48 inches duct dimension. So since the number of holes required for 48 inch duct dimension is 8 and 40 inch duct dimension is 7, so we need to make a matrix of 8 by 7, that is 56 number of points. We need to make a matrix of 56 points. As you can see that this is the position from A to H. We have total 8 points, that is representing as 48 inch duct dimension, and this is from 1 to 7, that is representing the duct dimension of 40 inches. So this is how we have created 56 number of points, that is 8 by 7 matrix. If you have 42 inches by 30 inch duct size, then you need to make a matrix of 7 by 5. So since we have 48 inches, the example which we are considering right now is 48 inches by 40 inches. That's why we have created 56 number of points, or 8 by 7 matrix. So after creating the holes, we need to insert that pitot tube inside to get the velocity pressure reading at the manometer. Let's say this is 48-inch dimension and the other is 40-inch the dimension, and we have 8 holes over here and 7 holes on the other side. So we need to insert the pitot tube at the first point here, that is called point A, and the other one is point 1. So if we put the pitot tube inside at point A1, we will get the velocity pressure reading at point A1, and then from A1 to next A2, then A3, then A4, then A5, then A6, and then A7. If we move to this point, this will be B point at 48-inch duct dimension. So we need to put that pitot tube inside at point B1. This is called B1. If you move inside more, it will be B2, then B3, then B4, and so on and so forth. We need to put the pitot tube one by one, and we need to get the velocity pressure readings at different points. So this is our matrix, and we need to put the reading whatever we got from pitot tube, but make sure that the reading which we got from pitot tube, it's in from the reading which we got from manometer, it will be in the velocity pressure. It will be the velocity pressure. So we need to convert this velocity pressure into the velocity by using this formula. So after using this formula, we will get the velocity in FPM. So let's say we got the velocity at point A1 is 885. This is just an example. You need to go to the site and you need to use this pitot tube to get the velocity pressure, and then you need to convert the velocity pressure into the velocity, and then you need to put that reading over here at point A1. So let's say at point B5 we got this reading over here, and then you need to write each and every reading over here, and after writing all the readings you need to sum at the point 1 and point 2, 3, 4, 5, 6, 7. So this is the duct traverse for 48 inches by 40-inch duct. So the number of points which we have taken for the reading are total 56. That is 8 by 7, and total number of points are 656. So we need to write number of points, reading points, that is 56. And now we need to calculate the average velocity. So we need to write the average velocity over here. So first we need to sum up all of these velocities. So the velocity which we have over here is 7244, and other point is 7442.9 and 7464, then 7263 and 6889.75, and then 6594.48, then 6437. So total velocity is this much, but we need to calculate the average velocity. Since we have taken 56 points reading, so we need to divide this with 56. So 881 feet per minute is the average velocity. So this is the average velocity across 48 inches by 40 inch duct. So let's say in the drawing we have a design airflow rate is 11,700 CFM. Now we need to calculate the actual flow rate across this duct by using this duct traverse method. So by using this equation, Q is equal to VA. Here Q is the actual flow rate that we need to calculate, and V average is the velocity which we have already calculated over here, that is 881 feet per minute, and A is the area of the duct, and V average, it is in feet per minute. We already calculated above, that is 881 feet per minute, and A is the area of the duct. So as we know that it is 48 inches by 40 inch duct. I will convert this into feet. 48 inches in the feet, it will be 4 inches, and the other one will be 3.33 feet. So 4 feet by 3.33 feet. So how much area we will have? That is 3.33 multiplied by 4. You will get 13.33 square feet area. So now we know the average velocity across 48 by 40 inch duct, that is 881 feet per minute, and the area which we already calculated here, that is 13.33 square feet. So we need to put the values in this equation, the average into area, that is 881 cross 13.33 square feet. So we'll get the actual CFM, 13.33 multiplied 881, so we got 11,746 CFM. 11,746 CFM. So the actual CFM which we got across this duct, 48 inches by 40 inch duct, is 11,746 CFM, and the design flow rate which was in the drawing is 11,700 CFM. This is just an example to show you how to perform the duct traverse. So this is how you can perform a duct traverse to get the velocity pressure from the pitted tube, and then convert this velocity pressure into the velocity, and you need to get the area of this duct, and using this average velocity in this equation you can calculate the actual flow rate across that duct and then compare it with the design flow rate. So this is how you can perform the duct traverse